There is a quiet story behind everything you see. Every solid object, every drop of liquid, every breath of air is built from particles too small to notice. Chemistry is the study of those particles, their patterns, their movements, and the invisible rules they follow. From early experiments in ancient alchemy to the organized science we know today, chemistry has always been about understanding change. Here, you don't need to rush. Just allow the foundations, atoms, elements, and reactions to unfold slowly, like a steady rhythm. You close your eyes and think of a kitchen, the soft hiss of boiling water, the way sugar vanishes into your tea, the tiny bubbles that rise from a glass of soda. None of this feels like a laboratory. And yet, every single one of those moments is chemistry doing its quiet, invisible work. Chemistry is not a subject you failed or a formula you memorized. It is the gentle conversation between all the stuff around you. How it touches, how it changes, how it stays the same even when it looks different. That ice cube melting in your palm? Chemistry. The smell of rain on dry ground? Chemistry. The slow warmth spreading through your chest when you drink something hot? That is chemistry too. Welcome to the Learn While You Sleep channel. Here, we do not demand your attention. We simply invite you to rest deeply and let the hidden patterns of the material world drift through your mind like leaves on a calm river. No grades, no pressure. Just the soft rhythm of understanding, wrapped in the kindness of night. This is a space where curiosity meets comfort, and every small observation lands gently, like a snowflake on warm glass. You have probably heard that everything is made of chemicals, and that word sometimes feels scary. But think of a single grain of sand. It is small, almost nothing. Yet inside that grain, atoms are holding hands in a pattern older than the mountains. Chemistry is the study of those handholds. It asks, what happens when two things meet? Do they bounce apart? Do they cling? Do they transform into something entirely new? If this quiet exploration fits your late-night mood, you might let me know by subscribing or pressing the hype button. It helps keep these stories flowing. And if you feel like sharing, where in the world are you listening from? Is it late and quiet, or early and bright? Are you here to study, to relax, or just to drift for a while? You can write it softly in the comments, like leaving a small note in the dark. You already know the answer when you see a candle flame flicker, when you smell bread baking, when you taste a lemon's sharp surprise. These are not mysteries. They are invitations. The world is constantly whispering its chemical secrets, and you have been hearing them your whole life. Consider a cup of coffee left on a table. By morning, it is cold. That seems simple. Heat left the cup. But where did the heat go? It traveled into the air, the table, and the room. The warmth did not disappear. It spread out, like a crowd leaving a stadium. Nothing is ever truly lost. The steam from your shower becomes humidity, then clouds, then rain. The smoke from a candle becomes invisible gases that trees will breathe. Even the cells that fall from your skin break down into molecules that feed tiny organisms in the soil. You are part of a continuous, ancient cycle of transformation. The study of matter began not in a laboratory, but around campfires and cooking pits. Early humans noticed that wet clay became hard pottery, that raw meat changed when heated, that certain stones produced sparks. Each observation was a tiny seed of chemistry, planted without knowing it would grow into a vast tree of knowledge. You share that same instinct when you adjust a recipe, when you add salt to melt ice, or when you mix cleaning vinegar with baking soda just to see the fizz. That fizz is carbon dioxide gas being born, a chemical reaction you can hear and touch. Chemistry is not distant. It is the quiet intelligence of your own hands. Sometimes people think chemistry is only about explosions, but most chemistry is slow, patient, almost shy. The rust forming on a forgotten bicycle wheel, the way bread goes stale hour by hour, the gradual fading of a photograph left in sunlight. These are all chemical reactions, just happening at a pace that does not startle you. There is a tenderness in that slowness. The universe does not rush. It transforms in its own time, and you get to witness small pieces of that transformation every day. Tonight, as you rest, you can let those slow changes be a lullaby. Nothing is abrupt. Everything is just becoming something else. A question to carry softly into sleep. If you could see one invisible chemical change happening around you right now, the air interacting with surfaces, the moisture gathering on your window, the subtle shift in temperature as your body prepares for rest, what would that look like in your imagination? Why humans became obsessed with matter. Long before anyone knew what an atom was, people picked up stones and wondered, why is this one heavy and this one light? Why does this metal melt over a fire while this clay hardens forever? You have probably done the same thing without noticing, rubbing a smooth pebble between your fingers, pressing your palm against a cool wall, feeling the difference between your cotton sheets and a wool blanket. That simple curiosity, the need to understand what things are made of, is older than language. It is what kept our ancestors alive. They learned which rocks made sharp tools, which wood burned slow and hot, which water was safe to drink. Over thousands of years, that survival knowledge turned into something deeper, a desire to know not just what things do, but what things are. Picture a child on a beach holding a handful of wet sand. The sand drips through her fingers, and she watches it fall. She does not know the word particle, but she sees that the handful is made of countless smaller pieces. That is the beginning of obsession. The moment you realize that the big world is built from tiny, repeatable units. Humans became obsessed with matter because matter is the only thing we can touch, taste, and transform. You cannot hold a thought, but you can hold a piece of iron. You cannot see a dream, but you can see water turn to steam. That tangibility gave our ancestors a sense of control in a wild, unpredictable world. If you understood clay, you could make pots. If you understood metals, you could make swords. If you understood herbs, you could make medicine. Every step forward was a quiet victory of observation over chaos. Even now, in the comfort of your room, that same obsession whispers. You check the temperature of your tea. You notice whether a surface feels rough or smooth. You might tap a glass to hear its ring. These are not random actions. They are tiny experiments, repeated millions of times a day by every human on Earth, all asking the same question. What is this stuff, and what can it do? The obsession with matter is not a cold scientific urge. It is warm and practical. It is the reason you know not to touch a hot pan. It is the reason you add salt before boiling pasta, because you have observed, perhaps without thinking, that salt raises the boiling point and seasons the food from the inside. That is chemistry living in your daily rhythm. The word chemistry may trace back through Arabic alchemia to the ancient Egyptian chem, meaning black earth, the fertile soil of the Nile Valley. So chemistry is, at its root, the study of black earth, the study of ground you can stand on. the study of the stuff beneath your feet. That humble origin suits the science well. Chemistry is not about rare or exotic things. It is about the ordinary world, the dirt, the air, the water, the fire, and how they dance together. When you walk barefoot on grass, when you scoop a handful of soil, when you watch a puddle dry in the sun, you are engaging with the oldest laboratory on the planet. The obsession with matter also gave birth to trade, to metallurgy, to cooking as an art form. When early humans realized that certain rocks contained shiny metal that could be shaped and hardened, they began traveling hundreds of miles to find those rocks. They traded them like treasure. They built entire civilizations around copper, then bronze, then iron. Your own world, your phone, your keys, the springs in your mattress, exist because someone, thousands of years ago, became obsessed with a green rock that melted into a golden brown metal called copper. That obsession never ended. It just got softer, quieter, more refined. Now it lives in you, in the calm curiosity that made you press play on this recording. Every object you see, from the heaviest piece of furniture to the lightest feather, is a temporary arrangement of atoms that have existed since the first stars exploded. That is not a fact you need to memorize. It is just a feeling you can rest in. The feeling that you are holding something ancient, something borrowed, something that will eventually become part of another table, another feather, another person. There is no hurry. The atoms do not mind waiting. They have waited billions of years already. The first questions about what things are made of. You do not need a degree to ask a deep question. A child staring at a single fallen leaf might wonder, where did this leaf come from? Where will it go when it crumbles? That same wonder lived in the first humans who ever looked at a rock and asked, can this rock be broken into smaller rocks forever? Or is there a smallest piece? That is a beautiful, impossible question. Because if you keep breaking a rock, you eventually get dust. Break dust, you get something finer. But your mind knows there must be an end, a point where you cannot split something without changing what it is. That invisible finish line is the beginning of all chemistry. Imagine holding a loaf of bread. You tear it in half. Then you tear that half. Then you keep tearing smaller and smaller until you have crumbs, then dust, then something your eyes cannot see. At what moment does it stop being bread? At what moment does it become just a collection of tiny pieces that used to be bread? That question haunted ancient thinkers for centuries. They had no microscopes. They had no electron scanners. They only had logic and observation. And yet, some of them arrived at an idea so brilliant that it still holds true today. The idea that matter is made of indivisible particles. In ancient Greek, those particles were called atomos, uncuttable. You know them as atoms. The first recorded person to propose atoms was a man named Leucippus, and then his student Democritus, around 400 BCE. They argued that if you kept cutting a piece of matter, you would eventually reach a point where the piece could not be cut anymore. Not because your knife was dull, but because the universe simply does not allow anything smaller to exist as that same substance. That is a radical thought. It means there is a flaw beneath reality, a smallest possible unit of something. Democritus believed that atoms were infinite in number, constantly moving, and came in different shapes and sizes. Smooth atoms made sweet things. Sharp atoms made sour things. Heavy atoms made metals. Light atoms made air. He had no evidence. He could not see atoms. But his mind reached across 2,000 years and guessed correctly. Democritus was known as the laughing philosopher because he believed that cheerfulness was the goal of life. So the man who first imagined atoms also thought that joy was the highest wisdom. That is a comforting thought for a sleepy mind, that the deepest questions about the universe can be asked with a smile, not a furrowed brow. Other ancient cultures asked similar questions without calling them atoms. In India, the philosopher Canada wrote about Anu, tiny indestructible particles that combine to form everything. In China, the Mohist school of thought proposed that matter was made of G, minimal units that could not be halved. These ideas emerged independently, separated by mountains and oceans, because human beings everywhere face the same physical world and the same curiosity. When you look at a smooth stone or a drop of rain, you are sharing an experience with every human who has ever lived. The questions are the same. Only the answers get better over time. One of the most beautiful things about early chemistry is that it did not need to be right to be useful. Even when people believed in 4 elements, earth, water, air, fire, that belief helped them organize their observations. They learned which plants grew best in which soil. They learned how to ventilate rooms for fresh air. They learned that water could be purified by boiling, and that fire transformed almost everything it touched. The wrong theory still produced right results. That is a comfort, perhaps. You do not need to understand everything perfectly to benefit from asking the questions. The asking itself is the medicine. As you rest here in the dark, consider the first person who ever asked, "What is this made of?" That person had no name, no university, no grant money. They might have been a potter watching clay dry, a cook watching dough rise, a child watching frost form on a leaf. They did not know they were starting a conversation that would eventually reveal atoms, molecules, and the periodic table. They just wondered. And you, in your quiet room, are wondering too. That chain of wonder has never been broken. It passes from hand to hand, from generation to generation, from that anonymous potter to you. The next time you pick up a spoon or a fork, you might feel a different kind of weight. Not just the weight of the metal, but the weight of billions of years of travel. Atoms that have been inside stars, inside oceans, inside dinosaurs. Now they are in your hand. That is not science fiction. That is just chemistry, doing what it has always done, holding things together long enough for you to hold them. Ancient ideas of elements, earth, water, air, fire. The world feels so full of different things. Wood, stone, bone, shell, wool, clay, metal, dust. Each one unique, each one with its own behavior. It would be easy to believe that everything is completely different from everything else. But ancient minds saw a hidden simplicity. They looked at the endless variety and said, perhaps this is all just 4 things mixed in different amounts. That idea, earth, water, air, fire, is one of the oldest surviving theories of matter. It is wrong by modern standards, but wrong in a beautiful, useful way. Picture a candle burning. You see the solid wax, earth, the melted pool, water, the smoke and heat rising, air and fire. In one small object, all 4 elements appear together. That is why candles were such powerful symbols for ancient philosophers. They showed transformation. The solid becomes liquid. The liquid becomes gas. The gas feeds the flame. And when the candle is gone, nothing has been destroyed. It has just returned to the 4 elements, waiting to become something else. That cycle was deeply comforting. It meant that nothing truly dies. It just changes form. Aristotle, working in Athens around 350 BCE, did not invent the four-element theory, but he gave it its most lasting form. He added the qualities: hot, cold, wet, dry. Earth was cold and dry. Water was cold and wet. Air was hot and wet. Fire was hot and dry. These qualities could swap places. If you heated water, you got air, steam. If you cooled air, you got water, condensation. If you burned wood, you released the fire hidden inside. The system was tidy, logical, and seemed to explain everything from weather to digestion. For nearly 2,000 years, doctors diagnosed illness as an imbalance of the four humours: blood, phlegm, black bile, yellow bile, which corresponded to the four elements. That system is gone now, but the instinct behind it, that health comes from balance, is still very much alive. Different cultures built different elemental families. In China, the 5 phases, wood, fire, earth, metal, water, described not just substances, but processes. Wood fed fire. Fire created earth, ash. Earth contained metal. Metal carried water. Water nourished wood. This cycle was used in medicine, agriculture, architecture, and even military strategy. In India, the 5 great elements included earth, water, fire, air, and space, akasha. Space was not empty. It was the container, the silence that allows the other elements to move. So while the West had 4 elements and a separate ether for the heavens, the East included the idea of openness as an element itself. You can feel why these ideas lasted so long. They are intuitive. When you hold a rock, you feel earth. When you drink water, you feel wetness. When you breathe deeply, you feel air filling your chest. When you stand near a fire, you feel heat. These are not abstract concepts. They are direct experiences. The 4-element theory was a map drawn from the body outward. It said that the world outside is made of the same things your body knows from the inside. That is a deeply human way of thinking. It makes the universe feel familiar, not alien. One of the quiet strengths of the 4-element theory was its ability to absorb new observations without breaking. When alchemists discovered that metals could be dissolved in acids, they said the metal had turned into water. When they found that certain powders exploded, they said the fire inside had been released. The theory was flexible, almost stretchy. It could accommodate almost any new finding by adding more complexity, more qualities, more interactions, more hidden relationships. That flexibility kept it alive for centuries, even as it became less and less useful for precise prediction. Eventually, the 4 elements had to go. They could not explain why some metals were heavier than others, why certain gases would not burn, why water sometimes froze at different temperatures. But the departure was gentle, not violent. One theory faded as another grew, and the 4 elements did not disappear entirely. They survive in the language of poetry, in the 4 classical elements of astrology, in the way you might still say someone has a fiery temper or an earthy personality. The words have lost their scientific meaning, but they have kept their emotional truth. As you lie here, feeling the weight of your blanket, earth, the moisture on your tongue, water, the air moving in and out, air, and the warmth of your own body, fire, you're experiencing the 4 elements directly. Modern chemistry would describe these sensations in terms of atoms, molecules, and energy. But the old description is not wrong. It is just different. Both ways of seeing are useful. Both are beautiful. and both lead back to the same place: wonder that anything exists at all. Early Greek thinkers and the nature of matter. Before Aristotle, before the four elements became a system, there were individuals who looked at the world with fresh eyes. They did not inherit theories from teachers. They invented them from scratch. These were the pre-Socratic philosophers living in Greek colonies along the coast of what is now Turkey and Italy, between 600 and 400 BCE. They had no laboratories, no funding, no peer review. They had only curiosity and the willingness to be wrong. And they were wrong about almost everything, except for the most important thing, that the natural world could be understood by human minds. Thales of Miletus suggested that everything was made of water. You can see why. Water is essential for life. It takes three forms: solid, liquid, gaseous, while remaining the same substance. It flows, it shapes landscapes, it appears in rain, rivers, and seas. For a thinker trying to reduce complexity to simplicity, water was a good candidate. Thales was wrong, but his method was right. He looked at the world and asked for a single underlying principle. That question, what is everything really made of, is the same question that drives physics and chemistry today. Anaximenes, also from Miletus, disagreed. He thought air was the fundamental substance. Air, he observed, could be thickened into wind, then clouds, then water, then earth, then stone. Or it could be thinned into fire. All change for Anaximenes was just air becoming more or less dense. That idea contains a surprisingly modern insight. Density, how tightly packed the particles are, is indeed a key property of matter. Gases are low density, solids are high density, and you can change one into the other by adding or removing energy. Anaximenes did not know about atoms or energy, but he felt his way toward a truth that would take 2,000 years to fully articulate. Heraclitus, known as the weeping philosopher because of his melancholy view of constant change, proposed that fire was the fundamental element. He saw that everything flows, everything shifts, nothing stays the same. Fire is the most obvious symbol of that instability. A flame is never the same from one moment to the next. It consumes, transforms, and moves. Heraclitus famously said that you cannot step into the same river twice because new water flows around you and you yourself have changed. That is a chemical thought as much as a philosophical one. The water molecules are different. The riverbed has shifted. The person has aged by a breath. Nothing is static. Parmenides took the opposite view. He argued that change is an illusion. If something truly exists, it cannot come from nothing or become nothing. Therefore, reality must be a single, unchanging, solid sphere of being. Your senses deceive you when they show birth, death, growth, decay. Only reason can reveal the truth, that there is only one thing, eternal and motionless. Parmenides was almost certainly wrong about physics, but his argument forced later thinkers to take change seriously. They had to explain how something could change without disappearing. That challenge led to the atomic theory, small particles that rearrange while remaining indestructible. Empedocles offered the compromise that became the four-element theory. He agreed with Parmenides that nothing can come from nothing, but he agreed with Heraclitus that change is real. His solution was four eternal roots: earth, air, fire, water, and two forces, love and strife, that mix and separate them. Love draws things together. Strife pulls them apart. The universe is a cosmic dance of attraction and repulsion. That idea is strikingly close to modern chemistry, where atoms bond love and break apart strife based on electromagnetic forces. Empedocles just used more poetic names. These early thinkers had no data. They had no experiments. They had only logic, observation, and imagination. And yet they built the foundation for everything that came after. They established that the universe is lawful, not random, that human reason can penetrate appearances, that asking the right question is more important than having the right answer. Their mistakes were honest, creative, and productive. Each wrong theory contained a seed of rightness. Tonight, as you rest, you can appreciate that you are part of that same tradition. Every time you wonder why something feels hot or cold, why sugar dissolves in tea, why a nail rusts, you are doing what Thales, Anaximenes, Heraclitus, Parmenides, and Empedocles did. You are trying to see the simple inside the complex. You are trusting that the world makes sense. That trust has never been betrayed. Every generation finds more sense than the last. The idea of atoms in ancient times. The word atom comes from the Greek atomos, meaning uncuttable or indivisible. That is a strange idea to hold in your mind. A piece of something that cannot be made smaller, a final stop on the long journey of cutting. But the ancient Greeks did not discover atoms through experiments. They discovered them through logic alone, and that is remarkable. They sat in the sun, walked through markets, watched dust motes dance in a beam of light, and they said, "If you keep breaking a rock forever, you never reach an end. But the universe must have an end. Therefore, there is a smallest piece." That is not science as you know it. That is philosophy. And yet it pointed toward the truth. Leucippus is usually credited as the first atomist, but almost nothing of his writing survives. His student Democritus, the laughing philosopher, is the one who filled in the details. Democritus said that atoms are eternal, indestructible, and constantly moving through empty space. They come in different shapes and sizes. Smooth atoms for honey, jagged atoms for bitterness, round atoms for softness. They do not have qualities like color or temperature. Those emerge from how atoms interact with your senses. When you see red, you are not seeing a red atom. You are seeing a particular arrangement of atoms that your eyes interpret as red. That was a radical separation between reality and perception. Empty space, or the void, was essential to atomism. If there was no empty space, atoms could not move. They would be frozen in a solid block of being. But the world clearly moves. Water flows, smoke rises, your chest rises and falls with breath. Therefore, there must be gaps between atoms. Those gaps allow sliding, separating, recombining. Change is just atoms rearranging in the void. Nothing is created or destroyed. That idea is extraordinarily close to the modern law of conservation of mass. Democritus arrived at it without a single test tube. Other ancient cultures developed similar ideas. In India, the Vaisheshika school of philosophy, founded by Canada around the 2nd century BCE, taught that everything is made of anu, tiny indestructible particles that are too small to see. These anu combine into larger divyanuka and then into visible objects. Different qualities, taste, color, smell, touch, arise from different combinations. The Indian atomists also believed that atoms are in constant motion, that they have different types based on the elements they form, and that they cannot be created or destroyed. Sound familiar? It should. The same insights emerged on opposite sides of the planet. without any contact between them. That suggests something profound. The structure of the universe is not arbitrary. A human mind, looking carefully at the world, can glimpse the truth. In China, atomism never took root. Chinese philosophy favored continuous systems, qi flowing, yin and yang transforming, rather than discrete particles. That is not a failure. Different cultures ask different questions, and they get different answers. The Chinese developed sophisticated understanding of change, cycles, and relationships. The Greeks developed particle theory. Modern chemistry needed both. The idea of permanent atoms and the idea of continuous energy and fields. You can rest with the thought that no single culture gets everything right. Wisdom is a patchwork. Democritus believed atoms were eternal. He did not know that atoms themselves are made of smaller parts, protons, neutrons, electrons. But that discovery does not destroy his insight. It deepens it. The atomos of ancient Greece is not the same as the atom of modern physics, but the core idea that matter has a smallest unit, that these units combine in predictable ways, that change is rearrangement, has survived 2,500 years. That is a stunning track record for a guess made without instruments. As you feel the weight of your blanket, the texture of your pillow, the slight coolness of the air on your skin, you are experiencing the results of atomic arrangements. Billions upon billions of atoms, moving in the void, holding together just long enough for you to rest. Democritus could not see them, but he believed in them, and he was right to believe. That is a quiet kind of triumph. How philosophy became early chemistry. For hundreds of years after Democritus, the atomists remained philosophers, not chemists. They thought about matter, but did not experiment on it. That changed slowly, as curiosity turned into action. You cannot learn how metals behave just by sitting and thinking. You have to heat them, hammer them, dissolve them, watch what happens. The shift from philosophy to early chemistry, often called alchemy, was the shift from asking, what is matter made of, to asking, what can matter do? That second question opened a door, and behind that door were furnaces, bellows, crucibles, and 1,000 small discoveries that would eventually become the science you know today. The first chemists were not scholars in libraries. They were craftspeople, metal workers, dyers, perfume makers, glass blowers, bakers. They learned by doing. A potter notices that certain clays fire to a harder finish. A metal worker observes that adding tin to copper produces bronze, which is stronger than either metal alone. A dyer discovers that a particular plant juice turns blue when mixed with ash water. These were not theories. They were recipes, passed from master to apprentice. But every recipe contains chemical knowledge. The recipe for bread tells you that yeast, warmth, and time produce gas that makes dough rise. The recipe for soap tells you that fat and ash create a slippery solid that cleans. No one called it chemistry, but it was chemistry. The word alchemy comes from the Arabic alchemia. The Arabic scholars preserved and expanded Greek and Egyptian knowledge after the fall of the Roman Empire. They built laboratories, developed new techniques like distillation, and wrote detailed manuals. Jabir ibn Hayyan, known in Europe as Geber, lived in the 8th century and is often called the father of chemistry. He prepared sulfuric acid, nitric acid, and hydrochloric acid. He discovered that aqua regia, a mixture of hydrochloric and nitric acids, could dissolve gold, which no single acid could do. He studied crystallization, filtration, and sublimation. These were not mystical speculations. They were hands-on reproducible procedures. Alchemy was becoming a real craft. In Europe, alchemy took root in monasteries and royal courts. Monks copied Arabic texts, translated them into Latin, and tried the experiments themselves. They were looking for two things: the philosopher's stone, which could turn lead into gold, and the elixir of life, which could grant immortality. Neither exists, but the search was productive. Alchemists invented new alloys, new pigments, new medicines. They learned to distill alcohol, to make strong acids, to extract metals from ores. They developed the equipment you would recognize in a modern lab: beakers, flasks, retorts, mortars, balances. The dead ends were not dead ends. They were detours that led somewhere else. One of the most important alchemical ideas was that metals grow inside the earth like seeds. Mercury and sulfur were considered the parents of metals. Different proportions of mercury and sulfur produced different metals. More sulfur for lead, less sulfur for gold. That is wrong. But it kept alchemists experimenting. They tried to purify mercury, to capture sulfur in different forms, to speed up the Earth's natural process in their furnaces. Every failure taught them something. They learned to identify metals by their reactions. They learned that heating a substance in a closed container gave different results than heating it in open air. They learned that air itself could be a participant in chemical change, a huge insight that would flower later. You can see the ghost of alchemy in the language of chemistry today. You still talk about dissolving, precipitating, calcining, heating to a powder. You still use the symbols that alchemists drew for metals: female symbol for copper, male symbol for iron, planet symbol for mercury. The equipment looks different, but the gestures are the same. Pour, heat, weigh, observe. Alchemy was not a delusion. It was a 1,000-year conversation between human hands and stubborn matter. And that conversation produced something precious: the habit of experiment. Once people started heating things just to see what happened, the modern world was inevitable. A gentle thought for the edge of sleep. Every time you cook an egg or brew coffee, you are doing what alchemists did. You are changing matter with heat, time, and attention. You are continuing their work. Alchemy, the mysterious origins of chemistry. The word alchemy often makes people think of old men in dusty rooms, whispering spells over glowing cauldrons. That image is not entirely wrong, but it misses the patience, the curiosity, and the genuine wonder that drove alchemists. These were people who believed that the universe had secrets, and that those secrets could be found through careful work. They prayed, yes. They drew symbols, yes. But they also weighed, measured, heated, and recorded. Alchemy was the bridge between magic and science, a bridge that took nearly 1,500 years to cross. The origins of alchemy are usually traced to Hellenistic Egypt, specifically the city of Alexandria, around the first few centuries of the Common Era. Greek philosophy met Egyptian craftsmanship. The result was a new kind of activity: transforming metals, making dyes, creating artificial gemstones, and writing down the procedures. The most famous early alchemical text is the Physica kai Mystica, Natural and Secret Things, attributed to a woman named Maria the Jewess. Maria invented several pieces of laboratory equipment, including a water bath, still called a bain-marie, and a distillation apparatus. She wrote, "Do not touch the philosopher's stone with your hands, but only with your mind." That is a sentence that belongs to both science and poetry. A quiet fact, resting in the background like a familiar shadow. The bain-marie you use to melt chocolate or warm sauces is named after Maria the Jewess. Maria's bath became bain-marie in French. A Roman chemist named Zosimos of Panopolis, writing around 300 CE, preserved many of her recipes. He described the art of making alloys, purifying metals, and creating tinctures that could change color. Zosimos also wrote about visions and dreams, mixing practical instructions with mystical allegory. That blending seems strange now, but it made sense then. If the universe was one thing, spiritual and material together, then changing matter was also a spiritual act. Alchemy spread from Egypt to the Islamic world after the 7th century. Arabic scholars translated the Greek texts, added their own experiments, and created the most advanced chemical knowledge of the Middle Ages. The word alchemy itself comes from alchemia, where al means the and chemia may derive from the ancient Egyptian chem, black earth. So alchemy means literally the black earth, the fertile soil of the Nile. That name is humble. It connects the most mystical pursuit to the most ordinary ground. In Islamic alchemy, a powerful figure was Jabir ibn Hayyan Geber. He wrote hundreds of books, though many may have been written by his followers. Jabir emphasized experiment over theory. He said, "The first essential in chemistry is that you should perform practical work and conduct experiments." That is a modern sentence. He also classified substances into spirits, volatile, metals, malleable, and stones, non-malleable. He developed the technique of crystallization, producing pure substances from solution. He discovered several new acids. He understood that distillation could separate alcohol from wine. His work was so thorough that European alchemists, centuries later, still relied on his methods. Alchemy reached Europe through Spain and Sicily, where Christian scholars translated Arabic texts into Latin. By the 12th century, alchemy was a recognized pursuit, practiced by monks, physicians, and some ambitious kings. The most famous European alchemist is probably Albertus Magnus, a bishop and teacher of Thomas Aquinas, who wrote extensively on metals, minerals, and chemical processes. He observed that arsenic trioxide could be made by roasting arsenic ores, and that it was a poison. He also described the preparation of potash, sal ammoniac, and other useful compounds. Albertus did not find the philosopher's stone, but he did find a deeper understanding of how matter behaves. The mystery of alchemy is not that it failed. It is that it succeeded enough to survive for centuries. Each generation added a little more precision, a little more knowledge, and eventually the mystical shell cracked open and modern chemistry stepped out. But the shell was not wasted. It protected the growing science during a long, dark winter of war, plague, and superstition. Alchemy was the careful mother of chemistry. Strange, sometimes embarrassing, but absolutely necessary. The dream of turning lead into gold. For more than 1,000 years, the most powerful people in the world funded the search for a single thing, the philosopher's stone. Not a stone, really, but a powder or a liquid or a solid that could transform any base metal into gold. Kings emptied their treasuries. Scholars dedicated their lives. Fraudsters and dreamers alike promised they were close, so close, just a little more gold to finish the experiment. The dream of transmutation, changing one metal into another, is as old as metallurgy itself. Why? Because lead and gold look so different. Lead is dull, soft, poisonous. Gold is bright, durable, beautiful. If one could become the other, then poverty could become wealth, sickness could become health, death could become life. The philosopher's stone was never just about gold. It was about perfection. The idea that metals can be transformed comes from observation. Alchemists noticed that heating certain rocks produced metals. They thought that metals grew inside the earth like plants, slowly ripening from imperfect to perfect. Lead was the most imperfect. Gold was the most perfect. The alchemist's job was to speed up this natural ripening using heat, chemicals, and perhaps a little magic. The philosopher's stone was the catalyst. A tiny amount of stone could transform a huge amount of lead, just as a tiny piece of yeast transforms a huge batch of dough. That analogy made sense, and it kept people experimenting for centuries. Many alchemists genuinely believed they could succeed. They were not all frauds. They were wrong, but wrong in a way that produced real discoveries. To test whether they had created gold, they had to develop better ways of testing metals, specific gravity, acid tests, cupellation. Heating with led to separate precious metals. They learned to distinguish between real gold and lookalikes like pyrite, fool's gold. They learned to refine gold to higher purity than had ever been possible. The quest for the stone pushed the limits of chemical knowledge. Even the failures were useful. The most famous story of successful transmutation involves a German alchemist named Henrik Brand, who in 1669 was searching for the philosopher's stone using a very strange raw material, urine. He boiled gallons of urine, hoping to extract some golden essence. He did not find gold. Instead, he found a waxy white solid that glowed in the dark. That solid was phosphorus, the first element to be discovered that was not known to the ancients. Brand had not turned lead into gold, but he had discovered a new substance, one that would eventually be used in matches, fertilizers, and even DNA. The stone was a ghost. The journey was real. Another English alchemist, John Dee, advised Queen Elizabeth I on matters of science and magic. He believed that transmutation was possible and spent years searching. He did not succeed, but his library was one of the largest in England, and his notes on mathematics, astronomy, and navigation helped shape the age of exploration. Dee's pursuit of the stone was not a waste. It was a container for his broader curiosity. The stone was the excuse. The real work was learning how the world works. Even Isaac Newton, perhaps the greatest scientist who ever lived, wrote hundreds of thousands of words on alchemy. He copied recipes, performed experiments, and searched for hidden meanings in ancient texts. Newton believed that the philosopher's stone was real. He also believed that the Bible contained a secret code. He was wrong about both, but his alchemical work sharpened his understanding of forces, reactions, and transformations. Some historians argue that his work on gravity and motion was influenced by alchemical ideas about attraction and repulsion. The dream of gold led, indirectly, to the laws of physics. You can smile at the alchemists now. They were chasing a fantasy, but fantasies can be useful. They motivate long, patient work. They keep people curious through years of failure. And sometimes, the thing you find is better than the thing you were looking for. Brand found phosphorus. The alchemists found chemistry. And you, in your quiet room, can find something too. Not gold, but the simple pleasure of knowing that human beings have always been willing to try impossible things. Alchemists and their secret symbols. When you look at an old alchemical manuscript, the first thing you notice is the symbols. Not the neat letters of a printed book, but strange shapes, a circle with a dot, a crescent moon, a cross with arms, a serpent eating its own tail. These symbols were not for decoration. They were a secret language designed to protect knowledge from the uninitiated. Alchemists lived in dangerous times. Accusations of heresy or witchcraft could lead to prison or death. Writing clearly about turning lead into gold could also attract the attention of kings who wanted the gold and would torture you to get it. So the alchemists encoded their recipes in symbols, astrological signs, and mythological references. The most common symbols represented the 7 metals known to the ancients: gold, the sun, silver, the moon, copper, Venus, iron, Mars, tin, Jupiter, Mercury, and lead, Saturn. Each metal was associated with a planet and a god. Gold, the sun, was king. Silver, the moon, was queen. Lead, Saturn, was the slowest and heaviest, associated with time and melancholy. These associations were not arbitrary. They connected the physical behavior of metals to broader cosmic patterns. Gold does not tarnish, so it is perfect, like the sun. Mercury is liquid and mobile, so it is messenger, like the god Mercury. The symbols helped alchemists remember and communicate complex relationships. Other symbols represented chemical processes: distillation, a dripping spout; calcination, a fire tool; fermentation, a vessel with bubbles. Still others represented hidden concepts: the philosopher's stone, a circle containing a triangle; the elixir of life, a caduceus; the green lion, a symbol of raw, unripe gold. Reading an alchemical text was like solving a puzzle. You had to know the code. Many alchemists enjoyed the puzzle. They believed that esoteric knowledge that requires initiation, is more valuable than common knowledge. That belief is still alive in some subcultures today. The secrecy had practical benefits. It prevented untrained people from performing dangerous experiments. Some alchemical processes produced toxic gases, explosive mixtures, or strong acids. If you did not know what the symbols meant, you would not try the experiment. The secrecy also built community. Alchemists who shared the same symbols could recognize each other as fellow seekers. They corresponded in code, visited each other's laboratories, and formed an invisible college that stretched across Europe and the Islamic world. That invisible college eventually became the Royal Society of London, the first modern scientific institution. One of the most famous alchemical symbols is the Ouroboros, a serpent or dragon eating its own tail, forming a circle. It represents unity, eternity, the cycle of birth and death, and the idea that the philosopher's stone can be created from within the work itself. The Ouroboros also symbolizes the alchemical maxim, as above, so below. The same patterns repeat at every level: the cosmos, the laboratory, the human body, the soul. That idea is not unscientific. Modern physics has discovered fractals, scaling laws, and the principle that the same physical laws apply everywhere. The alchemists were not wrong about the unity of nature. They were just describing it in a different language. You can see alchemical symbols today without knowing it. The Star of David, the cross, the crescent moon, the Ankh, all have roots in ancient alchemical or astrological traditions. The symbol for Mercury, Gidn, is still used in astronomy and astrology. The symbol for Venus is used for female or for copper in some contexts. The symbol for Mars is used for male or for iron. These tiny marks are fossils of a lost worldview. They survive because they are useful. A symbol that represents an idea can last longer than the idea itself. A final thought for this stretch of night. The alchemists hid their knowledge because they were afraid. Fear of persecution, fear of theft, fear of misuse. That fear is sad, but it is also human. Modern chemistry is open, published, shared. Anyone with an internet connection can learn how to make aspirin or test water quality. That openness is a gift. It came from alchemists who dared to write down their secrets, even in code, and from later scientists who broke the code and translated it into plain language. The search for the Philosopher's Stone. You have heard about the Philosopher's Stone already, the legendary substance that could turn lead into gold and grant immortality. But what did alchemists actually think the stone was? The answer changes depending on which century, which country, which alchemist you ask. Some described it as a red powder, heavy as gold. Others said it was a glassy solid, soft as wax. Still others insisted it was a liquid, the elixir of life, that could be drunk from a silver cup. The stone was not a stone at all. It was a projection of desire, the thing you would most want to hold if matter could be perfected. The search for the stone drove alchemists to develop new laboratory techniques. They learned to heat substances for days or weeks at specific temperatures. They learned to seal vessels so that nothing could escape. They learned to add seeds of gold to a solution and watch as more gold crystallized. A process that looked exactly like transmutation, but was actually just purification. Each dead end taught them something about the stubbornness of matter. Gold did not want to become lead. Lead did not want to become gold. The elements had personalities in a way. They resisted change unless you gave them enormous energy. One of the most detailed recipes for the Philosopher's Stone comes from the 14th century, attributed to a mysterious figure named Nicolas Flamel. Flamel was a real bookseller in Paris who left money to charities and hospitals. But the legend grew that he had discovered the stone and lived for centuries with his wife, Perenelle. The recipe involved the subtle matter that exists between mercury and sulfur, processed through 7 stages of heating, each stage marked by a color change: black, white, gray, yellow, red, purple, and finally the perfect red stone. Flamel's gravestone still exists, though he is not buried under it. The legend says he faked his death and moved to India. Why did so many intelligent people believe in the stone? Because the universe had already given them examples of transformation. A seed becomes a tree. That is a kind of transmutation. Caterpillars become butterflies. Winter becomes spring. The idea that some substances are base and others noble is not absurd. Gold is noble because it does not rust or tarnish. Lead is base because it easily corrodes. If nature can transform a crawling worm into a flying creature, why could it not transform lead into gold? The alchemists were not irrational. They were extending a valid pattern too far. The real tragedy of the Philosopher's Stone is not that it does not exist. It is that the search for it prevented alchemists from seeing what they had already achieved. They had learned to produce pure sulfuric acid, pure nitric acid, pure alcohol. They had learned to isolate antimony, bismuth, zinc, and phosphorus. They had invented the laboratory itself, the place where you go to ask matter questions and wait for answers. Those achievements are more valuable than any stone. But the alchemists could not see that because they were looking at the wrong horizon. Even Isaac Newton, 2,000 years after Democritus, wrote more than 1,000,000 words on alchemy. He believed that the Philosopher's Stone was hidden in the Bible, encoded in its measurements and genealogies. He performed experiments that destroyed his health, breathing toxic fumes, handling mercury with bare hands. Newton was not a fool. He was a genius who worked in a time before the periodic table, before atoms were proven, before chemistry had its own language. He used the tools available, and those tools included alchemical symbolism, transmutation theory, and the dream of perfect matter. We remember Newton for his laws of motion and gravity, but he would also have wanted to be remembered for his work on the stone. The dream of turning lead into gold is not dead. It just moved to a different scale. Modern particle accelerators can transform one element into another by smashing atoms together. You can turn lead into gold by bombarding it with protons. The process costs millions of dollars and produces less gold than you could buy with a single paycheck. But it is possible. The alchemists were not wrong about the possibility. They were just wrong about the method. They needed particle physics, not plant ashes and angelic invocations. Alchemy, as both science and spiritual practice. For a modern person, the line between science and spirituality is clear. You go to a laboratory to measure things. You go to a church or meditation cushion to find meaning. Alchemists did not see that line. They believed that the same principles govern the cosmos, the laboratory, and the soul. When you purified a metal in a crucible, you were also purifying your own character. When you combined mercury and sulfur to make a new compound, you were also uniting opposing forces within yourself. Alchemy was a spiritual discipline with glassware. And that dual nature, physical and metaphysical, is what makes it so strange and so beautiful. The spiritual side of alchemy is often called inner alchemy, or alchemical transformation of the soul. The stages of the great work, nigredo, blackening, albedo, whitening, citrinitas, yellowing, and rubedo, reddening, described both chemical changes and psychological states. Nigredo was the dark night of the soul, the moment when old beliefs dissolve. Albedo was purification, washing away contamination. Citrinitas was the dawn of wisdom. Rubedo was union with the divine, the red stone, the completed self. An alchemist who achieved the Philosopher's Stone was also, ideally, a wise and compassionate person. The two achievements were the same. The most famous expression of spiritual alchemy is the Emerald Tablet, attributed to Hermes Trismegistus, a legendary figure who blended the Greek god Hermes and the Egyptian god Thoth. The text is short, only 13 lines, but it has been commented on for centuries. Its most famous line, "As above, so below, as within, so without." That phrase means that the same patterns repeat at every level of reality. The way a metal purifies is the way a soul purifies. The way the planets move is the way the body's humors move. The way you treat a chemical is the way you should treat another person. Everything is connected. Everything is one. Carl Jung, the 20th century psychologist, rediscovered alchemy as a map of the human psyche. He noticed that alchemical symbols appeared in his patients' dreams: the sun and moon, the king and queen, the dragon and the stone. Jung argued that alchemy was not a failed science, but a successful symbolic system. It described the process of individuation, the journey toward wholeness. The Philosopher's Stone was the integrated self. The search for gold was the search for meaning. Jung's interpretation revived interest in alchemy among artists, writers, and therapists. It also irritated many historians of science who thought he was reading too much into old furnaces. But you can hold both views at once. Alchemy was a real chemical practice that discovered real substances. It was also a container for spiritual longing, a way of talking about transformation, when psychology did not exist as a discipline. The same person could heat a crucible and pray. The same recipe could be a set of instructions for making a medicine and a metaphor for healing the spirit. That is not confusion. That is richness. Life is not divided into neat categories. The alchemists understood that. They let their science be wet with wonder. As you rest here, you might notice that you also mix the practical and the spiritual. You cook a meal, that is chemistry. You feel love for the person you are cooking for, that is something else. But the love and the cooking happen together. You cannot separate them. The alchemists would say that is the point. The great work is happening in your kitchen, in your bedroom, in the quiet space between your breaths. You are the material. You're also the worker. Early laboratories and alchemical tools. Before alchemy, there was no such thing as a laboratory. There were workshops, potters' sheds, metal smithies, dye houses, apothecary shops. Each craft had its own tools and its own secrets. Alchemy brought those tools together into a single space dedicated to one purpose, asking questions of matter. The early laboratory was a hot, smoky, cluttered room. It smelled of sulfur, vinegar, and burned wood. It contained furnaces of different sizes, glass vessels of strange shapes, mortars and pestles worn smooth by years of grinding. And it contained the alchemist, often alone, sometimes with an apprentice, watching, waiting, recording. The most important tool was the furnace. Not one furnace, but several. The athanol was the slow furnace, kept burning for weeks or months at a low, steady heat. It looked like a tall cupboard with a fire at the base and vessels stacked above. The reverberatory furnace had a curved roof that reflected heat back onto the material. The blast furnace used bellows to force air into the fire, reaching higher temperatures. An alchemist could spend years learning how to control temperature by adjusting fuel, air, and the shape of the firebox. Temperature control is still the heart of chemistry. A reaction that works at 80 degrees may fail at 100. The alchemists knew that. Distillation apparatus was the second essential tool. The alembic, from the Arabic alambic, meaning the still, consisted of a gourd-shaped vessel, a head that collected rising vapors, a tube, the neck, and a receiving flask. You heated the material in the gourd. Vapors rose into the head, traveled down the tube, and condensed back into liquid in the flask. That simple device allowed alchemists to separate alcohol from wine, essential oils from plants, pure water from salt water. Distillation is still used in every chemistry lab, every perfume factory, every whiskey distillery. The shape has changed. The principle has not. Crucibles were the third essential tool. These were small, thick cups made of clay or ceramic, designed to withstand extreme heat. You put a metal or mineral inside the crucible, placed it in the furnace, and watched. The crucible revealed which substances melted, which burned, which turned into glass. It allowed alchemists to alloy metals, to reduce ores, to test the purity of gold. A good crucible could be used hundreds of times before cracking. A bad crucible would shatter in the heat, spilling hours of work. Alchemists treated their crucibles with respect. They were not easily replaced. Other tools included the mortar and pestle for grinding solids, the balance for weighing, the phial for storing liquids, the spatula for stirring, the filter for separating. Alchemists also used less recognizable equipment, the pelican, a vessel shaped like a bird, for continuous distillation, the cucurbit, a gourd-shaped flask, the retort, a curved tube for distilling corrosive substances. Each tool had a name, a purpose, and a history. Many of those names are still used in modern laboratories. The retort has been replaced by the round-bottom flask, but the idea is the same. Heat something, capture the vapor, learn what it is made of. Working in an early laboratory was dangerous. Fires could spread, vessels could explode, toxic fumes could accumulate. Alchemists died young. They breathed arsenic, mercury, lead. They drank poor quality alcohol to test their distillations. They burned their hands, their faces, their lungs. That is a sad truth, but it is also a heroic truth. They knew the risks, and they worked anyway. They were not seeking gold for themselves. Most of them died poor. They were seeking knowledge, and knowledge, they believed, was worth the price. How alchemists discovered real chemical processes. The alchemists were wrong about the philosopher's stone. They were wrong about transmutation. They were wrong about many things, but they were not wrong about everything. Between the mystical texts and the coded symbols, they discovered real chemical processes that are still used today. They learned to distill, to calcine, to sublime, to dissolve, to precipitate, to crystallize, to filter, to alloy, to amalgamate. Each of those words describes a physical operation that you could perform in a kitchen or a garage. And each one was first refined by alchemists working in smoke-filled rooms, trying to turn lead into gold. Take distillation. The alchemists did not invent it. People had been boiling water and collecting the steam since prehistory. But the alchemists transformed distillation from a crude technique into a precise art. They learned that different liquids boil at different temperatures. They learned to collect the fractions that came over at different stages. First, the light spirits, then the heavier oils, then the residues. They used this knowledge to produce high-proof alcohol, which became the basis for medicines, perfumes, and eventually antiseptics. Modern fractional distillation, used to separate crude oil into gasoline, kerosene, and diesel, is a direct descendant of alchemical practice. Take calcination. This is the process of heating a material in open air until it turns to powder or ash. Alchemists calcine metals, stones, shells, and bones. They observed that some metals gained weight when calcined. Lead and tin, for example, formed heavier powders. That observation seemed impossible. How could a solid lose material and gain weight? The answer is oxygen. The metal was combining with oxygen from the air. The alchemists did not know about oxygen, but they recorded the weight change carefully. Centuries later, those records helped Antoine Lavoisier discover the role of air in combustion. The alchemists had collected the data. They just did not know what it meant. Take crystallization. Alchemists learned to dissolve substances in hot water, then let the water cool slowly. Crystals would form, regular, geometric, beautiful. They learned that different cooling rates produced different crystal sizes. They learned that impurities could be removed by repeated crystallization. This process is still used to purify everything from table salt to pharmaceutical drugs. The alchemists also noticed that crystals often had specific shapes, cubes, prisms, needles, and they linked those shapes to the essence of the substance. Modern chemistry calls that crystal habit. The principle is the same. The shape tells you something about the internal arrangement. Take precipitation. alchemists discovered that mixing two clear solutions could produce a solid that fell to the bottom of the vessel. That solid was the precipitate. They used precipitation to test for metals, to purify compounds, to create pigments. The beautiful color of chrome yellow came from precipitating lead with chromate. The deep blue of Prussian blue came from precipitating iron with ferrocyanide. Many of those pigments are still used in artist paints. When you see a painting from the Renaissance or the Baroque period, you are looking at alchemical chemistry preserved on canvas. The alchemists also discovered new substances. They isolated antimony, which they used as a medicine with mixed results. They isolated bismuth, which they thought was a form of lead. They isolated zinc, which had been known in India and China, but was new to Europe. They produced sulfuric acid, oil of vitriol, by burning sulfur with saltpeter. They produced nitric acid, aqua fortis, by heating saltpeter with clay. They produced hydrochloric acid, spirit of salt, by heating salt with sulfuric acid. These three strong acids became the workhorses of chemistry. You cannot do modern chemistry without them. The alchemists made them first. Distillation, the first controlled chemical technique. Of all the techniques the alchemists refined, distillation was the most important. It allowed them to separate mixtures, purify liquids, and discover new substances. Distillation is simple in principle. Heat a liquid until it boils. Capture the vapor. Cool the vapor until it condenses back into liquid. But the simplicity hides a deep power. Distillation can separate alcohol from water, essential oils from plant matter, and even different components of crude oil. Without distillation, you would have no whiskey, no perfume, no gasoline, no pure water, no many medicines. The alchemists gave you a tool that still runs the world. The earliest distillation equipment was crude. A copper pot with a cloth tied over the top. The cloth would catch the steam and drip into a bowl. That works, but it is inefficient. By the 9th century, Arabic alchemists had developed the alembic, with its distinctive dome-shaped head. By the 13th century, European alchemists had added cooling tubes, water baths, and multiple receivers. They learned to distill the same material multiple times, rectification, to increase purity. They learned to distill in a vacuum using sealed vessels, to lower the boiling point of sensitive substances. Each improvement was a small revolution. The most famous distillation story in alchemy is the discovery of alcohol. Alchemists knew that wine could be distilled to produce a spirit that was much stronger than the original. They called it aqua vitae, water of life. They believed this spirit was the essential principle of fermentation, the soul of the grape. They used it to extract medicinal compounds, to preserve herbs, to make perfumes. By the 16th century, aqua vitae had become brandy, whiskey, and vodka. The alchemists did not set out to create alcoholic beverages. They set out to understand the hidden nature of wine. But understanding and pleasure often travel together. Another important distillation product was essential oils. Alchemists discovered that many plants, roses, lavender, mint, cinnamon, contained volatile oils that could be distilled with steam. These oils carried the scent and some of the medicinal properties of the plant. They were the first concentrates. An ounce of rose oil contained the essence of hundreds of pounds of rose petals. The alchemists used these oils in perfumes, in medicines, and in religious rituals. Today, essential oils are used in aromatherapy, cosmetics, and flavorings. The process has not changed in 1,000 years. you can still distill lavender oil the way the alchemists did. Distillation also revealed that air was not a single element. When alchemists heated certain substances, they produced airs that behaved differently from ordinary air. Some airs supported combustion powerfully. Some airs extinguished flames. Some airs made animals die quickly. These observations challenged the four-element theory. If air was a single element, why were there different kinds of air? The question festered for centuries, until chemists like Joseph Priestley and Antoine Lavoisier answered it. But the question itself came from the alchemists, holding their alembics, watching bubbles rise. As you lie here, breathing in and out, you can think about distillation as a metaphor. Your breath is a kind of distillation. You take in the mixture of gases around you, and your body separates them, keeping oxygen, releasing carbon dioxide. Your kidneys distill your blood, removing waste into urine. Your tears distill grief into release. The alchemists believed that distillation was a universal process, not just a laboratory technique. They were right about that. The universe distills stars from gas clouds. It distills life from chemicals. It distills this quiet moment from the noise of the day. The birth of experimental thinking. For most of human history, people learned about the world by trusting authority. If Aristotle said that heavy objects fall faster than light ones, you believed him. If the Bible said the earth was fixed at the center of the universe, you did not question it. But somewhere between the late medieval period and the 17th century, a new way of thinking emerged. It was slow, hesitant, and often dangerous, but it changed everything. This new way was experimental thinking. The belief that you should not trust what you are told. You should test it. You should build a furnace, mix the substances, observe the result, and write down what you see. The authority is not the book. The authority is the experiment. The shift from alchemy to chemistry was not a single event. It was a gradual change in posture. Alchemists had always performed experiments, but they often interpreted their results through mystical lenses. When a reaction produced an unexpected color, they might see it as a sign from God or a message from the spirit world. The new experimental thinkers kept the experiments, but dropped the lens. They looked at the color and asked, "What is this color made of? Why does it appear? Can I reproduce it?" The questions moved from what does it mean to how does it work. That tiny shift from interpretation to measurement is the birth of modern science. One of the first people to clearly articulate experimental thinking was Francis Bacon, an English philosopher born in 1561. Bacon did not perform many experiments himself. He was more like a choreographer than a dancer. He argued that knowledge should be built from observations, not from logical deductions alone. He proposed that scientists should collect data, sort it into tables, look for patterns, and then test those patterns with new experiments. This method, inductive reasoning, is the opposite of the old method. The old method started with a general truth and applied it. The new method started with specific facts and built up to general truths. Bacon's ideas were not immediately popular, but they spread. A quiet fact to rest with. Francis Bacon died from pneumonia after experimenting with freezing a chicken. He was stuffing snow into a chicken to see if cold would preserve meat. The experiment worked, but he caught a chill and died a few days later. He literally gave his life to experimental thinking. That commitment, that willingness to be cold and uncomfortable for the sake of knowledge, is what separates the new science from the old. In practice, experimental thinking meant keeping careful records. Alchemists had kept records, but they were often vague or symbolic. The new experimenters wrote down exact weights, temperatures, times, and observations. They repeated experiments to check for consistency. They tried to control variables, changing only one thing at a time while keeping everything else the same. They published their methods so that others could replicate the work. Replication became the gold standard. If an experiment could not be reproduced by another person in another laboratory, it was not considered reliable. That standard is still used today. The shift to experimental thinking was not welcomed by everyone. Many traditional scholars mocked the new approach. They said that messing about with furnaces and acids was the work of craftsmen, not gentlemen. They said that knowledge should come from reading, not from getting your hands dirty. But the results spoke for themselves. Experimental thinkers began discovering things that the ancient texts did not contain. They found new metals, new gases, new compounds. They could predict how materials would behave because they had seen it happen. The old scholars could not do that. Their knowledge was static. The new knowledge was alive. The scientific revolution begins. The 17th century was a turning point. You can feel it in the dates. Galileo's telescope, Harvey's circulation of blood, Boyle's air pump, Newton's prism. Something was in the air, something that made people look at the world with fresh eyes. The scientific revolution did not start in one country or with one person. It started everywhere at once, like a storm forming over a wide sea. And chemistry, which had been the slowest of the sciences to mature, finally began to catch up. One of the most important figures for chemistry was Robert Boyle. He was born in Ireland in 1627, the son of the Earl of Cork. He had money, education, and curiosity. He could have spent his life hunting or reading philosophy. Instead, he built a laboratory and began experimenting. Boyle was not a professional scientist. That profession did not exist yet. He was a natural philosopher, a gentleman who studied nature for its own sake. But his approach was rigorous. He measured everything. He wrote down everything. He published his results in clear English, not Latin, so that anyone who could read could learn. Boyle's most famous work is The Skeptical Chemist, published in 1661. The title is a play on words. Chemist was the old spelling. In this book, Boyle attacked the four-element theory and the three-principle theory, mercury, sulfur, salt, that had replaced it. He argued that elements are not a small set of abstract qualities. An element, he said, is a substance that cannot be broken down into simpler substances by any known chemical method. That definition is still used today. Boyle did not know how many elements there were, but he gave chemists a way to find out. Test every substance. If you cannot break it down, it might be an element. If you can break it down, it is not. Boyle also studied the behavior of gases. He and his assistant, Robert Hooke, built an air pump that could remove most of the air from a sealed vessel. They observed that a flame went out, that a bell could not be heard, that a mouse died. They also observed that the volume of a gas decreased when the pressure increased. That relationship, pressure times volume equals a constant, is called Boyle's law. It is one of the first mathematical descriptions of a chemical property. It showed that chemistry could be quantitative, not just qualitative. You could measure gases. You could predict their behavior. Another key figure of the scientific revolution was John Mayall, an English physician who studied the role of air in combustion and respiration. He showed that only a part of the air, what he called Spiritus igneo aereus, fiery air spirit, was necessary for burning and for life. He placed a mouse and a candle in a sealed container and watched as both went out at the same time. That observation suggested that what a flame uses, an animal also uses. Mayow had discovered oxygen without naming it, but his work was largely forgotten for a century. The scientific revolution was not a straight line. It was full of dead ends, forgotten discoveries, and giant leaps that landed in the wrong place. The scientific revolution also changed how knowledge was shared. In 1660, the Royal Society of London was founded. It was a group of natural philosophers who met to discuss experiments, demonstrate new findings, and publish a journal. The Philosophical Transaction of the Royal Society is the oldest scientific journal in continuous publication. It established the norm of peer review, that a paper should be read and critiqued by other experts before publication. That norm is still the backbone of modern science. No one works alone anymore. Every discovery is checked by others. Why observation started to matter more than belief. For most of human history, belief was more powerful than observation. If your religion taught that the world was created in 6 days, you believed it, even if the rocks suggested otherwise. If your philosopher taught that a vacuum was impossible, you believed it, even if the barometer said otherwise. But the scientific revolution slowly inverted that relationship. Observation became the judge. Belief had to stand in the dock and answer. This inversion was painful. People were burned at the stake for observing the wrong things. Galileo was forced to recant his observation that the Earth moved around the sun, but the inversion held. Once you start trusting your eyes and your instruments more than your books, you cannot go back. In chemistry, the shift from belief to observation was particularly hard. Alchemical texts were filled with claims that could not be verified. A recipe might call for the blood of a red lion or the milk of a black hen. No one knew what these meant. The new experimenters demanded clarity. If you claim that heating mercury with sulfur produces a red powder, you must describe exactly how much mercury, how much sulfur, what temperature, for how long. And you must produce the red powder so that anyone can see it. That is observation. That is evidence. One of the clearest examples of observation overturning belief is the discovery of the vacuum. Aristotle had said that nature abhors a vacuum, that empty space was impossible. For 2,000 years, almost everyone believed him. But in the 17th century, Evangelista Torricelli, a student of Galileo, filled a glass tube with mercury, inverted it in a dish, and watched. The mercury fell, leaving an empty space at the top. That space was a vacuum. Nature did not abhor it. The mercury simply could not stay up because the weight of the air outside was not strong enough. Torricelli's observation, the barometer, proved Aristotle wrong. Belief fell. Observation rose. In chemistry, the same thing happened with the 4 elements. Alchemists had believed for centuries that earth, air, fire, and water were the basic building blocks. But when chemists started weighing substances before and after reactions, they found that the 4-element theory could not account for the numbers. A piece of metal heated in air gained weight. Where did the extra weight come from? It could not come from earth or water or fire. It had to come from the air. That observation suggested that air was not a single element, but a mixture, and that one component of air was absorbed by the metal. Belief said air was simple. Observation said it was complex. Observation 1. the shift also changed how experiments were reported. Early alchemical texts were written in a way that required interpretation. You had to be initiated to understand the symbols. The new experimenters wrote in plain language. Robert Boyle described his air pump experiments so clearly that anyone with the right equipment could repeat them. He also reported his failures. He wrote about experiments that did not work, that produced unexpected results, that contradicted his hopes. That honesty was new. Before, people only published successes. Publishing failures seemed embarrassing. But Boyle understood that failures are also observations. They tell you what does not happen, which is as useful as knowing what does happen. As you rest here, you can notice that you also value observation over belief in small ways. You check the weather before dressing. You taste your food before adding salt. You feel the pillow to see if it is cool enough. These are tiny experiments. You are trusting your senses more than what someone told you. That is the scientific revolution living inside your daily habits. It took centuries to arrive, but now it is as natural as breathing. Robert Boyle and the redefinition of elements. Robert Boyle was not the first person to think about elements. Democritus had imagined atoms. Aristotle had proposed 4 elements. The alchemists had worked with mercury, sulfur, and salt. But Boyle was the first to define an element in a way that made sense for experimental chemistry. He wrote in The Skeptical Chemist that an element is a body not composed of any other bodies. That sounds simple, but it is powerful. If you take a substance and try to break it down, and you cannot, no matter what you do, then that substance is an element. If you can break it down into 2 or more simpler substances, then it was a compound, not an element. This definition turned chemistry into a game of breaking and testing. You heat something, dissolve it, electrolyze it, react it with other substances. If it splits, you keep splitting. When you reach a substance that refuses to split, you have found an element. Boyle did not know how many elements existed. He suspected there were more than 4, but he did not try to list them. He simply gave chemists a method. The method would take 200 years to complete. The periodic table was still far in the future, but the path was now clear. Chemistry had a goal. Find the fundamental substances, the alphabet of matter. Boyle's redefinition was controversial. Many traditional chemists, still called chemists, thought he was destroying the beautiful simplicity of the 4 elements. They liked the harmony, the symmetry, the poetry of earth, water, air, fire. Boyle's approach seemed cold and mechanical. But Boyle did not care about beauty. He cared about truth. And truth, he argued, is discovered by experiment, not by aesthetic preference. If the universe has 92 naturally occurring elements, then that is the truth. Our job is not to make the universe pretty. Our job is to describe it accurately. One of Boyle's key contributions was his emphasis on the distinction between mixtures and compounds. A mixture, he said, can be separated by physical means, like sand and salt, which can be separated by dissolving the salt in water. A compound, however, requires a chemical reaction to separate the components, like water, which needs electrolysis to be split into hydrogen and oxygen. That distinction is still fundamental. Everything you encounter is either a mixture or a pure substance, and every pure substance is either an element or a compound. Boyle gave you that framework. Boyle also studied the properties of air, showing that it was elastic, compressible, and that it had weight. He weighed a flask, then removed the air with a pump, then weighed it again. The flask was lighter. Air had weight. That observation was shocking. Air seemed weightless because it is fluid and you are immersed in it. But Boyle's balance told the truth. The air in your room right now weighs about as much as a large dog. You do not feel it because the pressure is equal in all directions. But the weight is there. Boyle's work on air pressure also led to practical applications. He predicted that a barometer could be used to measure altitude, that the air pressure would decrease as you climbed a mountain. That prediction was tested and confirmed. Barometers became essential for mountaineering, aviation, and weather forecasting, all from a simple experiment with a glass tube and mercury. That is how the scientific revolution worked. A small observation, carefully made, could change the world. What makes something an element? You have heard the word element many times. The periodic table, chemical elements, the elements of style. But what actually makes something an element? The answer is both simple and subtle. An element is a substance that cannot be broken down into simpler substances by ordinary chemical means. Ordinary chemical means include heating, cooling, dissolving, reacting with acids or bases, and passing electricity through. If none of those techniques can split the substance into different components, then it is an element. Gold is an element. You cannot turn gold into anything simpler by chemistry. You can melt it, hammer it, dissolve it in aqua regia, but it remains gold. The subtle part is the phrase, by ordinary chemical means, because with extraordinary means, like a particle accelerator or a nuclear reactor, you can split an element. You can knock protons out of a gold nucleus and turn it into platinum or mercury. But that is nuclear physics, not chemistry. Chemistry deals with electrons, not nuclei. So the definition holds. An element is a substance that cannot be broken down by chemical reactions. The atoms stay the same. You can move them around, combine them with other atoms, separate them from compounds. But the atom itself, the specific arrangement of protons, neutrons, and electrons, does not change. This definition means that elements are the alphabet of chemistry. Just as the letters A, B, C combine to form words, elements combine to form compounds. Water is 2 hydrogen atoms and 1 oxygen atom, H2O. Salt is 1 sodium atom and 1 chlorine atom, NaCl. Sugar is 12 carbons, 22 hydrogens, and 11 oxygens, C12H, 22O11. The same elements appear in thousands of different compounds, and the properties of the compound are not the same as the properties of the elements. Sodium is a soft, explosive metal. Chlorine is a green, poisonous gas. Together, they make harmless white salt. That mystery, that combination creates something entirely new, is the heart of chemistry. The number of known elements has grown over time. The ancients knew about 7: gold, silver, copper, iron, tin, lead, and mercury. They also knew about carbon, as charcoal and diamond, and sulfur, though they did not always count them as separate elements. By the time of Boyle, chemists had added a few more: antimony, bismuth, zinc, arsenic. By the end of the 18th century, about 25 elements were known. By the end of the 19th century, over 60. Today, there are 118 confirmed elements. 92 occur naturally. The rest are synthetic, created in laboratories and lasting only fractions of a second. The search for new elements continues. Each new element fills a slot in the periodic table and expands the alphabet. One of the most interesting questions about elements is, are there elements we have not discovered yet? The periodic table suggests that elements beyond 118 are possible, but they would be extremely unstable. Some physicists think there might be an island of stability, a set of super heavy elements that last for minutes or hours instead of microseconds. If that island exists, it would open new possibilities for chemistry, but no one has found it yet. The search involves smashing atoms together at near light speed and looking for the decay products. It is the most expensive form of treasure hunting in history. A quiet thought for your resting mind. Every element heavier than iron was forged in a supernova explosion. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were cooked in ancient stars that died before the earth was born. You are made of stardust. That is not a metaphor. That is chemistry. A final question for this cluster of sections. If you had to name the most important element in your life, not chemically, but emotionally, what would it be? And why does it feel fundamental? The rise of modern experiments. The 17th and 18th centuries saw a blossoming of experimental activity across Europe. Laboratories multiplied, not just in the basements of wealthy gentlemen, but in universities, apothecary shops, and even royal palaces. The equipment became more standardized, the methods became more precise, and the questions became more focused. Instead of asking, "How can I turn lead into gold?" chemists began asking, "What happens when I heat this substance in a closed container?" Or, "How much does this gas weigh?" The shift from alchemy to chemistry was not a rejection of the past. It was a refinement. The alchemists had built the tools. The new chemists learned to use them more carefully. One of the most important developments was the balance. Chemists had always weighed things, but the accuracy improved dramatically. The best balances in the 18th century could detect differences of a few milligrams. That might not sound like much, but it was enough to reveal that gases have weight, that metals gain weight when heated, that products of a reaction weigh exactly the same as the starting materials. These measurements change chemistry from a qualitative science, "What is it?" to a quantitative one, "How much?" You cannot understand a chemical reaction until you measure it. The balance made that possible. Another development was the thermometer. Early thermometers were crude. Alcohol in a glass tube with no standard scale. Daniel Gabriel Fahrenheit invented the mercury thermometer in 1714 and proposed a scale that set freezing of water at 32 degrees and boiling at 212. Anders Celsius proposed the scale in 1742, with 0 for boiling and 100 for freezing, later reversed. These scales allowed chemists to measure temperature precisely and to reproduce conditions exactly. A reaction that works at 60 degrees might fail at 70. With a thermometer, you could know the difference. The barometer also became standard equipment. Measuring air pressure allowed chemists to understand how gases behave under different conditions. They discovered that boiling point changes with pressure. Water boils at a lower temperature on a mountain than at sea level. They discovered that the volume of a gas changes with pressure, Boyle's law. They discovered that gases diffuse through each other, mix completely, and exert pressure in all directions. The barometer turned the invisible world of air into something measurable, predictable, and rational. Perhaps the most important experimental tool was the mind itself, trained in skepticism, patience, and record-keeping. Chemists began publishing their methods in such detail that anyone could replicate their work. They included negative results, experiments that did not work. They included tables of data. They drew diagrams of their apparatus. They named new substances in a systematic way. The goal was transparency. The goal was repeatability. Those two principles are still the bedrock of science. An experiment you cannot repeat is not an experiment. It is an anecdote. Gases, the invisible part of chemistry. For most of history, gases were almost invisible to science. You could feel the wind. You could see bubbles in water. You could watch smoke rise. But you could not hold a gas in your hand, weigh it on a balance, or store it in a bottle. Gases seemed ethereal, almost spiritual. The ancient elements called air a single substance. But as experimental techniques improved, chemists realized that air was actually a mixture of different gases, each with its own properties. That realization opened a new world, because if you could isolate individual gases, you could study them. You could find out what they do, where they come from, and how they interact with other substances. The first gas to be clearly distinguished from ordinary air was carbon dioxide. The Flemish chemist Jan Baptist van Helmont, working in the early 17th century, noticed that burning charcoal produced a wild spirit that was different from air. He called it gas sylvester, wood gas, because it came from burning wood. Van Helmont also observed that this gas was produced by fermentation, by the action of acid on limestone, and by the respiration of animals. He could not isolate it completely, but he knew it was different. He also coined the word gas from the Greek chaos, a happy accident that stuck. Another early gas discovery was hydrogen. Robert Boyle observed that when iron filings were added to dilute acid, a flammable vapor was produced. He collected the vapor in a jar and found that it burned with a pale flame. But Boyle did not recognize it as a distinct substance. That recognition came from Henry Cavendish in 1766. Cavendish collected hydrogen, he called it inflammable air, measured its density, and showed that it was the same gas regardless of the metal or acid used. He also discovered that when hydrogen burned, it produced water, a crucial clue for understanding the composition of water itself. Oxygen was discovered independently by Carl Wilhelm Scheele in Sweden and Joseph Priestley in England, both in the early 1770s. Scheele produced oxygen by heating various substances: mercury oxide, saltpeter, manganese dioxide. He called it fire air because it made candles burn brilliantly. Priestley heated mercury oxide using a large burning lens and collected the gas that was released. He noted that a candle burned in this gas with an astonishingly bright flame, and that a mouse lived longer in it than in ordinary air. Priestley called it dephlogisticated air, because he still believed in the phlogiston theory. He did not realize that he had discovered the gas that makes life itself possible. The phlogiston theory was the last major wrong idea in chemistry before the modern period. It proposed that combustible materials contain a substance called phlogiston, which is released during burning. When a metal heated in air turned into a calx, oxide, phlogiston was supposedly lost. The theory worked, sort of, but it had a fatal flaw. When metals gained weight during calcination, how could losing phlogiston make them heavier? Some phlogiston theorists proposed that phlogiston had negative weight. That was a desperate fix. The theory was dying, but it needed one decisive blow. That blow came from Antoine Lavoisier, who used careful weighing experiments to show that combustion and calcination involve the absorption of a gas from the air, not the release of a mysterious substance. He named that gas oxygen, from the Greek oxus, acid, and genao, to produce, because he thought it was present in all acids. Lavoisier's oxygen theory killed phlogiston. It also established that gases are real, measurable, material substances. They obey the same laws as liquids and solids. They have weight. They can be produced, stored, and reacted. The invisible part of chemistry had become visible. Discovering oxygen and its importance. The discovery of oxygen changed everything. Before oxygen, combustion was a mystery. Why does a candle burn? Why does a fire go out when you cover it? Why do some metals gain weight when heated? The phlogiston theory had answers, but they were confusing and contradictory. Lavoisier's oxygen theory provided a clear, consistent explanation. Combustion is a chemical reaction between a fuel and oxygen. The fuel combines with oxygen, releasing heat and light. The products weigh more than the original fuel because they contain the oxygen. That simple insight resolved decades of confusion and opened the door to modern chemistry. Lavoisier did not discover oxygen first. Priestley and Scheele both produced it before him, but Lavoisier understood what he had found. Priestley, stuck in the phlogiston framework, called it dephlogisticated air. He thought it was ordinary air, with the phlogiston removed. Lavoisier saw that it was a distinct substance, fundamental to combustion and respiration. He repeated Priestley's experiments, measured everything, and published his own interpretation. He did not steal credit. He acknowledged Priestley's work. But he provided the correct explanation. That more than the discovery itself is what matters. Science is not just finding things. It is understanding what you have found. One of Lavoisier's crucial experiments involved heating mercury in a sealed glass retort. The mercury formed a red calx, mercury oxide, and the volume of air in the retort decreased by 1/5. The remaining air did not support combustion or life. Lavoisier then heated the red calx, which released a gas that made a candle burn brilliantly. That gas was oxygen. The experiment showed that ordinary air is a mixture of two gases, one reactive, oxygen, and one inert, nitrogen. Lavoisier measured the proportions. About 1/5 oxygen, 4/5 nitrogen. Those numbers are still taught today. The importance of oxygen extended far beyond combustion. Lavoisier also studied respiration. He placed a guinea pig in a sealed container, measured the amount of oxygen consumed and the amount of carbon dioxide produced. He concluded that respiration is a slow form of combustion. Animals take in oxygen, combine it with carbon from their food, produce carbon dioxide and heat. That heat maintains body temperature. That carbon dioxide is exhaled. This insight connected chemistry to biology, to medicine, to the very process of being alive. Oxygen is not just something that feeds flames. It feeds you. Lavoisier also studied the role of oxygen in acid formation. He believed that all acids contained oxygen. That is why he named the element acid producer. He was wrong about that. Hydrochloric acid, for example, contains no oxygen, but his generalization pushed chemists to analyze acids carefully, leading to a better understanding of their composition. Even mistakes can be productive when they are tested experimentally. The discovery of oxygen also had practical applications. It allowed chemists to understand rusting, which is simply the slow combination of a metal with oxygen. It allowed them to understand why food spoils. Bacteria use oxygen to break down organic matter. It allowed them to develop better lamps, better furnaces, better ventilation systems. Today, oxygen is used in steelmaking, in rocket engines, in hospitals to help patients breathe. The gas that Priestley isolated with a burning lens, that Scheele collected in green jars, that Lavoisier named and explained, that gas is part of your every breath, a quiet fact to hold as you rest. The oxygen you are breathing right now was produced by plants, algae, and cyanobacteria using sunlight. Every molecule has a story that goes back millions of years, and you are part of that story. Fire, combustion, and early misunderstandings. Fire was the first chemical reaction that humans truly feared and revered. It kept predators away, cooked food, warmed shelters, hardened tools. But what was fire? The ancients thought it was an element, one of the four. Alchemists thought it was a transformative agent, able to purify or destroy. In the 17th and 18th centuries, fire became a subject of intense scientific investigation, and that investigation produced one of the most interesting wrong theories in history, phlogiston. The phlogiston theory was developed by Johann Joachim Becher and Georg Ernst Stahl in the late 17th and early 18th centuries. According to this theory, any material that could burn contained a substance called phlogiston. When the material burned, it released phlogiston into the air. The leftover ash or calx was the material without its phlogiston. Charcoal was almost pure phlogiston, which is why it burned so completely, leaving almost no ash. Metals contain phlogiston. When a metal was heated, it lost phlogiston to form a calx. To turn a calx back into a metal, you had to add phlogiston, for example by heating the calx with charcoal, which is rich in phlogiston. The theory was elegant. It explained why a candle goes out in a closed container. The air becomes saturated with phlogiston and cannot accept any more. It explained why a mouse cannot live in air where a candle has burned, because the air is full of phlogiston. It explained why charcoal burns so well, because it has so much phlogiston to give. For decades, phlogiston seemed to explain everything about combustion and calcination. Many intelligent chemists, including Joseph Priestley, were committed phlogistonists, but there was a problem. When you heated a metal in air, the calx weighed more than the original metal. If the metal had lost phlogiston, it should weigh less. Some phlogistonists responded that phlogiston had negative weight. It made things lighter when added, heavier when removed. That was a stretch. Others suggested that phlogiston was a form of light or heat, which had no weight, but the measurements kept improving, and the weight gain kept being confirmed. The phlogiston theory was dying. It needed a replacement. Antoine Lavoisier provided that replacement. He repeated the calcination experiments with extreme care, weighing everything before and after. He showed that the weight gain exactly matched the weight of oxygen absorbed from the air. When he heated the calx, it released that oxygen and returned to its original weight. No mysterious phlogiston was needed. Combustion, Lavoisier argued, is the chemical combination of a substance with oxygen. The heat and light are byproducts of that combination. The theory was simple, quantitative, and consistent with all known observations. By the 1790s, phlogiston was dead. But the death of phlogiston was not a humiliation for those who believed in it. Priestley, for example, never accepted the oxygen theory. He continued to defend phlogiston until his death. That does not mean he was a bad scientist. He was a brilliant experimenter who discovered oxygen, carbon monoxide, nitrous oxide, and many other gases. He was also a deeply honest thinker. He looked at the evidence and drew the conclusions that seemed the most reasonable to him. He happened to be wrong. But being wrong is not failure. It is the soil in which right grows. Every wrong theory teaches something. Phlogiston taught chemists to measure weight changes carefully. Without that lesson, Lavoisier might not have succeeded. Antoine Lavoisier and the death of old theories. Antoine Lavoisier was born in Paris in 1743 to a wealthy family. He studied law but preferred science. He inherited a fortune and used it to build the best private laboratory in Europe. He was methodical, precise, and relentless. He did not discover oxygen, but he explained it. He did not invent the balance, but he used it like no one before. He did not create the theory of elements, but he gave it a practical foundation. Lavoisier is often called the father of modern chemistry. That title is not an exaggeration. Before Lavoisier, chemistry was a collection of recipes and speculations. After Lavoisier, it was a quantitative science. One of Lavoisier's greatest contributions was the law of conservation of mass. He demonstrated that in any chemical reaction, the total mass of the products equals the total mass of the reactants. Nothing is lost, nothing is created. If you burn a candle in a sealed container, the mass of the container plus contents does not change. The wax seems to disappear, but it has only turned into carbon dioxide and water vapor, which still weigh the same as the original wax and oxygen. Lavoisier's experiments were so careful that his measurements were accurate to within a few milligrams, remarkable for the 18th century. This law may seem obvious to you now, but it was not obvious then. For centuries, people thought that things could disappear. Wood turned to smoke and ash, water evaporated into nothing, food was consumed and vanished. Lavoisier showed that disappearance is an illusion. The atoms, the mass, the matter, all of it persists. You can burn a log, grind a stone, dissolve a sugar cube. The form changes, the substance does not. That is a profound truth. It means that you are part of a closed system. Every atom in your body has been somewhere else, doing something else, for billions of years. You are borrowing them. You will give them back. Lavoisier also reformed chemical language. He published Méthode de nomenclature chimique in 1787 with colleagues Louis Bernard Guiton de Morveau, Claude Louis Berthollet, and Antoine François de Fourcroy. They proposed a systematic naming system for chemical substances. Instead of oil of vitriol, you say sulfuric acid. Instead of salt of tartar, you say potassium carbonate. The new names describe the composition of the substance, not its history or properties. That system, with modifications, is still used today. Look at any chemical label: sodium chloride, calcium carbonate, ethanol, and you are seeing Lavoisier's influence. Sadly, Lavoisier's life ended tragically. He was a tax collector for the French government, a position that made him wealthy, but also made him a target during the French Revolution. In 1794, during the Reign of Terror, he was arrested, tried, and guillotined. The judge famously said, "The Republic has no need of scientists." Lavoisier was only 50 years old. His friend, the mathematician Joseph Louis Lagrange, remarked, "It took only a moment to cut off that head, and 100 years may not produce another like it." Lavoisier's death was a loss to all of humanity, but his work survived. His wife, Marie-Anne Pierret-Pause, who had assisted him in the laboratory, translated English chemical works into French and preserved his notes. Her drawings of his apparatus appeared in his posthumous publications. She made sure that Lavoisier's ideas reached the next generation of chemists. Without her, much of his work might have been lost or forgotten. The law of conservation of mass. Imagine holding a block of ice in your hands. It is solid, cold, heavy. You set it on a table and watch it melt. The solid becomes liquid, but the puddle weighs the same as the ice did. You heat the water until it boils. The liquid becomes vapor, invisible. If you capture that vapor in a sealed container, it still weighs the same as the ice at the beginning. Nothing has disappeared. The form has changed, but the stuff, the H2O molecules, has only rearranged. This is the law of conservation of mass. It is one of the most fundamental principles in all of chemistry, and it was Antoine Lavoisier who placed it on a firm experimental foundation. Before Lavoisier, many people believed that matter could be destroyed or created. Wood burned to ash. Where did the wood go? Food was eaten. Where did the food go? Water evaporated. Where did the water go? Common sense seemed to say that things vanish. But common sense is not always right. Lavoisier showed that if you carefully measure everything that goes into a reaction and everything that comes out, the totals match. The wood becomes carbon dioxide, water vapor, and a small amount of ash. The food becomes carbon dioxide, water, and waste products. The water becomes vapor, still present in the air. Nothing is lost. One of Lavoisier's most elegant demonstrations involved heating tin in a sealed glass vessel. He weighed the vessel before heating, then heated it until the tin turned into a grey powder, tin oxide. He weighed the vessel again, the same weight. Then he opened the vessel, and air rushed in with a hiss. The weight increased. The increase was exactly the weight of the oxygen that had combined with the tin. The tin had gained weight, but the total system, tin plus oxygen, had not changed. The law held, and it held for every reaction Lavoisier tested. The conservation of mass has profound implications for how you see the world. It means that you are not a separate being, isolated from the rest of matter. You are a temporary collection of atoms that have been moving through the universe for billions of years. The carbon in your cells was once in the air, then in a plant, then in an animal, then in the soil, then in another plant. The water you drink today was once in a cloud, a river, an ocean, a dinosaur. The oxygen you breathe was produced by a tree or a phytoplankton. You are not owning these atoms. You are borrowing them. And one day, you will give them back. This insight can be comforting or unsettling, depending on your mood. But there is something beautiful about it. You are connected to everything that has ever lived. The atoms in your left hand may have been in a Roman soldier's sword. The atoms in your right hand may have been in a medieval monk's candle. The air in your lungs may have been exhaled by a whale, a pine tree, a baby. The boundaries of your body are not as solid as they seem. You are constantly exchanging matter with the environment. Every breath, every meal, every trip to the bathroom is a transaction with the world. The law of conservation of mass is not just a chemical principle. It is a kind of poetry. It tells you that nothing is ever truly gone. The people you have lost are still here, not as conscious beings, but as atoms that were once part of them. Those atoms are in the soil, the trees, the air, and perhaps in you. That is not a religious claim. It is a chemical fact. The matter that made them persists. The form is gone, but the substance remains. Lavoisier's law also has practical applications. It allows chemists to balance equations. If you start with certain amounts of reactants, you can predict how much product you will get. That is essential for manufacturing, for medicine, for environmental science. When a pharmaceutical company makes a drug, they need to know how much starting material to use. When an environmental scientist measures pollution, they need to track where the pollutants go. The conservation of mass is the accounting system of the material world. Why nothing truly disappears in reactions? You have probably thrown things away. A broken cup into the trash, a spoiled apple into the compost, a burned candle into the garbage. But where do these things go? The trash truck takes them to a landfill where they sit. Over time, they break down. The cup becomes smaller pieces of ceramic. The apple becomes soil. The candle wax becomes small molecules that bacteria eat. But the atoms, the silicon, the calcium, the carbon, the hydrogen, the oxygen, they never go anywhere. They just change partners. Nothing truly disappears. Everything is still there, somewhere, in some form. This is the law of conservation of mass in everyday life. When you cook an egg, the egg white turns from clear to opaque. The weight of the egg does not change. The proteins have unfolded and bonded to each other, but the atoms are the same atoms. When you burn a piece of paper, you see it turn into ash and smoke. The ash weighs much less than the paper, but the missing weight is not gone. It has combined with oxygen to form carbon dioxide and water vapor, which float away into the air. If you could catch those gases and weigh them, they would exactly account for the lost mass. Think about a tree growing in a forest. Where does the wood come from? Most people say the soil, but that is not correct. A tree's wood is mostly carbon, hydrogen, and oxygen. The carbon comes from carbon dioxide in the air. The hydrogen and oxygen come from water. The tree takes these gases out of the atmosphere and turns them into solid wood. That is why a tree does not leave a hole in the ground as it grows. It is building itself from thin air. When the tree dies and rots, the process reverses. The wood combines with oxygen and releases carbon dioxide back into the air. Nothing disappears. It just cycles. This cycling happens at every scale. Your body is a temporary knot in a flowing river of atoms. You eat food, you breathe air, you drink water. Your body uses those atoms to build itself. Then you exhale carbon dioxide, you sweat, you use the bathroom. The atoms leave you and become part of something else. A carbon atom that is in your hand right now might be in a blade of grass next year. It might be in a cow, then in a steak, then in another person. It might be in the ocean, in a shell, in a limestone cliff. The journey is endless. The idea that nothing truly disappears can change how you feel about waste. When you throw something away, there is no away. There is only somewhere else. The plastic bottle does not vanish. It goes to a landfill or an incinerator or the ocean. The atoms are still there, still taking up space, still interacting with other atoms. That is why recycling matters. That is why reducing consumption matters. The law of conservation of mass is not just a chemical curiosity. It is an ethical fact. You cannot make things go away. You can only move them. This principle also applies to the human body at the end of life. When a person dies, their body breaks down. The atoms that were once organized into a living person become organized into other things. Some become bacteria, some become plants, some become soil, some become air. The person is gone as a conscious entity, but the matter remains. Many cultures have rituals that honor this continuity, scattering ashes, natural burial, leaving the body to the elements. These rituals recognize the truth that Lavoisier proved. Nothing is created, nothing is destroyed. Everything is only transformed. Naming chemicals, bringing order to chaos. Imagine walking into a library where no book has a title. Every shelf is filled with volumes, but you cannot tell what they are about. You see a red book, a blue book, a thick book, a thin book. That is all. That is what chemistry was like before systematic naming. Substances had names like oil of vitriol, sulfuric acid, blue vitriol, copper sulfate, sugar of lead, lead acetate, cream of tartar, potassium bitartrate. These names told you something about appearance or origin, but nothing about composition. Two substances with completely different names might be the same chemical. Two substances with similar names might be completely different. It was chaos. Lavoisier and his colleagues decided to bring order. They proposed that every chemical should have a name that reflects its composition. A simple rule: the name should tell you what elements are present. Sulfuric acid was named from sulfur because it contains sulfur. Potassium carbonate was named from potash, a source of potassium, and carbonic acid. The system was not perfect, and it has been modified many times. But it established a principle. Naming is not arbitrary. A chemical's name is a condensed description of its molecular structure. The system they created is still the foundation of chemical nomenclature today. For simple substances, the name is the element: iron, copper, sulfur. For compounds of two elements, the name uses ID: sodium chloride, magnesium oxide, calcium carbide. For compounds that include oxygen, different suffixes indicate different proportions: sulfite versus sulfate, nitrite versus nitrate. For organic chemistry, a whole different system evolved, based on the structure of carbon chains. The names can become terrifying. Try saying tetraethyl lead or dichlorodiphenyl trichloroethan E, but they are logical. A trained chemist can look at a name and draw the molecule. This naming revolution had enormous consequences. It allowed chemists to communicate across languages and countries. A French chemist could read an English paper and know exactly which compound was used. It allowed chemical knowledge to accumulate. Instead of memorizing thousands of unrelated names, students could learn patterns. It allowed new compounds to be named consistently, fitting into the existing system. The periodic table itself, which would come later, depended on this clarity. You cannot organize elements if you do not have clear names for them. The naming system also revealed errors. Sometimes two different names referred to the same compound. Sometimes the same name referred to different compounds. Clearing up these confusions forced chemists to re-examine their experiments. Did you really make a new substance, or did you just give a new name to an old one? The requirement of clear naming imposed a kind of honesty. You could not hide behind vague terminology. You had to say exactly what you had, what it was made of, and how you made it. Of course, some old names survive in common usage. You still say quicklime, calcium oxide, and slaked lime, calcium hydroxide. You still say muriatic acid, hydrochloric acid in some contexts, but the official names are systematic. If you study chemistry, you learn the rules. You learn that ferrous means iron with a +2 charge, and ferric means iron with a +3 charge. You learn that 8 means more oxygen than IT. It is a language like any other. And like any language, it takes practice to speak fluently. A question for your sleepy mind. If you had to rename your own elements, the basic traits that make you who you are, what new names would you give them using consistent rules? The birth of modern chemistry. The period from 1770 to 1830 saw chemistry transform from a branch of natural philosophy into a mature science. Lavoisier had provided the theoretical framework. Conservation of mass, the role of oxygen, the definition of elements. His collaborators and successors refined the details. They discovered new elements. They developed new techniques. They established institutions, journals, societies, professorships that would carry chemistry into the 19th century and beyond. By the time Lavoisier died, chemistry was already different. By the time his students died, it was unrecognizable from what it had been a century earlier. One of Lavoisier's important collaborators was Claude Louis Berthollet. He studied the chemistry of bleaches and discovered that chlorine could be used to whiten fabrics. That discovery led to the modern bleaching industry. He also studied chemical equilibrium, the idea that many reactions are reversible and reach a balance point. Berthollet traveled to Egypt with Napoleon and observed that salt deposits formed in lakes, suggesting that reactions could run backward under different conditions. His work on equilibrium laid the foundation for later chemists like Henry Louis Le Chatelier. Another key figure was Joseph Louis Gay-Lussac. He studied the behavior of gases and discovered that when gases react, they do so in simple volume ratios. For example, 2 volumes of hydrogen react with 1 volume of oxygen to produce 2 volumes of water vapor. This is Gay-Lussac's law of combining volumes. It suggested that equal volumes of gases contain equal numbers of particles, an idea that would lead directly to Avogadro's hypothesis and eventually to the mole concept. Gay-Lussac also improved methods for analyzing gases and developed techniques for measuring vapor densities. The Swedish chemist Jöns Jacob Berzelius made enormous contributions. He developed the system of chemical symbols that you still use: H for hydrogen, O for oxygen, Ca for calcium, Fe for iron, from ferrum. He determined the atomic weights of many elements with unprecedented accuracy. He discovered several new elements: cerium, selenium, thorium. He distinguished between catalysts and promoters. He coined the terms allotropy, different forms of the same element, like diamond and graphite, and polymer, large molecules made of repeating units. Berzelius was one of the most productive chemists in history, and his laboratory trained a generation of students who spread his methods across Europe. The birth of modern chemistry also meant the death of older ideas. Phlogiston was gone. The 4 elements were gone. The idea of spirits and essences was gone. In their place was a framework based on measurable properties: weight, volume, temperature, pressure. Chemistry became quantitative. It became predictive. If you knew the composition of a substance, you could predict how it would react with other substances. If you knew the atomic weights, you could calculate the proportions needed for a reaction. This was not just description. This was engineering at the molecular level. Institutions also changed. The Royal Society of London continued to publish important work. The French Academy of Sciences supported Lavoisier and his circle. New journals appeared: Annales de Chimie in France, Journal für Chimie und Physik in Germany. Universities established chemistry chairs. The first chemical laboratories specifically designed for teaching were built at the University of Gießen by Justus von Liebig in the 1820s. Liebig's model, a research group, a teaching laboratory, a systematic curriculum, became the standard for chemistry education worldwide. That model is still followed today. A quiet fact to carry into sleep. The word chemistry itself comes from the same root as alchemy, the Arabic alchemia, from the Egyptian chem, black earth. But by 1800, the meaning had shifted. Chemistry was no longer the study of transformation for spiritual purposes. It was the study of matter for its own sake. That shift, from what can matter become to what is matter, is the birth you are resting with tonight. John Dalton and the atomic theory. John Dalton was a quiet English school teacher with a stammer and a passion for weather. He was born in 1766, the son of a poor weaver. He had little formal education, but taught himself mathematics, Greek, and Latin. He kept a daily weather diary for 57 years, recording over 200,000 observations. That patience, that careful attention to data would serve him well, because Dalton is the person who turned the ancient idea of atoms, the atomos of Democritus, into a quantitative, testable scientific theory. He is the father of the atomic theory in its modern form. Dalton's path to atoms began with the study of gases. He noticed that in a mixture of gases, each gas exerts pressure independently. He also noticed that different gases have different solubilities in water. None of the existing theories could explain these observations. Dalton wondered, what if gases are made of tiny particles? And what if the particles of different gases have different sizes and different weights? That would explain why some gases mix easily and others do not. It would explain why some dissolve more readily. The idea of atoms, dormant for 2,000 years, began to stir. Dalton's key insight was to connect atoms to measurable quantities. He realized that if atoms exist, then the mass of an atom relative to other atoms could be determined by measuring the weights of elements that combine. For example, if water is made of hydrogen and oxygen, and you know how much hydrogen combines with how much oxygen, you can calculate the relative atomic weight of oxygen compared to hydrogen. Dalton made the first table of atomic weights in 1803. His numbers were not accurate by modern standards. He thought water was HO, not H2O, but the method was revolutionary. Dalton published his atomic theory in 1808 in a book called A New System of Chemical Philosophy. The theory had 5 main points. First, all matter is made of atoms, which are indivisible and indestructible. Second, all atoms of a given element are identical in mass and properties. Third, compounds are formed when atoms of different elements combine in simple whole number ratios. Fourth, atoms of different elements have different masses. Fifth, chemical reactions involve the rearrangement of atoms, not the creation or destruction of atoms. These points, with some modifications, atoms are divisible, isotopes exist, are still taught today. The importance of Dalton's theory cannot be overstated. It gave chemists a reason to measure atomic weights precisely. It gave them a way to predict how much of one substance would react with another. It turned chemistry into a deductive science. If the theory is right, then water must always contain hydrogen and oxygen in the same proportion by weight. If you find a compound that breaks that pattern, either your measurement is wrong or the theory needs adjustment. Dalton's atoms were not visible. They were not directly proven, but they were powerfully useful. One of the strongest pieces of evidence for Dalton's theory was the law of multiple proportions. Dalton noticed that when two elements form more than one compound, the masses of one element that combine with a fixed mass of the other are in simple whole number ratios. For example, carbon and oxygen form CO and CO2. In CO, 12 grams of carbon combine with 16 grams of oxygen. In CO2, 12 grams of carbon combine with 32 grams of oxygen. The ratio of oxygen masses, 16 to 32, is 1 to 2, a simple whole number. This pattern would be random if atoms did not exist. But if atoms exist, it is exactly what you would expect. Dalton himself did not have experimental proof. He never saw an atom. But his theory was so elegant, so consistent, so useful that chemists began to accept it. Over the next century, experimental evidence would accumulate. Brownian motion, the discovery of electrons, radioactive decay, and finally, in the 20th century, images of individual atoms using electron microscopes. Dalton was right. The atoms that Democritus imagined, that Lucretius wrote about, that Lavoisier's law implied, they are real. And you, lying in the dark, are made of them. Atoms. Tiny building blocks of everything. Close your eyes and imagine the smallest thing you can see. A grain of salt, a speck of dust, a single hair. Now imagine something 1,000,000 times smaller. Now 1,000,000,000 times. Now 1,000,000,000,000. You are still not at the size of an atom. Atoms are so tiny that a single drop of water contains an almost unimaginable number of them, more than all the grains of sand on all the beaches of the earth. You cannot see them. You cannot feel them. You cannot imagine them directly, but you can imagine their effects. The hardness of a diamond, the softness of lead, the green of a leaf, the heat of a flame. All of these emerge from the arrangements and motions of atoms. An atom of hydrogen, the simplest and lightest element, consists of a single proton and a single electron. The proton is much heavier than the electron, about 1,800 times heavier, and it sits in the center, a tiny nucleus. The electron orbits this nucleus, not like a planet, but more like a fuzzy cloud of probability. Between the nucleus and the electron is mostly empty space. If the nucleus were the size of a marble, the electron cloud would be the size of a football stadium. Your body, your bed, your room, all of it is almost entirely empty space. You do not fall through the floor because the electrons in your feet repel the electrons in the floor. The emptiness is not passive. It is full of force. Atoms of different elements have different numbers of protons. Hydrogen has 1. Helium has 2. Carbon has 6. Oxygen has 8. Gold has 79. The number of protons determines the element. If you change the number of protons, you change the element. That is why alchemists could not turn lead into gold by chemical means. To change a lead atom into a gold atom, you would have to remove 3 protons from its nucleus. That requires nuclear physics, not chemistry. The alchemists were trying to do something impossible with the tools they had, but they were not foolish. They just did not know about protons. Atoms are not solid spheres, as Dalton imagined. They are mostly empty space with a dense nucleus and a cloud of electrons. The nucleus contains protons, which have a positive charge, and neutrons, which have no charge. The electrons have a negative charge and balance the protons, so the atom is neutral. The electrons occupy energy levels or shells. The outermost shell determines how the atom will behave chemically. atoms with a full outer shell, like helium, neon, argon, are inert. They do not react. Atoms with one missing electron or one extra electron are highly reactive. They will grab or give away electrons to become stable. The size of an atom is measured in tiny units called angstroms. A typical atom is about 1/10 billionth of a meter across. To give you a sense, a human hair is about 80,000 times wider than a single carbon atom. You could line up hundreds of thousands of carbon atoms across the width of a single hair. That is small. That is impossibly small. And yet, chemists can count atoms, weigh them, measure their properties, and even move them one by one using special microscopes. The invisible has become visible after 2,500 years of wondering. One of the most beautiful things about atoms is how they combine. They are like letters in an alphabet, only about 100 naturally occurring letters, but they can form an infinite number of words, called molecules. A water molecule is made of 2 hydrogen atoms and 1 oxygen atom. A salt molecule is made of 1 sodium atom and 1 chlorine atom. A sugar molecule is made of 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. Each molecule has a specific shape, a specific set of properties. The shape of a molecule determines how it tastes, how it smells, how it interacts with your body. A small change in the arrangement of atoms can turn a medicine into a poison, a perfume into a stench. Chemistry is the study of these tiny differences that make enormous differences. As you rest here, consider that you are not separate from the atoms. You are a collection of about 7 octillion atoms. Most of them are oxygen. About 18% are carbon. About 10% are hydrogen. The rest are nitrogen, calcium, phosphorus, and tiny amounts of many other elements. These atoms are not just sitting still. They are moving, vibrating, bonding, breaking. Your body is not a static object. It is a dynamic process, a continuous flow of atoms that enter and leave. Why atoms combine in simple ratios? If atoms are the building blocks, then chemistry is the art of stacking them. But atoms do not stack randomly. They follow strict rules. One of the most important rules is that atoms combine in simple, whole number ratios. You never find a compound that contains, say, 2.5 hydrogen atoms for every oxygen atom. It is always 2:1, or 1:1, or 3:2. These ratios are not arbitrary. They emerge from the way atoms share or transfer electrons. The need for stability drives atoms to form bonds, and those bonds produce specific, repeatable numbers. Consider water again. 2 hydrogen atoms and 1 oxygen atom. Why not 3 hydrogen atoms? Because oxygen has 6 electrons in its outer shell, and it wants 8. 2 hydrogen atoms each contribute 1 electron, giving oxygen a full outer shell. 3 hydrogen atoms would give oxygen 7 electrons, not full, and the extra hydrogen would have nowhere to put its electron. The ratio 2:1 is the most stable arrangement. The atoms are not choosing. They are following the laws of quantum mechanics, but you can imagine them as little magnets, each with a specific number of sticky spots. Hydrogen has 1 sticky spot. Oxygen has 2. So 2 hydrogens stick to 1 oxygen. This simple ratio rule was one of John Dalton's key insights. He noticed that when elements combine, the proportions are always in small whole numbers. For example, nitrogen and oxygen form several compounds. One compound contains 2 nitrogen atoms for every 1 oxygen atom. Another contains 1 nitrogen for every oxygen. Another contains 1 nitrogen for every 2 oxygens. All of these are simple ratios. Dalton used this pattern as evidence for atoms. If matter were continuous, you could have any ratio. Gasoline and air mix in many proportions. But compounds are not mixtures. They are chemical unions, and their formulas are fixed. The law of definite proportions states that a given compound always contains the same elements in the same proportion by mass. Water from your tap, water from a rain cloud, water from a glacier, all are about 11% hydrogen and 89% oxygen by weight. Not approximately. Exactly within the limits of measurement. If you find a sample that deviates, it is not pure water. It is water with something else dissolved in it. This law was established by Joseph Louis Proust in the late 18th century, after a long debate with Berthollet, who thought compositions could vary. Proust won because his measurements were more careful. The law of definite proportions is a cornerstone of modern chemistry, a quiet fact to hold as you breathe. The ratio of hydrogen to oxygen in water by weight is 1:8. That means 1 gram of hydrogen combines with 8 grams of oxygen to make 9 grams of water. No matter where you collect the water, no matter how old it is, that ratio holds. The same is true for every pure compound. Table salt is always about 39% sodium and 61% chlorine by weight. Sugar is always about 42% carbon, 6.5% hydrogen, and 51% oxygen. These fixed ratios are like fingerprints. They identify the substance. The law of multiple proportions, also discovered by Dalton, applies when 2 elements form more than 1 compound. In that case, the masses of one element that combine with a fixed mass of the other are in simple ratios. For 1 carbon-oxygen compound, 12 grams of carbon combine with 16 grams of oxygen. For another carbon-oxygen compound, 12 grams of carbon combine with 32 grams of oxygen. The ratio between the 2 oxygen amounts is 1:2. Simple, elegant, and inexplicable unless matter is made of atoms that combine in discrete units. These laws, taken together, form the experimental foundation of atomic theory. You do not need to see our atoms to know they exist. You just need to weigh things carefully and notice the patterns. Molecules. When atoms come together. An atom is lonely. It has electrons, a nucleus, a set of properties. But most atoms do not want to be alone. They want to hold hands. When 2 or more atoms bond together, they form a molecule. A molecule is the smallest unit of a compound that still has the properties of that compound. A single water molecule is still water. It is wet. It bends light. It freezes and boils at the same temperatures as a glass of water. But a single molecule is far too small to see, to taste, to feel. You need billions and billions of them to make a drop. But each drop is just those molecules stacked together. Molecules come in all sizes. The smallest molecule is hydrogen gas. 2 hydrogen atoms bonded together. Oxygen gas is 2 oxygen atoms bonded together. Nitrogen gas, which makes up most of the air, is 2 nitrogen atoms bonded together. These simple molecules are symmetrical and stable, but molecules can also be huge. A protein molecule can contain tens of thousands of atoms. A single DNA molecule contains billions. The molecule of a common plastic, like a plastic bottle, is a long chain of carbon atoms with hydrogen atoms attached. repeated thousands of times. Despite its size, it is still a single molecule, one continuous chain of bonds. The shape of a molecule matters enormously. Water is bent, not straight. The two hydrogen atoms attach to the oxygen at an angle. That bent shape gives water its unusual properties, its ability to boil at a relatively high temperature, its power to dissolve many substances, its strange habit of expanding when it freezes. If water were straight, it would be a gas at room temperature. Life would not exist. A small change in shape changes everything. Methane, the main part of natural gas, is shaped like a pyramid, a carbon atom in the center with 4 hydrogen atoms at the corners. Ammonia is shaped like a tripod, 3 hydrogens and 1 pair of electrons. Each shape determines how the molecule interacts with other molecules. Molecules are not static. They vibrate. Bonds stretch and compress. Atoms rotate around single bonds. The whole molecule tumbles through space. At room temperature, a typical molecule undergoes billions of collisions per second, each collision changing its motion, its shape, its energy. You cannot see this dance, but it is happening right now in your pillow, your blanket, your body. The molecules of air around you are moving at hundreds of meters per second, bouncing off each other and off your skin. That motion is heat. When you feel warm, you are feeling the kinetic energy of molecules. Some molecules are held together by strong bonds, like the bonds within a diamond. Others are held together by weak forces, like the hydrogen bonds between water molecules. These weak forces are not weak in an absolute sense. They still require energy to break, but compared to the bonds within a molecule, they are gentle. That gentleness is what allows water to flow, ice to melt, steam to rise. If the forces between molecules were as strong as the bonds inside them, everything would be a rigid solid. Movement would be impossible. Life would be impossible. The discovery of molecules as distinct entities came from chemistry, not from direct observation. A scientist named Amedeo Avogadro proposed that equal volumes of gases contain equal numbers of molecules. That idea was controversial for decades, but it led to the determination of molecular weights and the distinction between atoms and molecules. Today, you can see molecules with special microscopes. Images of individual molecules shaped exactly as theory predicted. The invisible has become visible. The beauty of chemical formulas. A chemical formula looks like a code. You might have seen something like water written as H2O or carbon dioxide as CO2. These letters and numbers are not arbitrary. They tell you exactly which atoms are present and in what proportion. The small number after an element means that many atoms of that element in the molecule. Water written that way means 2 hydrogen atoms and 1 oxygen atom. Carbon dioxide means 1 carbon and 2 oxygens. Table salt written as NaCl means 1 sodium and 1 chlorine. The number 1 is usually not written. The formula is a compact, elegant description of a molecule. Formulas can be simple or complex. Methane, the main ingredient of natural gas, is written as CH4. Glucose, a simple sugar, is written as C6H12O6. The difference between glucose and another sugar called fructose. Both have the same formula with 6 carbons, 12 hydrogens, and 6 oxygens, is not in the formula. They have the same atoms but in different arrangements. That is why chemists also use structural drawings, which show how atoms are connected. A structural drawing of glucose looks like a ring of 5 carbons and 1 oxygen, with side chains. The formula tells you what is there. The structure tells you where everything is. The beauty of chemical formulas is that they allow prediction. If you know the formula of a compound, you can calculate how much of each element it contains. You can predict its molecular weight. You can determine how much of it will react with another substance. The formula is not just a label. It is a key. It unlocks the quantitative side of chemistry, the side that allows engineers to design factories, pharmacists to make medicines, environmental scientists to track pollution. Without formulas, chemistry would still be a catalogue of stories. One of the most satisfying achievements of 19th century chemistry was the determination of correct formulas for hundreds of compounds. Chemists developed methods to burn a sample and measure how much carbon and hydrogen were in it. They measured carefully, calculated the ratios, and proposed formulas. Often, they disagreed. The debate over the formula of water, was it HO or H2O, lasted decades. The correct formula, 2 hydrogens and 1 oxygen, was settled by combining Avogadro's idea about gases with measurements of vapor density. Once it was settled, the whole field advanced rapidly. Chemical formulas also reveal patterns. The formulas of alcohols are all variations of a pattern, a chain of carbon atoms with hydrogen atoms, ending with OH. The formulas of simple fuels like methane, ethane, propane are all variations of CnH2n+2. The formulas of vinegar and other related acids are variations of CnH2n+1, COOH. These patterns are not coincidences. They reflect the underlying structures of organic chemistry, carbon chains with hydrogen atoms attached. Once you see the pattern, you can predict the properties of a compound you have never seen before. A formula can also be beautiful in its simplicity. The formula of ozone is O3, 3 oxygen atoms bonded in a bend shape. The formula of hydrogen peroxide is H2O2, 2 hydrogens and 2 oxygens, with a weak bond between the oxygens that makes it a powerful bleach. The formula of baking soda is NaHCO3, 1 sodium, 1 hydrogen, 1 carbon, 3 oxygens. That single formula explains why baking soda fizzes when you add vinegar. The carbonate turns into carbon dioxide gas. Why it makes cakes rise, why it freshens refrigerators. Behind every everyday object, there is a formula. As you rest, you might think of your own body as a collection of formulas. The water in your cells is H2O. The salt in your blood is NaCl. The calcium in your bones is a formula involving calcium, phosphorus, and oxygen. The hemoglobin in your blood is a huge formula with nearly 10,000 atoms. That formula is not just a string of letters. It is a precise description of a protein that carries oxygen from your lungs to your fingers, your toes, your brain. Without that formula, you would not be here. Early experiments that proved atoms exist. For 2,000 years, atoms were a hypothesis. A beautiful, useful, plausible hypothesis, but still unproven. No one had ever seen an atom. No one had ever measured a single atom. The evidence was indirect. The laws of definite and multiple proportions, the combining volumes of gases, the patterns of chemical formulas. But indirect evidence is not proof. Some scientists remained skeptical. They argued that atoms were a convenient fiction, a mathematical trick, not real physical objects. The proof would come from experiments in the 19th and early 20th centuries, experiments that made the invisible visible. One of the first convincing pieces of evidence came from the study of Brownian motion. In 1827, a botanist named Robert Brown observed under a microscope that tiny pollen grains suspended in water jittered and danced continuously. They never stopped. Brown could not explain why. For decades, the cause was a mystery. In 1905, Albert Einstein published a paper showing that the jittering was caused by water molecules colliding with the pollen grains. The water molecules were too small to see, but their collective effect was visible. Einstein derived a mathematical relationship between the size of the grains, the temperature of the water, and the rate of jittering. When a French physicist named Jean Perrin tested Einstein's predictions, he got a perfect match. Perrin could calculate the number of molecules in a given volume. The agreement with other methods was stunning. Brownian motion provided direct visual proof that molecules exist. Another line of evidence came from chemistry itself. A Canadian chemist named Frederick Soddy studied radioactive materials and discovered that atoms of the same element could have different masses. He called them isotopes. The existence of isotopes proved that atoms were real, because you could weigh them individually using a device called a mass spectrograph. The English physicist J. Thomson developed the mass spectrograph in the early 20th century, allowing the measurement of atomic masses with astonishing precision. He could separate isotopes of neon gas and show that they had different weights. You cannot separate a fiction. Isotopes are real. The most direct evidence came from an invention in 1981 called the scanning tunneling microscope, created by Gerd Binnig and Heinrich Rohrer. This microscope uses a very sharp tip that scans over a surface at a distance smaller than the width of a few atoms. A tiny electrical current flows between the tip and the surface. By measuring the current, the microscope can map the position of individual atoms. In 1990, researchers at a company called IBM used this microscope to arrange 35 xenon atoms on a nickel surface to spell out the company's initials. That image, individual atoms arranged by human hands, circulated around the world. It was the final proof. Atoms are real. You can see them. You can move them. You can write with them. A quiet fact to carry into sleep. The same year that Einstein wrote his paper on Brownian motion, 1905. He also published papers on special relativity and the photoelectric effect. That year is called his miracle year. One of his 3 great works proved the existence of atoms. So the same mind that gave you the famous equation relating energy and mass also gave you the mathematical proof that matter is made of tiny dancing particles. The experiments that proved atoms exist are a testament to human ingenuity. You cannot see an atom with your eyes, but you can build instruments that see them for you. You can design experiments that reveal their effects. You can calculate their properties from measurements of things you can see. The path from Democritus to the scanning tunneling microscope is a path of 2,500 years of persistent, patient, cumulative inquiry. Each generation added a little more evidence, a little more certainty. And now, lying in your quiet room, you can rest in the knowledge that atoms are not a theory. They are a fact. They are what you are made of. They are what the whole world is made of. The discovery of electrons. By the late 19th century, most chemists had accepted that atoms existed. But what did an atom actually look like? John Dalton had imagined them as tiny, solid spheres, like miniature billiard balls that could never be broken. That image was comforting in its simplicity. But new experiments were beginning to suggest something far stranger. Atoms were not solid at all. They contained even smaller pieces. The first of these subatomic pieces to be discovered was the electron, a particle so incredibly light that it would take nearly 2,000 of them to equal the mass of a single hydrogen atom. The discovery of the electron came from the work of a British physicist named J. Thomson in 1897, and it cracked open the atom for the first time. Thomson was studying cathode rays, those mysterious glows that appeared inside glass tubes when electricity was passed through them at very low pressure. No one knew what these rays were. Some thought they were a form of light. Others thought they were some kind of wave. Thomson built a special tube that allowed him to bend the rays using electric fields and magnetic fields. By measuring exactly how much the rays bent, he could calculate the ratio of the particle's electric charge to its mass. The result was astonishing. That ratio was enormous, meaning the particles were either very highly charged or incredibly light. And the ratio was exactly the same no matter what gas he put in the tube, and no matter what metal he used for the electrodes. That meant these particles were present in all atoms. They were universal. Thomson called them corpuscles, but the name that stuck was electrons. Thomson also tried to measure the charge of a single electron. He could not do it directly, but his experiments showed that the electron was at least 1,000 times lighter than the lightest atom, hydrogen. That was a shock. The atom was supposed to be the smallest thing in existence. Yet here was something much, much smaller. The indivisible atom had been divided. Thomson proposed a model of the atom as a sphere of uniform positive charge, with electrons embedded inside it like raisins in a pudding. This became known as the plum pudding model. It was a first attempt to picture the atom's interior, and although it would soon be proven wrong, it was a necessary step toward the truth. The discovery of electrons solved several long-standing puzzles. For centuries, people had wondered what carries electricity through a metal wire. The answer was electrons. They flow from atom to atom, pushed along by an electric field. That is why metals are such good conductors. Their outer electrons are free to move about, not tied down to any single atom. The discovery also explained why certain chemical reactions produce electric currents. A battery works because electrons are forced to travel through an external wire, doing useful work as they go. The tiny, almost weightless electrons suddenly became the key to understanding electricity, magnetism, and the nature of chemical bonds. Think about your own body for a moment. Your nervous system runs on electrical signals. Every thought, every movement, every heartbeat begins with a tiny flow of ions, atoms that have gained or lost electrons. When you decide to lift your hand, a wave of electrical depolarization travels down your nerves. That wave is nothing more than electrons shifting their positions, sodium and potassium ions moving across cell membranes. You are alive because electrons dance in precise patterns. Without them, there would be no consciousness, no sensation, no life at all. The electron, discovered in a glass tube in a Cambridge laboratory, is the silent partner in every breath you take. There is something deeply human about Thomson's discovery. He was not trying to revolutionize physics. He was just curious. He saw a strange glow and wanted to know what it was. He built apparatus, took measurements, and let the data speak. That openness to surprise, the willingness to follow evidence even when it contradicts your expectations, is the heart of science. Thomson expected to find waves. He found particles, and instead of dismissing the result, he embraced it. His discovery opened a door that led, eventually, to quantum mechanics, to semiconductors, to every electronic device you have ever used. The electron is the ghost in the machine of modern life. Inside the atom, more than just a solid sphere. After J. Thomson discovered the electron, scientists knew that atoms contained tiny, negatively charged particles. But atoms are electrically neutral overall. That means there must be positive charge somewhere to balance the negative electrons. Where was that positive charge hiding? Thomson thought it was spread out in a diffuse cloud, with electrons embedded inside like raisins. It was a neat, tidy model. But a brilliant experiment by one of Thomson's former students, Ernest Rutherford, would shatter that tidy picture forever. The year was 1909. The place was the University of Manchester, and the experiment was about to reveal the true structure of the atom. Rutherford, working with his assistants Hans Geiger and Ernest Marsden, designed an experiment to test Thomson's model. They took a very thin sheet of gold foil, so thin that it was only a few hundred atoms thick. Then they fired a beam of alpha particles at the foil. Alpha particles are heavy, positively charged particles emitted by radioactive elements. They are fast and energetic. According to Thomson's model, the positive charge in the gold atoms was spread out thinly, so the alpha particles should pass straight through the foil with only tiny, gentle deflections. That was the expectation. What Geiger and Marsden saw was completely different. Most of the alpha particles did pass straight through. That part matched the expectation. But a small number, about 1 in every 8,000, were deflected at sharp angles. Some bounced back almost exactly the way they had come. Rutherford later said that this result was almost as incredible as firing a 15-inch artillery shell at a piece of tissue paper and having the shell bounce back and hit you. It was impossible to explain with Thomson's model. There was nothing solid enough in the plum pudding to deflect a heavy alpha particle so dramatically. Rutherford thought deeply about the results. He realized that the positive charge of the atom could not be spread out. It had to be concentrated in an incredibly tiny, incredibly dense nucleus. The electrons must be orbiting around this nucleus at a relatively large distance, leaving most of the atom as empty space. That is why most alpha particles went straight through. They missed the tiny nucleus entirely. But when an alpha particle happened to hit the nucleus directly, it was repelled by the positive charge and bounced back. The nuclear model of the atom was born. This discovery changed everything. The atom was not a solid sphere. It was mostly emptiness. If you blew up a hydrogen atom to the size of a football stadium, the nucleus would be a single marble in the center. The electron would be a tiny speck whirling around the outer walls. Everything else, the vast volume of the stadium, is empty space. Your body, made of trillions of such atoms, is also mostly empty space. The reason you do not fall through the floor is not because atoms are solid, but because the electrons in your feet repel the electrons in the floor. The emptiness is filled with electric forces. The gold foil experiment is now considered one of the most beautiful experiments in the history of science. It was simple, cheap, and decisive. It used no complex electronics, no massive machinery, just a radioactive source, a sheet of gold, and a screen that glowed when alpha particles hit it. And yet it revealed the fundamental structure of matter. Rutherford's name is now remembered alongside Newton and Einstein. not because he was a genius of abstract theory, but because he knew how to ask nature a question and listen to the answer. Consider the courage it took to trust that result. 8,000 particles passed straight through for every one that bounced back. Rutherford could have dismissed the few bounces as anomalies, as experimental error. But he did not. He recognized that the rare events were the most important. That is a lesson that extends beyond physics. Sometimes the exceptions, the outliers, the things that do not fit the pattern, those are the clues that lead to deeper understanding. A small, unexpected observation, a few alpha particles bouncing back from a sheet of gold, overturned a model that had been accepted for decades. That is how science progresses, not by accumulating more of the same evidence, but by paying attention to the evidence that does not fit. As you rest here, you might think about something in your own life that does not fit your expectations. What might that outlier be trying to tell you? Protons, neutrons, and atomic structure. Rutherford had discovered the nucleus, but he did not yet know what the nucleus was made of. Soon after the gold foil experiment, he began firing alpha particles at various gases and observed that hydrogen nuclei were knocked out of the atoms. He realized that the hydrogen nucleus, which he called a proton, was a fundamental building block present in all atoms. The number of protons in an atom determines what element it is. A hydrogen atom has 1 proton. Helium has 2. Carbon has 6. Oxygen has 8. Gold has 79. This simple rule, the atomic number equals the number of protons, became the organizing principle of chemistry. It explained why elements behave the way they do. But there was a problem. The mass of an atom was consistently greater than the sum of its protons. For example, a helium atom has 2 protons, but its mass is about 4 times that of a hydrogen atom. That meant there must be something else inside the nucleus, something with mass but no electric charge. Rutherford suspected the existence of such a neutral particle, but he could not detect it. It was his student, James Chadwick, who finally proved its existence in 1932. Chadwick bombarded a thin sheet of beryllium with alpha particles and observed a mysterious radiation that was not deflected by electric or magnetic fields. This radiation knocked protons out of paraffin wax. Chadwick measured the mass of the new particle and found it was slightly heavier than a proton. He named it the neutron. The discovery of the neutron explained a long-standing mystery: isotopes. Isotopes are atoms of the same element that have different masses. For example, most carbon atoms have 6 protons and 6 neutrons, giving them a mass of 12. But some carbon atoms have 7 neutrons, that is carbon-13. Some have 8 neutrons, carbon-14, which is radioactive and used in archaeological dating. All of these are carbon because they have 6 protons. The number of neutrons can vary, but the chemical behavior is almost identical. Isotopes had been discovered earlier by Frederick Soddy, but their existence was puzzling until Chadwick's neutron explained them. The structure of the atom now seemed clear. A tiny, incredibly dense nucleus sits at the center, made of protons and neutrons bound together by the strong nuclear force. Surrounding the nucleus is a cloud of electrons, held by electromagnetic attraction. The electrons do not orbit like planets. They occupy probability clouds called orbitals. These orbitals come in different shapes and energy levels. The first shell can hold only 2 electrons. The second can hold 8. The third can hold 18. The arrangement of electrons in these shells determines how an atom behaves chemically. Atoms with a full outer shell are inert. They do not react. Atoms with one electron missing or one extra electron are highly reactive. They will bond with other atoms to achieve a stable configuration. The nucleus itself is a wonder. Protons with their positive charges should repel each other violently. The fact that they stay together in a tiny space is evidence of a force far stronger than electricity, the strong nuclear force. This force acts only at extremely short distances, but within the nucleus it is powerful enough to overcome the electromagnetic repulsion of the protons. When you split a large nucleus into smaller pieces, the strong force is disrupted and energy is released. That is nuclear fission. Alternatively, when you fuse small nuclei into larger ones, you also release energy. That is nuclear fusion, the process that powers the sun. One of the strangest properties of the neutron is that it has no charge. That means it can pass through most materials without interacting. A beam of neutrons can penetrate thick layers of lead, concrete, or steel. But when a neutron does happen to hit an atomic nucleus, it can cause that nucleus to split, releasing more neutrons and a tremendous amount of energy. That chain reaction is the basis of nuclear reactors and nuclear weapons. A particle that is invisible, silent, and almost impossible to detect holds the power to light entire cities or to destroy them. That is a strange and sobering thought. Why atoms are mostly empty space. You have heard the phrase before. Atoms are mostly empty space. But what does that actually mean for you, lying in your bed, feeling the solid mattress beneath you? The mattress feels solid. The pillow feels soft. The blanket feels warm. None of these sensations seem to come from emptiness. Yet the physical truth is that every atom in your body and every atom in the mattress is about 99.999% empty space. If you removed all the empty space from every atom in your body, you would be smaller than a grain of salt. But you would still weigh the same. All that mass would be crammed into a microscopic speck. To understand this emptiness, imagine blowing a single atom up to the size of a large concert hall. The nucleus would be a tiny marble sitting on the stage. The electrons would be specks of dust flying around the balconies. Everything else, the entire vast volume of the hall, would be empty. No walls, no seats, no air, just emptiness. That is the scale of an atom. The reason the concert hall feels solid is not because the atoms themselves are solid, but because the electrons at the edges of your atoms are pushing against the electrons at the edges of the mattress's atoms. You are not actually touching anything. You are hovering a tiny distance above every surface, separated by a gap of electric repulsion. This repulsion is incredibly strong. The electrons in your skin and the electrons in the bed are all negatively charged, and like charges repel. The closer they get, the stronger the repulsion. So they settle into a balance, close enough to feel pressure, but far enough apart that the repulsive force is exactly balanced by the weight of your body. That distance is measured in nanometers, billionths of a meter. You cannot feel the gap. Your nerves interpret the repulsion as solid contact, but the gap is always there. You never truly touch anything in the way that two billiard balls touch. You only experience the electromagnetic force keeping you separate. What about the emptiness inside the atom? Empty space is not truly empty. It is filled with quantum fields, with virtual particles popping in and out of existence, with electric and magnetic forces that extend throughout the volume. The electron is not a tiny sphere zipping around a fixed path. It is a cloud of probability. You cannot say exactly where the electron is at any given moment. You can only say where it is likely to be found if you look. That probability cloud occupies space. So the atom is empty in the sense that there is no solid material filling it, but it is full in the sense that forces and fields and quantum probabilities are present everywhere. The implications of this emptiness are profound and strange. The world you experience, the solidity of a table, the surface of a glass, the texture of a leaf, is an illusion created by your nervous system. Your senses evolved to detect the average behavior of trillions of atoms, not the underlying reality. What you call solid is actually a dynamic dance of electric forces across empty space. What you call still is actually atoms vibrating billions of times per second. What you call empty is actually filled with the ghostly presence of quantum fields. There is a kind of peace in this knowledge. The solid walls of your room, the roof above you, the ground below, all of it is mostly nothing. And yet that nothing holds you. It supports you. It keeps the cold out and the warmth in. You do not need to understand the quantum mechanics of the wall to trust that it will not collapse. The wall does its job whether you understand it or not. The same is true for your body. It is a temporary arrangement of mostly empty space, held together by forces you cannot see. And for tonight, that is enough. You do not need to solve the mystery. You only need to rest inside it. Maybe there is something comforting about being mostly empty space. It means you are not a solid, separate object isolated from the rest of the universe. You are a dynamic pattern, a temporary fluctuation, a place where forces meet and balance. The boundaries of your body are not as fixed as they seem. Every breath brings new atoms into your lungs. Every meal replaces old atoms with new ones. You are more like a flame than a rock, a shape that persists even as the material flows through it. That shape is you. And for this quiet moment, that shape is breathing gently, surrounded by mostly empty space, safe and still. The periodic table, organizing the universe. By the middle of the 19th century, chemists had discovered more than 60 different elements. Each one had its own name, its own properties, its own behavior. But the list was chaotic. There was no obvious order, no clear pattern. Some elements were shiny metals that conducted electricity. Others were dull non-metals that did not. Some reacted violently with water. Others did nothing at all. It felt like a random collection of things, not a coherent system. But slowly, patterns began to emerge from the chaos. Certain properties seemed to repeat every 8 elements when they were arranged by atomic weight. A Russian chemist named Dmitry Mendeleev saw the pattern clearly. In 1869, he published the first truly successful version of the periodic table. Mendeleev arranged the elements in rows and columns so that elements with similar properties fell into the same columns. The rows, called periods, contain elements with increasing atomic weight. The columns, called groups, contain elements with similar chemical behavior. The first group, the alkali metals, lithium, sodium, potassium, are all soft, shiny, highly reactive metals. The last group, the noble gases, helium, neon, argon, are all colorless, odorless, and almost completely unreactive. The transition metals in the middle, iron, copper, gold, are harder, conduct electricity, and often form colorful compounds. The pattern was not perfect, but it was undeniable. Nature was telling chemists that there was an underlying order. Mendeleev's genius was not just in seeing the pattern, it was in what he did with the gaps. In his table, there were places where an element seemed to be missing, where the pattern suggested that an element of a certain atomic weight should exist, but no such element was known. Mendeleev left an empty space. He even predicted the properties of those missing elements, their density, their melting point, the formulas of their compounds. When those elements were discovered later, gallium, scandium, germanium, their properties matched Mendeleev's predictions almost perfectly. That was a stunning victory. It showed that the periodic table was not just a convenient way to organize a list. It was a discovery about the deep structure of matter. The periodic table is now organized by atomic number, the number of protons, not atomic weight. That change came after Henry Moseley's work in 1913, which showed that atomic number was the fundamental property, but Mendeleev's basic insight that properties repeat periodically remains unchanged. The table has grown. When Mendeleev published his first version, there were 63 known elements. Today, there are 118. The newest elements do not occur in nature. They are synthesized in particle accelerators, existing for only fractions of a second before decaying. But even these fleeting, artificial elements have their place in the table. They fill the gaps at the bottom, completing the 7 rows. Why does the periodic table have such a regular shape? The answer lies in the electron shells. As you move from left to right across a period, the number of protons increases, and the number of electrons increases by the same amount. The electrons fill the shells in a specific order. The first shell fills with 2 electrons. That is the first period, with hydrogen and helium. The second shell fills with 8 electrons. That is the second period, from lithium to neon. The third shell fills with 8 electrons initially, then more later. That is the third period. The columns of the table correspond to elements with the same number of electrons in their outermost shell. That is why they behave similarly. Chemistry is, at its deepest level, the story of those outer electrons. The periodic table is one of the great achievements of the human mind. It is elegant, beautiful, and useful. A chemist can look at the table and predict the properties of an element they have never seen. An engineer can use the table to choose materials for a new device. A student can look at the table and see the entire universe of matter, from hydrogen to oganesson laid out in a single page. The table is not a finished product. New elements may still be discovered or synthesized, but the structure is complete. The pattern has held for more than 150 years. As you rest here, you might glance at the wall or the ceiling. The paint contains calcium carbonate. The metal fixtures contain iron, chromium, nickel. The air contains nitrogen, oxygen, argon. Every one of those elements has a place on the periodic table. Every one of them was forged in a star billions of years ago, and every one of them is, tonight, keeping you company in the dark. That is the quiet miracle of the periodic table. It is not just a chart. It is a family album of the universe. Dmitri Mendeleev and his brilliant pattern. In a small Russian university office, a bearded man sat surrounded by playing cards. But these were not ordinary cards. Each one held the name of an element, its atomic weight, and its chemical habits. The year was 1869, and Dmitri Mendeleev was trying to solve one of the most frustrating puzzles in science. 63 elements had been discovered, each with its own personality. Some were soft and explosive, others were hard and noble. Some bonded eagerly, others stood apart. There seemed to be no logic, no system. Mendeleev suspected otherwise. He believed that hidden beneath the chaos there was a pattern. He just had to find it. He spread the cards across his desk. He arranged them by atomic weight, lightest to heaviest. Then he watched. The properties jumped around. Lithium was a soft metal. Beryllium was harder. Boron was a non-metal. But then, after a while, something odd happened. Every eighth element, a similar property reappeared. Lithium, sodium, potassium, all light, all reactive, all forming the same kind of compounds. It was like a musical scale repeating an octave. Mendeleev called this the periodic law. He arranged the elements in rows so that the columns contained elements with matching behaviors. That was the birth of the periodic table. But the table did not fit perfectly. A few elements seemed out of place. Tellurium was heavier than iodine, but iodine clearly belonged in the same column as fluorine and chlorine. Mendeleev made a bold choice. He trusted the pattern more than the numbers. He swapped tellurium and iodine, placing iodine first. He predicted that the atomic weights must have been measured incorrectly. Later measurements proved him right. That trust in the pattern, that willingness to believe that nature is lawful even when the data seems contradictory, is what separates a great scientist from a good one. Even more striking were the gaps. In several places, the pattern demanded an element of a certain atomic weight, but no such element was known. Mendeleev left empty spaces. He did not just leave blanks. He predicted the properties of those missing elements. He said that an element between calcium and titanium would be found, and he named it Eka-boron. He described its density, its melting point, the formulas of its oxides and chlorides. When gallium was discovered a few years later, its properties matched his predictions almost exactly. The same happened with Eka aluminum, scandium, and Eka silicon, germanium. Each discovery was a quiet victory. Mendeleev did not have an easy life. He was the youngest of 14 children. His father went blind, and his mother walked hundreds of miles to get him into a university. He was often in trouble with the authorities for his liberal views. His work on the periodic table was submitted just before a deadline while he was ill. But he persisted. He believed that the elements were not a random collection. They were a family. His table showed how they were related. It was a map of matter. One evening, after 3 days without sleep, Mendeleev put his head on his desk and dreamed. In his dream, he saw the completed table. He woke up and drew it from memory. That dream may be legend, but it captures something true. Sometimes the answer comes when you stop forcing it. The mind needs rest. The pattern reveals itself in silence. The periodic table is still used today. It has grown from 63 elements to 118, but the structure is the same. Mendeleev's genius was not in having all the answers. It was in asking the right question. He asked, what if the elements are not isolated individuals, but parts of a single system? And that question, patiently pursued, changed chemistry forever. Why some elements behave similarly. Walk your finger down the first column of the periodic table. You start with hydrogen, then lithium, sodium, potassium, rubidium, cesium, francium. All of them are soft, shiny metals. All of them react with water to produce hydrogen gas. All of them form compounds with chlorine in the same 1-to-1 ratio. They are like members of the same family, different ages, different sizes, but the same habits. Why? The answer lies not in their nuclei, but in the electrons that orbit them. Every atom has a set of electron shells, like layers of an onion. The outermost shell is the one that matters for chemistry. It is called the valence shell. Elements in the same column have the same number of electrons in that outer shell. The first column elements all have one outer electron. That single electron is lonely. It wants to leave. The atom will give it away to almost anyone who will take it. When sodium meets chlorine, sodium's outer electron jumps to chlorine. That transfer creates an ionic bond. The sodium becomes a positive ion. Chlorine becomes negative. They snap together like magnets. The number of outer electrons determines how many bonds an atom can form. Carbon has 4 outer electrons. It can share them with up to 4 other atoms. That ability to form 4 bonds is why carbon can build long chains, rings, and complex structures. It is the backbone of every organic molecule, every protein, every piece of DNA. Without carbon's 4-arm grip, life as you know it would not exist. Now look at the last column, the noble gases. Helium has 2 outer electrons, but its shell is full. Neon, argon, krypton, xenon, radon. They all have 8 outer electrons, a complete shell. A full shell is stable. These atoms have no desire to gain, lose, or share electrons. They are the loners of the periodic table. They do not react. For decades, chemists thought they were completely inert. Then, in the 1960s, researchers forced xenon to form compounds, but only under extreme conditions. For most purposes, the noble gases just sit there, peaceful and unreactive. Between the extremes are the transition metals, iron, copper, zinc, and their relatives. Their outer electron shells are not simply full or empty. They have partial shells that can accommodate different numbers of electrons. That is why iron can exist with a +2 charge or a +3 charge. That is why copper can form blue compounds and green compounds. The transition metals are the chameleons of the periodic table. They change color, change charge, and catalyze reactions. Your blood is red because iron in your hemoglobins can switch between its 2 oxidation states. That switching carries oxygen from your lungs to your cells. Why do elements in the same group behave similarly? Because the number of outer electrons is the same. The inner electrons do not matter much for chemistry. They are tucked away, shielded by the outer shell. But the outer electrons, they are the face the atom shows to the world. They determine everything, how reactive the atom is, what kind of bonds it forms, what color its compounds are, whether it conducts electricity. The periodic table is, at its heart, a chart of outer electron configurations. Mendeleev did not know that, but he saw the pattern anyway. One quiet implication. If you understand the group, you understand the element. You do not need to memorize each one separately. You can learn the habits of the family, and that is what makes the periodic table so powerful. It is not a list, it is a key. Metals, non-metals, and everything between. A hammer strikes a piece of iron. The iron flattens. A hammer strikes a piece of sulfur. The sulfur shatters. These 2 materials live on opposite sides of the periodic table. Iron is a metal. Sulfur is a non-metal. The difference between them runs deep. Metals are shiny, malleable, ductile, and conductive. Non-metals are dull, brittle, and insulating. About 3/4 of the elements are metals. They occupy the left side and the middle of the table. The non-metals huddle in the upper right corner. Between them runs a diagonal line, the home of the metalloids. Pick up a copper wire, bend it. It does not break. That is ductility. Hammer a gold coin. It flattens into a thin leaf without crumbling. That is malleability. Heat one end of an iron rod. The other end soon becomes hot. That is thermal conductivity. Connect a battery to a piece of aluminum. Current flows. That is electrical conductivity. These properties all come from the way electrons behave in metals. The outer electrons are not tied to any single atom. They form a sea of mobile charge that flows freely. That sea allows the atoms to slide past each other without breaking, hence malleability. That sea carries heat and electricity, hence conductivity. Non-metals do not have that electron sea. Their electrons are held tightly in covalent bonds. When you hit a non-metal, the bonds break, and the material fractures. Sulfur, phosphorus, carbon, as diamond, all brittle. Non-metals do not conduct electricity well. Pure silicon, in its crystalline form, is a semiconductor. It conducts a little, but not as much as a metal. That is why silicon is useful for computer chips. You can control its conductivity by adding tiny amounts of other elements. That control is the basis of every transistor, every microchip, every digital device you own. The metalloids sit on the border. They are the border crossers. Silicon, germanium, arsenic, antimony, tellurium. They have properties of both worlds. They look like metals, shiny and grey, but they are brittle, like non-metals. Their conductivity is intermediate. That intermediate character is not a failure. It is a gift. Without metalloids, there would be no semiconductors, no computers, no smartphones, no solar panels. The digital age rests on the narrow strip of elements that refuse to pick a side. Consider mercury. It is a metal, but it is liquid at room temperature. That liquid nature comes from the way mercury's electrons are arranged. The outer electrons are held unusually tightly for a metal, so the atoms do not bond strongly to each other. They slide past like water molecules. Mercury was used in thermometers for centuries because it expands evenly with temperature. But mercury is also toxic. Its vapors damage the nervous system. Today, most thermometers use alcohol or digital sensors. At the other extreme, tungsten has the highest melting point of any metal. It remains solid until about 3,400 degrees Celsius. That is why tungsten filaments glow white hot in light bulbs without melting. Osmium is the densest naturally occurring element. A piece the size of a sugar cube weighs about 22.6 grams, more than twice as heavy as a sugar cube of lead. These extremes are not random. They follow the patterns of the periodic table. Metals on the left are soft and reactive. Metals in the middle are hard and dense. The transition metals show the widest range of properties. The boundary between metals and non-metals is not a sharp line drawn by nature. It is a convenience, a way to organize your thinking. Some elements near the boundary can be classified either way depending on the property you emphasize. That is fine. Classifications are tools, not truths. What matters is that the periodic table helps you predict how an element will behave. If you know it is a metal, you expect it to conduct electricity. If you know it is a non-metal, you expect it to be brittle. And if you know it is a metalloid, you expect it to be a semiconductor. Those expectations are almost always correct. The next time you pick up a fork, feel its coolness. That is heat being conducted away from your hand by the metal. The next time you see a diamond, notice its sparkle. That is light being bent by the rigid covalent bonds of carbon. The next time you turn on a computer, thank the metalloids. They made it possible. The periodic table is not just a chart in a classroom. It is a catalogue of the materials that build your world. The hidden patterns in the periodic table. Gaze at the periodic table from a distance. It looks like a grid, neat, orderly, predictable. But the grid hides deeper rhythms. Look closer, and you see that atomic size shrinks as you move from left to right. Then, when you drop to the next row, the size jumps back up. That pattern is not an accident. It comes from the way electrons fill the shells. Each new row adds a new shell, so the atoms get bigger. But within a row, the increasing positive charge pulls the electrons inward, making the atoms shrink again. This seesaw of size affects everything: reactivity, bond strength, melting points. Another hidden pattern is ionization energy, the force needed to rip an electron away from an atom. That force is weakest at the bottom left of the table. Cesium gives up its outer electron almost gladly. That is why cesium explodes on contact with water. The force is strongest at the top right. Helium holds its electron so tightly that it almost never reacts. Fluorine, just to the left of helium, also has a huge appetite for electrons. It will tear them from almost any other atom. That hunger makes fluorine the most reactive non-metal. It attacks glass, burns skin, and reacts with noble gases under the right conditions. Electronegativity is a cousin to ionization energy. It measures how strongly an atom pulls electrons when it is part of a compound. Fluorine is the king of electronegativity. It pulls electrons like a black hole. Cesium is the opposite. It barely pulls at all. The difference in electronegativity between two atoms tells you what kind of bond they will form. A large difference produces an ionic bond, electron transfer. A small difference produces a covalent bond, electron sharing. A medium difference produces a polar covalent bond, uneven sharing. Water is a polar covalent bond. That polarity is why water can dissolve salt and sugar, and why it beads up on a wax surface. The periodic table also hides clues about oxidation states. The charges atoms take when they form ions. The first group almost always forms +1 ions. Sodium becomes sodium +1. Potassium becomes potassium +1. The second group forms +2. Magnesium becomes magnesium +2. The seventh group forms -1. Chlorine becomes chloride -1. The sixth group forms -2. Oxygen becomes oxide -2. These patterns are so reliable that you can predict the formula of a compound just by looking at the group numbers. Calcium, group 2, and oxygen, group 6, make calcium oxide. Aluminum, group 3, and chlorine, group 7, make aluminum chloride. The table gives you the recipe without you having to memorize anything. One of the most subtle patterns is the diagonal relationship. Sometimes an element behaves more like the element below and to the right of it than like the element directly below it. Lithium, for example, has some properties in common with magnesium, not with sodium. Beryllium behaves like aluminum. Boron behaves like silicon. These diagonal relationships occur because the decrease in size from left to right is balanced by the increase in size from top to bottom. The result is that elements that are not in the same group can still be cousins. The noble gases were a late addition to the table. When they were discovered in the 1890s, their properties were so strange, complete inertness, that they did not fit anywhere. A new column had to be created. That column, group 18, sits at the far right. It is the finishing line of each period. Once the outer shell is full, the period ends. The next period starts with a new shell and a new alkali metal. That rhythm, fill, then jump, is the heartbeat of the periodic table. Understanding these hidden patterns turns the table from a static chart into a dynamic tool. You can look at an element you have never studied and estimate its size, its reactivity, the kind of bonds it will form, and the charge of its ions. That is not magic. It is pattern recognition. And pattern recognition is what science does best. Chemical bonds. Why atoms stick together. Without bonds, the universe would be a fog of lonely atoms. No molecules, no solids, no liquids, no you. Bonds are the forces that hold atoms together. They come in two main flavors, ionic and covalent. A third flavor, hydrogen bonding, is weaker, but just as important. Understanding these bonds is like learning the grammar of matter. Once you know the rules, you can read the sentences, the molecules that make up the world. An ionic bond forms between a metal and a non-metal. The metal gives up one or more electrons. The non-metal takes them. The metal becomes a positive ion. The non-metal becomes a negative ion. Opposite charges attract. That attraction is the ionic bond. Table salt is the classic example. Sodium gives an electron to chlorine. The resulting sodium ion and chloride ion cling together. They form a crystal, a repeating grid of alternating charges. That grid is why salt is hard and brittle. Hit it, and the grid can shift, bringing like charges together, which repel and split the crystal. Covalent bonds form between nonmetals. Instead of transferring electrons, the atoms share them. Each atom contributes one electron to the shared pair. That pair spends time around both nuclei, holding them together like a handshake. The simplest covalent bond is in hydrogen gas. Two hydrogen atoms sharing a single pair. Oxygen gas has a double bond. Two oxygen atoms sharing two pairs. Nitrogen gas has a triple bond, 3 shared pairs. Triple bonds are very strong. That strength explains why nitrogen gas is so unreactive, even though it makes up most of the air you breathe. Covalent bonds can be polar or non-polar. If the two atoms are identical, they share electrons equally. That is a non-polar bond, like in hydrogen gas or oxygen gas. If the atoms are different, the electrons may be pulled more toward one side. That creates a polar bond. One end slightly negative, the other slightly positive. Water is the champion of polar bonds. The oxygen pulls electrons away from the hydrogens, making the oxygen end negative and the hydrogen ends positive. That polarity is why water can dissolve so many substances. The positive end of a water molecule attracts negative ions. The negative end attracts positive ions. Water is a universal solvent because it is a polar molecule. Carbon is the master of covalent bonding. It has 4 outer electrons. It can form 4 bonds. That allows it to build long chains, branching trees, and closed rings. These carbon skeletons are the backbone of organic chemistry. They are also the backbone of life. Every protein, every carbohydrate, every fat, every piece of DNA is built from carbon atoms linked by covalent bonds. No other element can match carbon's versatility. That is why life on Earth is carbon-based. Hydrogen bonds are the third flavor. They form between a hydrogen atom, already covalently bonded to an electronegative atom like oxygen or nitrogen, and another electronegative atom nearby. Hydrogen bonds are about 1/10 as strong as covalent bonds, but they are ubiquitous. They hold the two strands of DNA together. They give water its high boiling point and its unusual density. Ice floats because hydrogen bonds push the molecules apart. They allow proteins to fold into the specific shapes that make them functional. Without hydrogen bonds, you would not have enzymes, antibodies, or cell membranes. Bonds are not permanent. They can break and form. A chemical reaction is just the breaking of old bonds and the making of new ones. The energy you use to move your muscles comes from breaking the bonds in sugar molecules and forming new bonds with oxygen. The warmth of your body comes from the same process, combustion, slowed down and controlled. The light of a candle comes from breaking the bonds in wax and forming bonds with oxygen. Every change you see, from rust to digestion to the fading of a photograph, is a story of bonds breaking and forming. Some bonds are strong. The covalent bonds in diamond are so strong that diamond is the hardest natural substance. Some bonds are weak. The forces between the molecules in a gas are so weak that the molecules barely notice each other. Between those extremes, there is a spectrum. The strength of a bond determines the melting point, the boiling point, the hardness, the reactivity. Tungsten has strong metallic bonds, so it melts at a very high temperature. Mercury has weak metallic bonds, so it is liquid at room temperature. All of these bonds, ionic, covalent, hydrogen, metallic, are electromagnetic in origin. The same force that makes your hair stand up on a dry day, that lights a lightning bolt, that holds electrons in orbit. That force also holds atoms together. It is the most versatile force in the universe. It builds crystals and clouds, bones and bread, stars and smartphones. And right now, in the quiet dark, it is holding you together. Ionic versus covalent bonds, explained to NTE. Gently. You have seen two people hold hands. Sometimes they grip tight, unwilling to let go. Other times they just touch fingertips, a light connection. Chemical bonds are similar. Some bonds are tight transfers. One atom gives an electron to another, and the resulting ions cling together like magnets. Those are ionic bonds. Other bonds are shared. Atoms hold electrons together, like two people carrying a heavy box between them. Those are covalent bonds. Both types keep matter from falling apart, but they do it in different ways. Picture a playground. A child has a ball. Another child wants it. The first child throws the ball to the second. Now the first child has no ball. The second has one. That is an ionic bond, a complete transfer. The child who lost the ball becomes a positive ion. The child who gained it becomes a negative ion. They are now opposite charges, and they feel drawn to each other. That attraction is the bond. In the world of atoms, sodium does this with chlorine. Sodium throws its outer electron to chlorine. The resulting ions, sodium plus and chloride minus, snap together. That is table salt. Now picture two children carrying a heavy box together. Neither lets go. They both grip the handles. The box belongs to both of them. That is a covalent bond, a shared pair of electrons. Neither atom loses its electron completely. Instead, both atoms contribute one electron, and the pair orbits around both nuclei. The bond holds because both atoms benefit from the arrangement. Hydrogen gas is the simplest example. Two hydrogen atoms each have one electron. They share them. Each hydrogen now feels like it has two electrons, a full shell. They are happy together. Which bond is stronger? It depends. Some covalent bonds, like the triple bond in nitrogen gas, are extremely strong. Some ionic bonds, like the one in salt, are also strong, but they break easily in water. Water molecules are polar. They have a positive end and a negative end. Those polar ends pull the sodium and chloride ions apart, dissolving the crystal. That is why salt dissolves in water. Covalent bonds in sugar also dissolve, but differently. The sugar molecules themselves remain intact. They just float away from each other. That is why sugar water tastes sweet. The sugar molecules are still there, just separated. Ionic compounds tend to form crystals. Think of a brick wall. Sodium ions and chloride ions alternate in a regular grid. Positive, negative, positive, negative. That alternating pattern is stable because opposites attract. If you hit the crystal, the layers can shift, bringing positive next to positive. They repel and the crystal shatters. That is why salt is brittle. Covalent compounds can be gases, like oxygen, liquids, like water, or soft solids, like wax. They do not form repeating ionic grids. Instead, each molecule is a separate unit, held together by internal covalent bonds, but only weakly attached to its neighbors. Metals use a third kind of bond, often called metallic bonding. Picture a crowd of people all tossing a beach ball around. The ball moves freely from person to person. In a metal, the outer electrons are not tied to any single atom. They form a sea of mobile charge. The positive metal ions sit in this sea, like raisins in pudding. The electron sea is why metals conduct electricity. The electrons can flow. It is also why metals are malleable. The ions can slide past each other without breaking the bond. The sea holds everything together. Real life is a mix. Your body contains ionic bonds in bones, in nerve signals, covalent bonds in proteins, in DNA, and metallic bonds in trace metals like iron in your blood. The bonds work together. They are not competing. They are cooperating. Your bones are hard because of ionic bonds between calcium and phosphate. Your muscles move because of covalent bonds breaking and forming in ATP. Your blood carries oxygen because of a metallic ion, iron, sitting inside a protein cage. You're a hybrid. Think of a house. Ionic bonds are the concrete foundation, rigid, strong, but able to crack under stress. Covalent bonds are the wooden frame, flexible, tough, able to bend without breaking. Metallic bonds are the electrical wiring, carrying energy from place to place. You need all three to build a life. Chemistry does not choose one bond type over another. It uses whatever works, and what works is often a combination. The next time you taste salt, you are feeling ionic bonds breaking on your tongue. The next time you drink water, you are swallowing covalent molecules. The next time you turn on a light, you are using metallic bonds to carry current. These bonds are not abstract concepts. They are the architecture of your world, and they are all around you, even in the dark. Why water is such a special molecule. A glass of water sits on your nightstand, ordinary, transparent, tasteless. But that water is one of the strangest substances in the universe. It expands when it freezes. Almost nothing else does. It has an unusually high boiling point for such a small molecule. It dissolves more substances than any other liquid. It climbs up narrow tubes against gravity. It holds heat better than most liquids, which is why oceans moderate the climate. All of these weird properties come from one thing: the shape of the water molecule and the way water molecules stick to each other. A water molecule is bent. Two hydrogen atoms attach to one oxygen at an angle of about 104.5 degrees. That bend is not a trivial detail. If water were straight, it would be a gas at room temperature. Life would not exist. The bend creates a polar molecule. One end, the oxygen side, has a slight negative charge, and the hydrogen ends have slight positive charges. This polarity is like a tiny magnet. The negative end of one water molecule attracts the positive end of another. That attraction is called a hydrogen bond. Hydrogen bonds are weak, about 1/10 the strength of a covalent bond, but there are many of them. In liquid water, each molecule forms hydrogen bonds with several neighbors. These bonds are constantly breaking and reforming, billions of times per second. That dynamic network gives water its fluidity. It also gives water its high boiling point. To turn water into steam, you have to break all those hydrogen bonds. That takes energy. That is why water boils at 100 degrees Celsius, while a similar sized molecule like hydrogen sulfide boils at -60 degrees. Ice is even stranger. In liquid water, molecules are close together, constantly rearranging. As water freezes, the molecules lock into a crystalline lattice held together by hydrogen bonds. That lattice has more empty space than the liquid arrangement, so ice is less dense than water. That is why ice floats. If ice sank, lakes would freeze from the bottom up, killing fish and other life. But ice floats, forming an insulating layer on top. The water below stays liquid. Life survives the winter because water expands when it freezes. Water climbs up narrow tubes, a phenomenon called capillary action. This happens because water molecules are more attracted to the walls of a narrow tube, if the walls are polar like glass, than they are to each other. The water spreads out, pulling itself upward. Trees use capillary action to draw water from roots to leaves. So do paper towels, paintbrushes, and the ink in a fountain pen. Without water's polarity, no tree would grow taller than a few feet. Water is called the universal solvent because it dissolves so many substances. The polar ends of water molecules pull ions apart, like salt. The hydrogen ends also interact with polar molecules like sugar. That is why you can make tea, coffee, soup, and almost every drink. Water carries nutrients into your cells and wastes out. Your blood is about 90% water. Your brain is about 75% water. You are mostly water, shaped by water's strange bent molecules. One more oddity. Water has a very high specific heat. That means it takes a lot of energy to raise its temperature. Oceans absorb huge amounts of solar energy without boiling. That stabilizes the climate. Land heats up and cools down quickly. Water moderates the extremes. That is why coastal areas have milder weather than deserts. Your own body uses water to regulate temperature. You sweat. The sweat evaporates, taking heat with it. Evaporative cooling works because water molecules need energy to break free from their hydrogen bonds. That energy comes from your skin. Water's weirdness is not a coincidence. It is the result of quantum mechanics and molecular geometry. The oxygen atom is electronegative. It pulls electrons toward itself. The two hydrogens are not opposite each other. They are bent. That bend creates a permanent dipole. The dipole creates hydrogen bonds. The hydrogen bonds create all the strange properties. Change the bend by a few degrees, and water becomes a completely different substance, one that might not support life. The universe gave you a molecule bent at just the right angle. The glass on your nightstand is full of millions of trillions of molecules, each one bent, each one hydrogen bonded to its neighbors, each one dancing. And you, like all living things, are a container for that dance. Drink, sweat, float. Water is not just a substance, it is the medium of life. The chemistry of air around you. You cannot see it, you cannot taste it, but you feel it when it moves. A breeze, a draft, a sigh. Air is the invisible ocean in which you live. It has weight, pressure, and composition. It is not empty. It is a mixture of gases, each with its own personality. About 78% of the air is nitrogen. About 21% is oxygen. The remaining 1% is argon, carbon dioxide, neon, helium, methane, krypton, hydrogen, and water vapor. These gases are not just floating around. They react, they cycle, they sustain you. Nitrogen is the quiet giant. It makes up most of the air, but it is almost completely unreactive under normal conditions. The triple bond between its two atoms is one of the strongest in chemistry. Breaking that bond requires enormous energy. That is why nitrogen gas does not burn and does not support combustion. It just sits there, diluting the oxygen, keeping fires from being too intense. But living things need nitrogen for proteins and DNA. Plants cannot pull it from the air. They depend on bacteria that can break the triple bond, a process called nitrogen fixation. Those bacteria live in the roots of beans, clover, and other legumes. Without them, the soil would be barren. Oxygen is the fire starter. It is reactive. It combines with almost everything. When it combines rapidly, you get fire. When it combines slowly, you get rust or decay or respiration. Your body uses oxygen to burn the fuel from your food. That slow combustion releases energy, keeping you warm and powering your muscles. Every breath you take brings oxygen into your lungs. From there, it diffuses into your blood, binds to iron in hemoglobin, and travels to every cell. Without oxygen, you would last about 3 minutes. Carbon dioxide is the exhale. You breathe it out. Plants breathe it in. They use carbon dioxide, water, and sunlight to make sugar and oxygen. That process, photosynthesis, is the reverse of respiration. It stores energy from the sun in chemical bonds. When you eat plants or animals that ate plants, you release that energy. Carbon dioxide is also a greenhouse gas. It traps heat in the atmosphere. Without it, the Earth would be a frozen ball. Too much of it, and the planet overheats. The balance is delicate. Argon is the noble gas in your air. It makes up almost 1% of the atmosphere. It does nothing. It does not react. It does not burn. It does not support life. It is just there, an inert leftover from the formation of the Earth. That inertness is useful. Argon is used to shield welding arcs from oxygen. It is used in light bulbs to keep the filament from burning. It is used in double-pane windows for insulation. A gas that does nothing can do a lot. Water vapor varies from near zero to about 4% of the air. It is the invisible humidity. When it condenses, it forms clouds, fog, rain, snow. The amount of water vapor affects how hot or cold you feel. Humid air feels hotter because sweat does not evaporate easily. Dry air feels cooler because evaporation happens quickly. Water vapor is also a greenhouse gas. more powerful than carbon dioxide on a molecule-for-molecule basis. But it condenses out of the air, so its concentration is controlled by temperature. The air also contains tiny particles: dust, pollen, spores, smoke, salt crystals from the ocean. These particles are called aerosols. They are not gases. They float. They can trigger allergies. They can see clouds. Water vapor condenses around them. Without aerosols, clouds would not form. Without clouds, no rain. Aerosols also scatter sunlight, making the sky blue. The blue color comes from the particles scattering short wavelength light more than long wavelength light. That is why the sky is blue and the sunset is red. The air around you is not static. It moves. High-pressure systems push air downward, clearing skies. Low-pressure systems pull air upward, creating storms. The wind that rustles your curtains is air flowing from high to low pressure. That flow is driven by the sun, which heats the equator more than the poles. The warm air rises, cool air sinks, and the planet spins, creating the weather patterns you see on the news. You're breathing that air right now. Each breath contains about 10 sextillion molecules of nitrogen, 2 sextillion molecules of oxygen, and smaller amounts of the others. Some of those molecules have been around since the dinosaurs. Some were exhaled by a tree yesterday. Some came from a volcano, a forest fire, a whale's breath. Air is the most shared substance on Earth. You breathe what others exhaled. The atmosphere is a communal lung, and tonight it is holding you gently. Everyday reactions happening constantly. While you sleep, the world around you is reacting, not in dramatic, explosive ways, but quietly, constantly. Molecules are breaking and forming. The iron in a nail is slowly combining with oxygen, rusting. The copper on a penny is reacting with air and moisture, tarnishing. The silver in a necklace is reacting with sulfur from your skin, darkening. These are chemical reactions. They are not laboratory events. They are the background hum of everyday life. Open your refrigerator. The smell you notice when you open it is a chemical reaction. Food spoils because bacteria and enzymes break down complex molecules into smaller, smellier ones. The sour smell of milk comes from lactic acid. The rotten smell of meat comes from putrescine and cadaverine. These are not foreign substances. They are your food returning to simpler compounds, a natural process of decay that recycles atoms back into the ecosystem. You call it spoilage. Nature calls it digestion. Cut an apple and leave it on the counter. Within minutes, the white flesh turns brown. That is oxidation. Enzymes in the apple react with oxygen to form melanin, the same pigment that darkens human skin in the sun. Lemon juice prevents browning because it lowers the pH, interfering with the enzyme. That is chemistry you can see, taste, and prevent. Every cook knows this trick. They may not call it enzyme inhibition, but they are doing chemistry. Light a match. The red tip contains phosphorus and sulfur. The friction generates heat, which triggers a reaction between the potassium chlorate in the match head and the phosphorus. That reaction ignites the wood. The wood then reacts with oxygen in the air, producing carbon dioxide, water vapor, and heat. The heat sustains the flame. That is combustion, the same reaction that happens in a car engine, a gas stove, a campfire. A match is a tiny, controlled explosion. Your own body is a reactor. You digest food using acids and enzymes. You convert sugar into energy through a series of reactions called cellular respiration. You build proteins from amino acids. You repair damage using antioxidants. These reactions happen billions of times per second in every cell. You do not feel them, you do not control them, but they keep you alive. Your body temperature, about 37 degrees Celsius, is the result of thousands of exothermic reactions, reactions that release heat. Soap cleans because of a chemical reaction. Soap molecules have two ends. One end loves water. The other end loves oil and grease. The oil-loving end grabs onto dirt. The water-loving end lets the whole thing be rinsed away. That is not just mechanical scrubbing. It is molecular chemistry. Without that dual nature, soap would just spread grease around. Instead, it lifts grease off your skin and sends it down the drain. Baking a cake involves multiple reactions. Baking soda, sodium bicarbonate, reacts with acid, buttermilk, vinegar, or cream of tartar to produce carbon dioxide gas. That gas forms bubbles, making the cake rise. Heat causes proteins in eggs to denature, to unfold and link together, giving the cake structure. Sugar caramelizes, turning brown and producing hundreds of new flavor compounds. A cake is not just mixed ingredients. It is transformed by heat and chemistry into something new. Even the fading of your blue jeans is chemistry. The dye molecules in denim are held to the fabric by weak bonds. Washing, sunlight, and friction break those bonds. The dye molecules detach and wash away. The blue becomes lighter. That is not damage. That is wear. A slow, gentle reaction that tells the story of the garment's life. You do not need a laboratory to see chemistry. You need only look around. The rust on a bike chain, the tarnish on a spoon, the browning of a banana, the rising of bread dough, all reactions. Some are fast, like a match igniting. Some are slow, like a statue eroding. But all are governed by the same principles. Atoms rearrange. Energy flows. Matter transforms. And you, lying in the dark, are also transforming. Your cells are repairing. Your brain is consolidating memories. Your liver is filtering blood. All of that is chemistry. You are not separate from the reactions. You are the temporary result of them. A quiet, complex, ongoing reaction. Still happening, still holding together, still breathing in the night. Acids and bases in daily life. You have tasted sour things. Lemons, vinegar, yogurt. You have tasted bitter things. Coffee, dark chocolate, baking soda. That sourness is the taste of acids. That bitterness is often the taste of bases. Acids and bases are chemical opposites. They neutralize each other. When you mix an acid and a base, they react to form water and a salt. That reaction is one of the most common in chemistry, and it happens all around you every day. What makes an acid? An acid is a substance that donates hydrogen ions, protons, when dissolved in water. Lemon juice contains citric acid. Vinegar contains acetic acid. Your stomach contains hydrochloric acid, strong enough to dissolve metal, but diluted and protected by a mucus lining. When you taste sourness, your tongue is detecting those hydrogen ions. The more hydrogen ions, the stronger the acid, and the more sour the taste. What makes a base? A base accepts hydrogen ions. Baking soda is a base. Soap is a base. Bleach is a base. Many bases feel slippery to the touch. That slipperiness comes from the base reacting with the oils on your skin, turning them into soap. Bases taste bitter, but you should not taste most bases. Many are toxic. The bitterness of coffee comes partly from basic compounds. The bitterness of chocolate comes from theobromine, which is also a base. When an acid and a base meet, they neutralize each other. The hydrogen ions from the acid combine with the hydroxide ions from the base to form water. The remaining ions form a salt. For example, hydrochloric acid in your stomach and sodium hydroxide, a strong base, react to make water and sodium chloride, table salt. That is a clean, simple reaction. The acid loses its sourness. The base loses its bitterness. They become neutral. Your body uses acid-base chemistry constantly. Your stomach is acidic to digest food. Your blood must remain slightly basic, pH about 7.4. If your blood becomes too acidic or too basic, you get sick. Your lungs and kidneys work constantly to maintain that balance. You breathe out carbon dioxide, which is an acid. You excrete acids and bases in your urine. Every time you exercise, your muscles produce lactic acid, which your body must buffer. That burning feeling in your muscles is acidity. The recovery is neutralization. The pH scale measures how acidic or basic a solution is. It runs from 0 to 14. 7 is neutral. Below 7 is acidic. Above 7 is basic. Lemon juice has a pH of about 2. Battery acid is 0. Oven cleaner is about 13. Bleach is 12. Each step on the pH scale is a factor of 10. A pH of 3 is 10 times more acidic than pH 4. A pH of 2 is 100 times more acidic than pH 4. That is why a small change in pH can have a large effect. Acids and bases are used in countless products. You brush your teeth with a base, fluoride is basic, to neutralize the acids produced by bacteria in your mouth. Those acids dissolve tooth enamel. The base in toothpaste helps prevent cavities. You clean your oven with a strong base, sodium hydroxide, that reacts with burnt grease, turning it into soap that washes away. You unclog a drain with a base that dissolves hair. You add baking soda to a pool to raise the pH. You add vinegar to a cake to react with baking soda, producing bubbles that make the cake rise. Some acids are dangerous. Hydrofluoric acid can dissolve glass. Sulfuric acid can burn skin. Some bases are dangerous too. Sodium hydroxide can cause severe burns. But the same chemistry that can hurt you can also help you. The acid in your stomach does not hurt you because your stomach lining is protected. The base in soap does not hurt you because it is diluted. Danger is a matter of concentration and context. The next time you squeeze a lemon, you are holding an acid. The next time you sprinkle baking soda, you are holding a base. Mix them, and you get a fizz, carbon dioxide gas, water, and a salt. That fizz is neutralization happening in front of your eyes. It is safe, it is fun, and it is chemistry. As you close your eyes, think about the balance in your own body, the constant dance between acid and base, between sour and bitter. That balance is delicate, but it is robust. Your body has been maintaining it since the day you were born. And tonight, while you sleep, it will continue, quietly, perfectly, automatically. The acids and bases in your blood will stay in harmony. What pH really means. You have seen pH written on shampoo bottles, pool test strips, and soil kits. But what does it actually mean? The letters stand for potential of hydrogen, a measure of how many hydrogen ions are floating in a solution. The scale runs from 0 to 14. 7 is neutral. Pure water is 7. Below 7 means more hydrogen ions, acidic. Above 7 means fewer ions, basic or alkaline. Each step on the pH scale is a factor of 10. A solution at pH 5 has 10 times more hydrogen ions than one at pH 6. A solution at pH 4 has 100 times more than pH 6. Think of a crowd. At low pH, hydrogen ions are packed tight, like a sold-out concert. They bounce around, reacting with anything they touch. That is why strong acids are corrosive. Those ions attack molecules, breaking bonds. At high pH, hydrogen ions are scarce. Instead, hydroxide ions dominate. They are also reactive. A strong base can burn skin just as badly as a strong acid. The crowd at high pH is different, but just as energetic. Your stomach is pH 1.5 to 3.5, a mosh pit of hydrogen ions. That acidity kills most bacteria and starts breaking down proteins. Your stomach lining regenerates quickly because the acid would digest it otherwise. Your blood must stay between pH 7.35 and 7.45. If it drops below 7.35, you have acidosis. You feel tired, confused, short of breath. If it rises above 7.45, you have alkalosis, causing muscle twitching, nausea, or tingling. Your body has 3 systems to keep pH stable: buffers, respiration, and the kidneys. Buffers are like sponges. They soak up excess hydrogen ions or release them when needed. The most important buffer in your blood is bicarbonate. When your blood becomes too acidic, bicarbonate grabs hydrogen ions to form carbonic acid, which turns into carbon dioxide and water. You breathe out the carbon dioxide. When your blood becomes too basic, carbonic acid releases hydrogen ions. This constant give and take keeps you alive. Without buffers, a single glass of lemon juice could kill you. Rainwater is slightly acidic, pH about 5.6, because it absorbs carbon dioxide from the air. But when rain absorbs sulfur dioxide and nitrogen oxides from burning fossil fuels, it becomes much more acidic, pH 4 or lower. Acid rain damages forests, leaches toxic metals, and eats away stone buildings. The same acidity that helps your stomach digest food can destroy a marble statue over years. Soil pH matters to gardeners. Blueberries like acidic soil, pH 4 to 5. Potatoes prefer slightly acidic, pH 5 to 6. Asparagus likes neutral to slightly basic, pH 6.5 to 7.5. Lavender thrives in alkaline soil, pH 7 to 8. The pH affects which nutrients are available to roots. In acidic soil, aluminum can poison plants. In alkaline soil, iron becomes insoluble, and plants turn yellow. Gardeners add lime to raise pH or sulfur to lower it. They are doing acid-base chemistry in the dirt. Your skin has a natural pH of about 4.5 to 5.5, the acid mantle. It protects you from bacteria, fungi, and viruses. Many microbes cannot survive in acidic conditions. Soap is basic, pH 9 to 10. That is why soap can disrupt your skin's acid mantle. Some people use pH-balanced cleansers to avoid stripping that protective layer. Your hair is also slightly acidic. Hair products often adjust pH to smooth the cuticle or open it for color treatment. The food you eat changes your urine pH, but not your blood pH. Your body tightly controls blood pH regardless of diet. That is why alkaline diets have little effect on health, except through the nutrients they provide. Your urine can vary from pH 4.5 to 8.0, depending on what you ate. That variation is normal. It means your kidneys are doing their job. Even the ocean has a pH. It is slightly basic. about 8.1. But as carbon dioxide levels rise, the ocean absorbs more CO2, forming carbonic acid, lowering the pH. This is ocean acidification. It makes it harder for shellfish and corals to build their calcium carbonate shells. A change from pH 8.1 to 8.0 sounds tiny, but because the scale is logarithmic, it is a 26% increase in acidity. That change is already harming marine life. The pH scale was invented by a Danish chemist named Søren Sørensen in 1909. He worked at the Carlsberg laboratory, originally a research lab for brewing. He needed a way to measure acidity in beer. Production depends on precise pH. Too acidic, and the fermentation goes wrong. Too basic, and the beer tastes soapy. Sørensen's scale became standard not just for beer, but for all of chemistry, medicine, and biology. A brewer gave the world a way to measure hydrogen ions. Why some reactions release heat? Strike a match. A tiny flame appears releasing heat. Pour vinegar on baking soda. The mixture fizzes and feels cold. Why does one reaction get hot and the other get cold? The answer lies in the bonds. Every chemical bond stores energy. Breaking bonds requires energy. Forming bonds releases energy. The net difference between the energy needed to break bonds and the energy released from forming new bonds determines whether a reaction heats up or cools down. An exothermic reaction releases heat. The energy released from forming new bonds is greater than the energy absorbed to break the old bonds. Combustion, burning, is exothermic. The bonds in wax, long carbon-hydrogen chains, break, and the atoms recombine with oxygen to form carbon dioxide and water. The new bonds are stronger and more stable than the old ones. The extra energy escapes as heat and light. That is why a candle warms a room. An endothermic reaction absorbs heat. The energy needed to break bonds is greater than the energy released from forming new ones. The reaction pulls heat from its surroundings. The vinegar and baking soda reaction is endothermic. The bonds in acetic acid and sodium bicarbonate break, forming carbon dioxide, water, and sodium acetate. The process draws heat from the mixture, making it feel cool to the touch. Some instant coal packs use a similar reaction, ammonium nitrate dissolving in water. You squeeze the pack, break it in a bag, and the salt dissolves, absorbing heat and numbing the injury. Your body uses both types. The digestion of food is exothermic overall. You release heat, which maintains your body temperature. But specific steps in digestion can be endothermic, requiring energy input. Your body manages these trade-offs with enzymes and energy carriers like ATP. When you exercise, your muscles convert stored energy into heat. That is why you feel warm after running. When you shiver, your muscles contract rapidly, producing heat through exothermic reactions. Shivering is your body's furnace turning on. Photosynthesis is endothermic. Plants absorb sunlight, energy, and use it to break the bonds in carbon dioxide and water, forming glucose and oxygen. The energy from the sun is stored in the chemical bonds of sugar. When you eat that sugar, your body breaks the bonds and releases the stored energy. Photosynthesis stores energy. Respiration releases it. They are reverse reactions, one endothermic, the other exothermic. The heat of a reaction depends on the substances involved. Some reactions are violently exothermic. Thermite, aluminum and iron oxide, releases so much heat that it melts iron. It is used to weld railroad tracks. Some reactions are gently exothermic. The setting of concrete releases heat slowly over days. That is why large concrete structures can crack if cooled too quickly. The internal heat expands the material. Endothermic reactions are usually milder, but some can be dramatic. The reaction between barium hydroxide and ammonium thiocyanate absorbs so much heat that it freezes water droplets on the container. You can watch a flask frost over in seconds. The difference between exothermic and endothermic is not about good or bad. Both happen naturally. Both are essential. An exothermic reaction powers your car, your stove, your body. An endothermic reaction makes instant ice packs, cooks food, absorbing heat from the oven, and allows plants to grow. Without endothermic reactions, you could not cook an egg. Without exothermic reactions, you could not stay warm. You can feel these differences in everyday life. Touch a metal spoon left in hot soup. The spoon is hot because it absorbed heat from the soup. That is not a chemical reaction, but the same principle of energy transfer. Touch a metal spoon left in ice cream. It feels cold because heat flows from your hand into the spoon. Reactions that release heat are like the hot soup. Reactions that absorb heat are like the ice cream. They are not good or evil. They just are. Energy and chemistry, a quiet connection. Energy is not a thing. It is a relationship. It is the capacity to do work, to cause change, to move something. In chemistry, energy lives inside bonds. It hides in the spaces between atoms. When bonds break, that energy is set free. When bonds form, energy is stored. Chemistry is the art of moving energy from one place to another, one form to another. The food you eat contains chemical energy. Your body turns that energy into motion, heat, and new tissue. The gasoline in a car contains chemical energy. The engine turns that energy into motion and heat. A battery contains chemical energy. A wire turns that energy into light, sound, or motion. There are many forms of energy. Thermal energy is heat, the random motion of molecules. Kinetic energy is motion, a thrown ball, a flowing river. Potential energy is stored energy, a raised weight, a stretched rubber band. Chemical energy is potential energy stored in bonds. When you digest sugar, you convert chemical energy into thermal energy and kinetic energy. That is why you feel warm after a meal, and why you can walk. The energy did not disappear. It changed form. The first law of thermodynamics says, energy cannot be created or destroyed. It can only change form. That is the same rule as conservation of mass, but for energy. Every chemical reaction obeys this law. If you measure the heat released by a burning candle and add the energy stored in the products, it equals the energy stored in the starting materials. Nothing is lost. That is why perpetual motion machines cannot work. You cannot get more energy out of a reaction than you put in. You can only transform. Activation energy is the hill you must climb before a reaction starts. Many reactions need a push. A mixture of hydrogen and oxygen gases can sit forever without reacting. But a spark provides activation energy. The spark breaks a few bonds, releasing heat, which breaks more bonds, and the reaction becomes self-sustaining. That is why fuel needs a spark, or a flame, or a hot surface. The activation energy is the price of admission. Once the reaction is running, it may release enough heat to keep itself going. But it needs that first push. Catalysts lower activation energy. They do not change the final outcome, but they make the reaction easier. Your body uses enzymes, biological catalysts, to run thousands of reactions at body temperature. Without enzymes, those reactions would require high heat that would kill you. A catalase enzyme in your cells breaks down hydrogen peroxide, a toxic waste product, into water and oxygen. It does it 1,000,000 times faster than the reaction would happen on its own. That is why you can pour hydrogen peroxide on a cut and see bubbles. The enzyme in your blood is catalyzing the reaction. Energy flows. It flows from the sun to plants as light, from plants to animals as food, from animals to the soil as waste, from the soil back to the air as decomposed gases. That flow is not random. It follows the laws of thermodynamics. Energy tends to spread out. It goes from concentrated to diffuse. A hot object cools because its thermal energy spreads to the cooler surroundings. A sugar molecule breaks down because its chemical energy spreads into heat and motion. The universe is slowly moving toward a state where all energy is evenly spread, maximum entropy. That end state is heat death. But it is billions of years away. For now, energy flows in patterns that allow life to exist. Your own body is an energy transformer. You eat about 2,000 calories a day. That chemical energy is roughly equivalent to the energy in a handful of batteries. Your body uses that energy to pump blood, to fire neurons, to build new cells, to maintain temperature. About 60% of the energy from food becomes heat. That is why you are warm. The rest becomes work. Breathing, thinking, moving. Even when you sleep, your body uses energy. Your brain alone consumes about 20% of your resting energy. Dreaming is not free. The quiet connection between energy and chemistry is this. Every bond, every reaction, every breath is a transaction. You give energy to break a bond. You receive energy when a bond forms. The currency is invisible, but the accounts balance. Nothing is wasted. That is why a candle can heat a room, and why your body can warm your bed. The energy was always there, stored in bonds, waiting to be released. And tonight, as you rest, your body is still trading energy, slowly, gently, keeping the transaction going until morning. The speed of reactions, chemical kinetics. Some reactions are instant. A firecracker explodes in milliseconds. Some are glacial. A diamond turns into graphite over billions of years. Why the difference? The answer is kinetics, the study of reaction rates. Kinetics asks, how fast do reactants turn into products? And what factors speed up or slow down that transformation? The same principles that govern a wildfire also govern the rusting of a nail. They just operate on different timescales. The most important factor is concentration. More molecules in the same space means more collisions. More collisions mean more chances for bonds to break and form. That is why a spark in a pure oxygen environment is more intense than in air. Oxygen concentration is higher. That is why a campfire burns faster if you fan it. You are bringing more oxygen to the fuel. Your lungs work the same way. Deep breaths increase oxygen concentration in your blood, giving your cells more fuel for energy. Temperature is the second factor. Higher temperature means molecules move faster. Faster molecules collide more often and with more energy. A reaction that takes hours at room temperature may take seconds in an oven. That is why cooking speeds up the breakdown of food. That is why refrigerators slow down spoilage. Lower temperature means slower reactions. Every 10 degrees Celsius increase roughly doubles the reaction rate. A rule of thumb. Food in a warm kitchen spoils twice as fast as in a cool pantry. Surface area matters enormously. A whole log burns slowly because only the outer surface touches oxygen. But wood chips or sawdust have enormous surface area. They can ignite almost explosively. That is why grain silos sometimes explode. Fine dust has so much surface area that a tiny spark sets off a fireball. It is also why your digestive system breaks down food mechanically. Chewing increases surface area, allowing enzymes to work faster. A pill swallowed whole would take days to dissolve. Ground into powder, it dissolves in minutes. Catalysts speed reactions without being consumed. They lower the activation energy, the hill that reactants must climb. A tiny amount of catalyst can transform a reaction speed. Your body's enzymes are catalysts. One enzyme molecule can process thousands of substrate molecules per second. Industrial catalysts are used to make gasoline, plastics, and fertilizers. The catalytic converter in your car uses platinum and palladium to speed up the breakdown of pollutants. Without catalysts, many essential reactions would be uselessly slow. Inhibitors slow reactions. They are the opposite of catalysts. Some inhibitors work by binding to catalysts and blocking them. Others absorb reactive intermediates. Preservatives in food are inhibitors. They slow the reactions that cause spoilage. Antioxidants are inhibitors that slow the reaction of oxygen with food or with your cells. Vitamin E, vitamin C, and other antioxidants protect your body from damage by free radicals, highly reactive molecules that can harm DNA and cell membranes. Reaction rates can be measured. Chemists use spectrophotometers, pressure gauges, thermometers, and other tools to track how fast reactants disappear and products appear. The data often fit simple mathematical equations, but you do not need equations to understand the principles. A cold soda stays fizzy longer because the reaction that releases carbon dioxide is slower at low temperatures. A hot soda goes flat quickly. That is kinetics. A whole potato takes forever to bake. Cut it into small pieces and it cooks in minutes. That is kinetics. A rusty nail sits in the rain for years. The same nail, ground into powder, would rust in seconds. That is kinetics. Biological systems use kinetics to regulate themselves. Enzymes are turned on and off, sped up and slowed down, to control the flow of energy and materials. Your body knows when to digest, when to store fat, when to build muscle. It does this by controlling reaction rates. If your metabolism is fast, you burn energy quickly. If it is slow, you conserve energy. Both are healthy, depending on the context. The speed of a reaction is not about good or bad. It is about fitness. A fast reaction can be useful, a fire for warmth, or dangerous, an explosion. A slow reaction can be useful, a rust-proof coating, or frustrating spoiled food. Kinetics gives you a knob to turn. Heat it, cool it, concentrate it, dilute it, add a catalyst, add an inhibitor. You are always turning those knobs, even without knowing it. You adjust the flame under a pan. You put leftovers in the fridge. You add lemon juice to slow the browning of an apple. You are a kineticist, practicing chemistry in your kitchen. Catalysts, speeding things up without changing. A catalyst is a kind of chemical helper. It stands on the sidelines, never joining the game, but making the game possible. A catalyst speeds up a chemical reaction without being consumed. It can be used over and over. A tiny amount of catalyst can transform a reaction that would take years into one that takes seconds. Without catalysts, life would be impossible. Your body would be a bag of slow, useless chemicals. the industrial world would collapse. Catalysts are the silent enablers of modern chemistry. Enzymes are biological catalysts. They are proteins folded into specific shapes that match the molecules they work on. Think of a lock and key. The enzyme has a pocket, the active site, that fits only one type of molecule, the substrate. When the substrate enters the pocket, the enzyme stresses certain bonds, making them easier to break. The reaction happens millions of times faster than without the enzyme. Then the product leaves, and the enzyme is ready for another substrate. One enzyme molecule can process thousands of substrate molecules per second. The enzyme catalase is a classic example. Hydrogen peroxide is a toxic byproduct of metabolism. It needs to be broken down into water and oxygen. Without catalase, this reaction would take years. With catalase, it happens in milliseconds. That is why hydrogen peroxide bubbles when you pour it on a cut. The catalase in your blood is doing its job. Another enzyme, lactase, breaks down lactose, the sugar in milk. People who lack lactase are lactose intolerant. They cannot digest milk because the reaction is too slow. Industrial catalysts are often metals. Platinum, palladium, nickel, and iron are common. The Haber process uses an iron catalyst to combine nitrogen and hydrogen into ammonia, the basis of most fertilizers. Before this process, farmers relied on natural sources of nitrogen like manure and guano. The Haber process, developed in the early 20th century, doubled the world's food production. It also feeds half the people alive today. The iron catalyst is not consumed. It sits in the reactor year after year, doing its job. Catalytic converters in cars use platinum, palladium, and rhodium to convert toxic exhaust gases into less harmful ones. Carbon monoxide becomes carbon dioxide. Nitrogen oxides become nitrogen and oxygen. Unburned hydrocarbons become carbon dioxide and water. The catalysts are coated onto a honeycomb structure to maximize surface area. They last the life of the car, never wearing out, never being used up. Without them, city air would be unbreathable. Catalysts work by lowering activation energy. Activation energy is the hill. A reaction must climb. Think of a boulder at the top of a hill. It wants to roll down, but it is stuck behind a small ridge. The ridge is the activation energy. A catalyst does not push the boulder. It cuts a pathway around the ridge. The boulder still ends up at the bottom, but it takes a lower, easier route. That is why the reaction speeds up. The catalyst never changes the final outcome. It only changes the path. Some catalysts are specific. One enzyme will not work on another substrate. That specificity is how cells control thousands of reactions without chaos. Each reaction has its own enzyme. Some catalysts are general. Acid and base catalysts work on many different reactions. A drop of acid can speed up the breakdown of many molecules. That is why you add lemon juice, acid, to jam. It helps break down pectin, making the jam set. That is why baking soda, base, is added to cakes. It helps the browning reaction, producing a golden crust. Catalysts can be poisoned. Impurities can bind to the active site, blocking it. This is called catalyst poisoning. Lead is a poison for platinum catalysts. That is why leaded gasoline was phased out. It destroyed catalytic converters. Sulfur is a poison for many metal catalysts. That is why natural gas is purified before use to remove sulfur. Catalyst poisoning is a major problem in industry. Engineers must carefully purify reactants to keep catalysts active. The human body uses feedback loops to control its catalysts. Some enzymes are produced only when needed, others are turned off by their own products. This regulation prevents waste. You do not produce digestive enzymes when you have not eaten. You do not break down glucose when your blood sugar is already low. The catalysts are there, but they are waiting for the signal. That is elegant control. Equilibrium, when reactions balance out. A seesaw in a playground. Two children of equal weight sit at opposite ends. They bounce gently, one up, one down. The seesaw never stays perfectly still, but the average position is level. That is equilibrium, not a frozen state, but a dynamic balance. In chemistry, equilibrium occurs when a forward reaction and a reverse reaction proceed at identical rates. Reactants become products at the same speed that products revert to reactants. No net change is visible, yet underneath, molecules are constantly colliding, bonding, and breaking apart. Think of a sealed soda bottle. Carbon dioxide gas dissolves into the liquid, forming carbonic acid. That is the forward step. At the same time, carbonic acid decomposes back into gas and water. The reverse step. When the bottle remains closed, these two processes reach a balance. The concentration of gas in the air pocket above the liquid stops changing. Twist the cap off, and the gas escapes. The balance tips. More carbon dioxide fizzes out of solution until a new equilibrium, now with less gas, is established. That simple observation is the heart of Le Chatelier's principle. Le Chatelier's principle states that a system at equilibrium will adjust to counteract any external disturbance. Increase the amount of a reactant, and the reaction shifts to make more product. Raise the temperature, and the reaction that absorbs heat gets favored. Squeeze a gas reaction by increasing pressure, and the side with fewer gas molecules wins. The system does not think. It simply follows the statistical probabilities of molecular collisions. But the effect is predictable and reproducible. Consider the reaction that produces ammonia, essential for fertilizer. Nitrogen gas and hydrogen gas combine to form ammonia. The forward reaction releases heat. The reverse reaction absorbs heat. 4 molecules of reactant gas become 2 molecules of product gas. To push the equilibrium toward ammonia, industrial chemists use high pressure, favoring fewer gas molecules, and moderate temperature to keep the reaction fast enough while not shifting too far backward. They also remove ammonia as it forms, constantly disturbing the equilibrium to pull more product. Your own body relies on equilibrium every moment. The pH of your blood must stay between 7.35 and 7.45. Your lungs and kidneys manage this by shifting equilibria. When blood becomes too acidic, you breathe faster, exhaling more carbon dioxide. That removes an acid, pulling the equilibrium toward less acidic conditions. When blood becomes too basic, you breathe slower, retaining carbon dioxide. These adjustments happen without your awareness. They are homeostatic equilibria, fine-tuned by evolution. Even a simple salt solution reaches equilibrium. Table salt dissolving in water reaches a point where salt crystals dissolve at the same rate that ions reform crystals. That is why a saturated salt solution contains visible crystals at the bottom. The system has found its balance. Add more salt, and it will not dissolve. Heat the solution, and more salt may dissolve because higher temperatures shift the equilibrium for many solids. Catalysts do not change the equilibrium position. They simply help the system reach equilibrium faster. In your body, enzymes are catalysts that accelerate thousands of reactions to equilibrium in milliseconds rather than years. Without them, you would be a bag of chemicals slowly approaching balance, too slowly to sustain life. The equilibrium constants stay the same. Only the time changes. Equilibrium is not a finish line. It is a steady state of continuous exchange. The molecules in your body today will not be the same molecules in your body a year from now. But the patterns, the concentrations, the pH, the temperature, remain constant. That is dynamic equilibrium. It is how you stay alive while atoms flow through you like water through a river. Chemistry in cooking and food. Step into your kitchen. The stove, the refrigerator, the pantry. Each holds chemical reactions waiting to happen. Cooking is not just art. It is applied chemistry using heat, acid, base, and time to transform raw ingredients into something delicious. Every change you see, browning, rising, thickening, setting, has a molecular explanation. Understanding a few key reactions can make you a better cook and a more curious eater. The Maillard reaction is responsible for the deep, savory flavors of grilled steak, toasted bread, roasted coffee, and dark beer. It occurs when proteins, amino acids, and sugars react at temperatures above 140 degrees Celsius. The reaction produces hundreds of volatile compounds, furans, pyrazines, thiols, that create nutty, toasty, meaty notes. A steak cooked rare has a thin brown crust because the Maillard reaction only happens at the surface. A well-done steak is brown throughout, but also drier and tougher. The balance is personal. Caramelization is different. It involves only sugars, no proteins. As the temperature rises beyond 160 degrees, sucrose, table sugar, melts into a clear syrup. Further heating breaks the sugar molecules into fragments that recombine into new compounds. The syrup darkens from yellow to amber to dark brown. The flavor shifts from sweet to nutty to slightly bitter. Perfect caramel requires careful attention. A few degrees too hot, and it burns to bitter black. Caramelization is why onions become sweet when cooked slowly. Their natural sugars break down into simpler, sweeter compounds. Denaturation is the unraveling of proteins. Egg whites are liquid because the egg white proteins are folded into compact globules. Heat breaks the weak hydrogen bonds that hold these folds. The proteins unfold and then stick to each other, forming a solid mesh. That is why a fried egg becomes opaque and firm. The same process happens when you cook meat. Collagen, a tough connective protein, denatures into gelatin, which is soft and slippery. That is why slow-cooked meat becomes tender. The collagen turns into gelatin over hours of gentle heat. Acids and bases modify food dramatically. Baking soda, sodium bicarbonate, is a base. When it reacts with an acid, buttermilk, yogurt, vinegar, or cream of tartar, it produces carbon dioxide gas. Those gas bubbles expand in the heat of the oven, making pancakes, cakes, and quick breads rise. Too much baking soda leaves a soapy, bitter taste because unreacted base remains. Baking powder contains both baking soda and a dry acid, so that it works without additional ingredients. Acids tenderize meat by breaking down protein fibers. A marinade with vinegar, lemon juice, or yogurt makes chicken or beef softer, but prolonged exposure can over-tenderize, turning meat mushy. Acids also brighten flavors. A squeeze of lemon on grilled fish, or a splash of vinegar in a sauce cuts through richness, balancing the taste. The chemistry of sour is the chemistry of hydrogen ions, and your tongue is very sensitive to them. Fats and oils are essential for heat transfer and flavor. When you saute garlic in oil, the oil carries the fat-soluble compounds, allicin, diallyl disulfide, from the garlic into the dish. Water would not dissolve these flavors. Fats also coat your tongue, carrying flavor molecules to your taste receptors. That is why low-fat foods often taste bland. The texture of fat, creamy, smooth, adds pleasure independent of taste. Emulsions are mixtures of two liquids that normally separate, like oil and vinegar. A vinaigrette is a temporary emulsion. You shake it, and the oil breaks into tiny droplets dispersed in the vinegar. Mustard contains mucilage, a natural emulsifier that coats the oil. Our droplets, keeping them suspended longer. Mayonnaise is a stable emulsion of oil in egg yolk and vinegar. The lecithin in egg yolks is a powerful emulsifier. Break the emulsion by overheating or adding too much acid, and the mayonnaise separates into a greasy puddle. Gelatin is denatured collagen. When you simmer bones and skin, the collagen unravels and dissolves in the water. As the broth cools, the gelatin molecules form a loose, three-dimensional network that traps water, creating a wobbly solid. That is aspic, panna cotta, or jello. Heat it, and the network melts. Cool it, and it reforms. This reversibility is rare in cooking. Most reactions are one way. The kitchen is a laboratory where you are the chemist. You adjust temperatures, measure ingredients, observe results. Every meal is a set of experiments, and when they work, you get to eat the data. That is the delicious intersection of chemistry and life. Why smells and flavors exist. Take a deep breath through your nose. What do you smell? Perhaps nothing distinct, just room air. But if you were to sniff a rose, your brain would instantly recognize its fragrance. That recognition is a chemical event. Odor molecules float off the rose, travel through the air, and land on receptors deep in your nasal cavity. Each receptor is a protein that changes shape when a matching molecule binds. That shape change triggers an electrical signal that zips along a nerve to your brain. Your brain decodes the pattern of activated receptors and says rose. Humans have about 400 different types of odor receptors. Each receptor can bind to many different molecules, and each molecule can bind to many different receptors. The combination of receptors activated creates a unique pattern. Your brain learns these patterns. By adulthood, you can distinguish thousands of distinct odors. Some patterns are innate. The smell of rotten food triggers disgust without learning. Others are cultural. The smell of durian fruit is heavenly in Southeast Asia and repulsive to many Westerners. The smell of rain on dry earth is called petrichor. It comes from a compound called geosmin, produced by soil bacteria. Your nose is incredibly sensitive to geosmin. You can detect it at a few parts per trillion. That sensitivity likely evolved because rain was essential for survival. The smell of rain meant water was nearby. Geosmin also gives beets their earthy flavor. Your brain did not need to learn this one. It came pre-wired. Flavor is not the same as smell. Your tongue has only 5 basic taste receptors: sweet, sour, salty, bitter, and umami. Sweet detects sugars and some artificial sweeteners. Sour detects acids, hydrogen ions. Salty detects sodium ions. Bitter detects many different compounds, often toxins. Umami detects glutamate, an amino acid found in meat, cheese, tomatoes, and mushrooms. These 5 tastes are limited. The explosion of pleasure when you eat a strawberry comes almost entirely from its volatile molecules reaching your nose through the back of your throat. Pinch your nose while eating a jelly bean. You will taste sweetness, but not the fruit flavor. Release your nose and the flavor floods in. Vanilla is a single molecule, vanillin. Natural vanilla beans contain vanillin plus hundreds of other compounds that add complexity. Your nose cannot tell the difference between natural and synthetic vanillin. They are the same molecule, but the other compounds in natural vanilla extract contribute subtle notes that some people prefer. Artificial vanilla tastes flat because it lacks those companions. The smell of a skunk comes from thiols, sulfur-containing molecules. Thiols are also added to natural gas, so you can detect leaks. Your nose is exquisitely sensitive to thiols because sulfur compounds often signal danger. A tiny whiff of skunk spray is enough to trigger disgust. But thiols can be pleasant in small doses. Grapefruit, coffee, and some cheeses contain thiols that add complexity. Why do some smells trigger strong memories? The olfactory nerve sends signals directly to the amygdala, emotion center, and hippocampus, memory center, without passing through the thalamus like other senses. That direct connection means smells can evoke memories more vividly and emotionally than sights or sounds. The smell of a particular perfume might flood you with a memory of a grandparent because the molecules bypass your brain's filters. Flavor is also affected by temperature. Hot food releases more volatile molecules, so it smells stronger. That is why hot coffee is more aromatic than iced coffee. But cold numbs your tongue receptors, so sweet things taste less sweet. Ice cream needs extra sugar to taste sweet when cold. Warm soda tastes sickly sweet because the sugar is more detectable. The next time you eat, pause for a moment. Breathe through your nose while chewing. Notice the layers, the 5 tastes on your tongue, the complex orchestra of volatile molecules in your nose. You are tasting chemistry, billions of years in the making. The molecules that trigger pleasure evolved to attract you to ripe fruit, to warn you away from poison, to guide you toward nutrients. You are the product of that evolutionary conversation. The chemistry of the human body. Your body is a marvel of chemical organization. It contains about 7 octillion atoms, a 7 followed by 27 zeros. Most are hydrogen, oxygen, carbon, and nitrogen. The rest are calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, and trace elements. These atoms are not static. They flow in and out through food, water, and air. Every week, you replace a significant fraction of your atoms. The pattern, the shape, the identity persists, but the material is new. Water makes up about 60% of your body. It transports nutrients, dissolves waste, regulates temperature, and cushions joints. Without water, your cells would collapse, your blood would thicken, and your kidneys would fail. Even a 2% loss of body water impairs thinking. That is why thirst is urgent. The water molecule, bent and polar, is the perfect solvent for life. Proteins are the workers. They are chains of amino acids folded into specific 3-dimensional shapes. The sequence of amino acids is determined by genes. The shape determines function. Enzymes are proteins that catalyze reactions. Hemoglobin is a protein that carries oxygen. Collagen is a protein that provides structure to skin and bones. Antibodies are proteins that defend against infection. Your body makes tens of thousands of different proteins, each with a precise job. Carbohydrates are fuel. Sugars, starches, and fibers are all carbohydrates. Glucose, a simple sugar, is the primary fuel for your cells. Your body breaks it down through a series of reactions called cellular respiration, releasing energy stored in ATP, adenosine triphosphate. ATP is the energy currency of the cell. When you need energy to think, to move, to breathe, your cells spend ATP. When you rest, your cells recharge. ATP by breaking down glucose. Fats, or lipids, serve multiple roles. They store energy in a concentrated form. A gram of fat contains more than twice the energy of a gram of carbohydrate. They form the membranes that surround every cell. They act as signaling molecules, hormones, and as insulation. The fat under your skin keeps you warm. The fat around your organs cushions them. Your brain is nearly 60% fat, mostly in the myelin sheaths that insulate nerve fibers. DNA is the instruction manual. It is a double helix of nucleotides: adenine, thymine, guanine, cytosine. The sequence of these bases encodes the information to make proteins. Your DNA is about 3 billion base pairs long. If stretched out, it would reach about 2 meters, but it is coiled into 46 chromosomes inside the nucleus of almost every cell. The famous double helix is held together by hydrogen bonds, weak but numerous, between complementary bases. Minerals are essential helpers. Calcium builds bones and teeth, but also helps nerves fire and muscles contract. Phosphorus is part of DNA, RNA, and ATP. Potassium and sodium are critical for nerve signals, the electrical impulses that allow you to think and move. Iron is at the core of hemoglobin, binding oxygen in your lungs and releasing it in your tissues. Zinc is a cofactor for hundreds of enzymes. Iodine is part of thyroid hormones that control metabolism. You need tiny amounts, but you cannot live without them. Hormones are chemical messengers. They travel through your bloodstream, binding to receptors on target cells. Insulin tells cells to take up glucose from the blood. Adrenaline prepares your body for fight or flight, increasing heart rate, dilating airways, releasing glucose. Thyroid hormones set your metabolic rate. Estrogen and testosterone regulate reproduction and many other functions. Each hormone is a molecule, a steroid, a peptide, or an amine, shaped to fit specific receptors. Your body is constantly building and breaking down. Old cells die and are replaced. Proteins are degraded into amino acids and rebuilt into new proteins. Fat stores are mobilized and replenished. This turnover requires energy and raw materials. That is why you need to eat. Food is not just fuel. It is the source of the amino acids, sugars, and fats that become your body. Tonight, as you rest, your body is not idle. Your liver is processing toxins. Your kidneys are balancing electrolytes. Your brain is consolidating memories. Your immune system is patrolling for invaders. All of this is chemistry. Silent, relentless, precise. You're a chemical reaction that has been running since the moment of conception, and it will continue through the night, without your direction, without your awareness, simply because that is chemistry's nature. Materials that change civilization. The story of humanity is written in materials. Our ancestors used stone, then clay, then bronze, then iron. Each new material enabled new ways of living. Stone axes cleared forests. Bronze swords changed warfare. Iron plows allowed farming of heavy soils. Steel rails connected continents. Concrete built empires. Aluminum made flight possible. Silicon created the digital age. Behind every material is chemistry, the understanding of elements and their combinations. Stone was the first engineered material. Flint knapping, striking one stone against another to produce sharp flakes, is a form of applied mineralogy. Certain stones break conchoidally, producing razor edges. Others crumble. Choosing the right stone required observation and experimentation. That is the beginning of material science. Bronze is an alloy of copper and tin. Pure copper is soft. Adding about 10% tin makes it harder and more resistant to corrosion. The Bronze Age began around 3300 BCE. It required long-distance trade, copper from Cyprus or Sinai, tin from Cornwall or Afghanistan. Bronze tools were superior to stone, but expensive. Only the wealthy could afford them. Iron replaced bronze because iron ore is everywhere, but smelting iron requires higher temperatures, about 1,200 degrees Celsius, and more technical skill. The Hittites developed iron smelting around 1200 BCE, keeping it secret for centuries. When the secret spread, iron became cheap. Iron plows allowed agriculture on heavy clay soils, and axes cleared forests faster. The Iron Age was an agricultural revolution. Steel is iron with a controlled amount of carbon, between 0.2 and 2%. Plain iron is too soft. Add carbon, and it becomes hard and strong. Early steel was made by accident. Blacksmiths learned to control carbon content by heating iron with charcoal, then quenching in water. The Bessemer process made steel cheap and plentiful. Steel beams allowed skyscrapers. Steel ships replaced wooden ships. The modern industrial world is built on steel. Concrete is a mixture of cement, water, and aggregate. The Romans discovered that volcanic ash, lime, and seawater produced a mortar that hardened even underwater. They built the Pantheon, still standing after 1,800 years, with a concrete dome. The recipe was lost for centuries and rediscovered in the 1700s. Reinforced concrete, concrete with steel bars, was developed in the 19th century. It combines the compressive strength of concrete with the tensile strength of steel. Glass is melted sand with soda ash and lime. The first glass was made in Mesopotamia about 3,500 years ago. The Romans perfected glass blowing, making it cheap. Glass windows let light in while keeping weather out. Lenses enabled microscopes and telescopes, tools that expanded human vision. Glass beakers and flasks made chemistry visible. Without glass, modern science would be blind. Aluminum was once more precious than gold. Napoleon III served honored guests with aluminum cutlery. Extraction was difficult because aluminum is very reactive. In 1886, researchers discovered electrolysis, passing an electric current through a molten mixture of aluminum oxide and cryolite. The price plummeted. Aluminum is light, strong, and corrosion resistant. It replaced copper in power lines and wood in window frames. Plastics are synthetic polymers, long chains of repeating molecules. Bakelite was the first fully synthetic plastic. Nylon was the first synthetic fiber. Polyethylene is now used in bags and bottles. Plastics are cheap, light, and durable. But that durability is a problem. Most do not biodegrade. A plastic bottle takes 450 years to decompose. Chemists are working on biodegradable plastics and better recycling methods. Silicon is a metalloid, the basis of microchips. By doping it with tiny amounts of other elements, you can control its electrical conductivity precisely. That control enables transistors. Thousands of transistors make a microprocessor. Billions make a computer. Silicon chips are the brains of every digital device: phones, laptops, cars. The information age rests on a material that was barely known a century ago. Each material tells a story of human curiosity. They are ideas made solid, chemistry made useful. Tonight, you are surrounded by them. The steel springs in your mattress, the concrete in your walls, the glass in your window, the silicon in the chip that brought you this voice. All are the legacy of chemistry. They hold you, shelter you, and connect you. They will still be here long after you are gone. Plastics, metals, and modern chemistry. Look around your room. The frame of your glasses, the casing of your phone, the insulation on your charger cord, the buttons on your pajamas. Many of these are plastic. The word plastic comes from the Greek plastikos, meaning able to be molded. Plastics are synthetic polymers, long chains of repeating molecular units. The first fully synthetic plastic was bakelite, invented in 1907 by Leo Baekeland. It was hard, heat-resistant, and non-conductive. It replaced wood and metal in radios, telephones, and jewelry. Bakelite was the beginning of the age of plastics. How are plastics made? Most start with petroleum or natural gas. The raw material is cracked into smaller molecules like ethylene and propylene. Under pressure and with catalysts, these molecules link into chains. Polymerization. Depending on the conditions, you get different plastics. Polyethylene, plastic bags, bottles, is soft and flexible. Polystyrene, cups, insulation, is rigid and brittle. Polyvinyl chloride, PVC, pipes, is tough and durable. Nylon is a polyamide, strong and elastic, used in clothing and ropes. Each plastic has a unique structure and set of properties. Plastics are cheap, light, moldable, and durable. That durability is a double-edged sword. Most plastics do not biodegrade. They break into smaller pieces, called microplastics, which accumulate in oceans, soil, and even inside living organisms. A plastic bottle takes 450 years to decompose. A fishing line takes 600 years. This persistence is a chemical problem because the bonds in plastics are strong and not easily broken by bacteria or fungi. Researchers are working on biodegradable plastics made from cornstarch or vegetable oils, but these are not yet cheap or strong enough to replace traditional plastics. Metals have been with us much longer. Bronze, iron, steel, aluminum, copper. Each transformed civilization. Modern metallurgy is chemistry at an industrial scale. Pure metals are often too soft or reactive. Alloys combine metals to improve properties. Stainless steel is iron with chromium and nickel. The chromium forms a thin oxide layer that prevents rust. Brass is copper and zinc, harder than copper and more corrosion resistant. Bronze is copper and tin, harder than copper and easier to cast. Solder is tin and lead, now often tin and silver, with a low melting point for joining wires. Aluminum is the most abundant metal in the Earth's crust. but it took until the 19th century to extract it cheaply. The Hall-Héroult process uses electrolysis. An electric current passes through a molten mixture of aluminum oxide and cryolite. Pure aluminum deposits at the cathode. Aluminum is light, 1/3 the density of steel, strong when alloyed, and corrosion resistant because of its oxide layer. It is used in airplanes, cars, cans, foil, and smartphone cases. Recycling aluminum uses only 5% of the energy needed to make it from ore, which is why aluminum cans are the most recycled beverage container. Titanium is another modern metal. It is as strong as steel, but 45% lighter. It is also extremely corrosion resistant, even to seawater and chlorine. Titanium is used in jet engines, artificial joints, and bicycle frames, but it is expensive to extract. The Kroll process uses magnesium to reduce titanium tetrachloride, producing a titanium sponge that is then melted. The high cost limits titanium to specialized applications. Metals and plastics often work together. Your phone has a plastic case, light, insulating, and metal components, conductive, strong. The circuit board has copper traces on a plastic fiberglass substrate. The battery has metal electrodes and a plastic separator. Modern materials are hybrid, combining the best of each. Chemistry gives you the ability to design materials at the molecular level, tuning properties for specific needs. One of the newest classes of materials is composites. Fiberglass is glass fibers embedded in a plastic matrix. It is strong, light, and corrosion resistant. Carbon fiber is carbon filaments in a plastic matrix. It is stronger than steel and lighter than aluminum. Carbon fiber is used in racing cars, bicycles, and aircraft. The Boeing 787 Dreamliner is 50% carbon fiber by weight. Without modern chemistry, such materials would not exist. As you rest here, you are surrounded by the products of materials chemistry. The springs in your mattress are steel. The foam is polyurethane. The fabric is polyester or cotton. The walls are plasterboard, calcium sulfate, or concrete. The window glass is silica. Each material was chosen for a reason: strength, flexibility, insulation, transparency. And each material came from a laboratory, a factory, and a long chain of chemical discoveries. You are sleeping on a history of innovation. The role of chemistry in medicine. Before chemistry, medicine was guesswork. Herbs, rituals, bloodletting. Some worked, many did not. Chemistry gave medicine precision. It gave us aspirin, antibiotics, anesthetics, vaccines, and cancer drugs. It gave us the ability to synthesize molecules that never existed in nature, designed to fit specific targets in the body. Modern medicine is applied chemistry, and without it, you would not expect to live past 40. Aspirin is one of the oldest synthetic drugs. The active ingredient, salicin, comes from willow bark. Hippocrates prescribed it for pain and fever. In the 19th century, chemists isolated salicylic acid, but it irritated the stomach. In 1897, a chemist at Bayer named Felix Hoffmann added an acetyl group, creating acetyl salicylic acid, aspirin. It worked better and was gentler on the stomach. Aspirin is now used for pain, fever, inflammation, and in low doses to prevent heart attacks. It is one of the most successful drugs ever made. Antibiotics changed the world. Before penicillin, a minor infection could kill you. In 1928, Alexander Fleming noticed that a mold called penicillium killed bacteria in a petri dish. he could not isolate the active compound. A decade later, Howard Florey, Ernst Chain, and their team purified penicillin and showed it could cure bacterial infections in mice and humans. Penicillin works by inhibiting the synthesis of bacterial cell walls. Human cells do not have cell walls, so the drug is selective. Penicillin saved millions of lives in World War II and beyond. Today, many antibiotics are semi-synthetic, natural molecules modified by chemists to improve potency, reduce side effects, or overcome resistance. Amoxicillin, tetracycline, ciprofloxacin. Each is a chemical compound designed to kill bacteria without harming you. But bacteria evolve resistance. Overuse of antibiotics accelerates this evolution. Chemistry must constantly develop new antibiotics to stay ahead. It is an arms race. Anesthetics allow surgery without pain. Early anesthetics, ether, chloroform, nitrous oxide, laughing gas, were crude and dangerous. Modern anesthetics are precise. They target specific receptors in the nervous system, inducing unconsciousness, amnesia, and muscle relaxation. The chemistry is delicate. A tiny dose too much can stop breathing. A tiny dose too little, and the patient wakes up. Anesthesiologists are applied chemists, monitoring drug levels, adjusting doses, keeping you safe. Vaccines teach your immune system to recognize pathogens. Chemistry is involved in every step, purifying antigens, synthesizing adjuvants, substances that boost the immune response, stabilizing formulations, and checking purity. The mRNA vaccines for COVID-19 use synthetic messenger RNA, a chemical code that tells your cells to make a viral protein. That protein triggers immunity. The mRNA itself is synthesized by chemical reactions, then packaged in lipid nanoparticles, also chemicals. The entire vaccine is a product of chemistry. Cancer drugs are often toxic to dividing cells. They target DNA replication or cell division. The challenge is selectivity. Cancer cells divide faster than most normal cells, but some normal cells, hair follicles, gut lining, also divide quickly. That is why chemotherapy causes hair loss and nausea. Newer drugs are more targeted. Imatinib, Gleevec, blocks a specific protein that drives certain leukemias. It was designed by chemists who understood the protein's shape. That rational drug design is a triumph of molecular chemistry. Even diagnostic tools rely on chemistry. Blood tests measure glucose, cholesterol, enzymes, hormones. Pregnancy tests detect human chorionic gonadotropin, HCG, using antibodies. COVID-19 tests detect viral RNA using polymerase chain reaction, PCR, a chemical amplification process. Imaging contrast agents for MRI, CT scans are chemical compounds that enhance the visibility of tissues. Without chemistry, doctors would be blind. The medicines in your bathroom cabinet, pain relievers, antacids, allergy pills, antiseptics, are all chemical compounds. They have been tested, purified, and formulated to work predictably. They are the result of centuries of accumulated knowledge, and they are why a toothache today is an inconvenience, not a death sentence. Chemistry is the silent partner in every prescription, every recovery, every life saved. The future of chemistry and new discoveries. Chemistry is not finished. There are still mysteries to solve, problems to fix, materials to invent. The periodic table may be full, but the combinations are infinite. Chemists are working on new batteries, new medicines, new plastics that degrade safely, new catalysts that mimic enzymes, new ways to capture carbon dioxide, new methods to create clean fuel. The future of chemistry is about sustainability, precision, and discovery. Batteries are a frontier. Lithium-ion batteries power phones, laptops, and electric cars. But lithium is scarce, and batteries can catch fire. Chemists are developing alternatives. Sodium-ion batteries, using abundant sodium. Solid-state batteries, no liquid electrolyte safer. And lithium-sulfur batteries, higher energy density. Each requires new materials, new electrode designs, new electrolytes. A breakthrough in battery chemistry could make electric cars cheaper and grid storage feasible, transforming energy systems. Carbon capture is another challenge. Burning fossil fuels releases carbon dioxide, which traps heat. Removing CO2 from the air or from power plant exhaust is chemically difficult. CO2 is dilute, 0.04% in air, and stable. Chemists are designing new materials, metal organic frameworks, MOFs, zeolites, membranes, that selectively bind CO2. Some are like molecular sponges. Others use electricity to convert CO2 into formic acid or ethanol, turning waste into fuel. If these technologies scale up, they could help reverse climate change. Green chemistry is the design of chemical products and processes that reduce or eliminate hazardous substances. It means using renewable feedstocks, plants instead of petroleum, designing biodegradable products, avoiding toxic solvents, and maximizing atom economy, using as much of the starting material as possible. The 12 principles of green chemistry guide researchers towards safer, more sustainable practices. A green chemist might synthesize a drug using water instead of benzene, or make a plastic from cornstarch instead of crude oil. Medicinal chemistry is becoming more precise. With better understanding of protein structures, chemists can design drugs that fit perfectly, like a key in a lock. Computer modeling speeds up the process. Instead of testing millions of random molecules, researchers screen virtual libraries and synthesize only the most promising candidates. This rational drug design produced HIV protease inhibitors, kinase inhibitors for cancer, and antiviral drugs for hepatitis C. It will produce more. Synthetic biology blurs the line between chemistry and biology. Chemists can now edit DNA, create synthetic genomes, and engineer bacteria to produce medicines, fuels, and materials. Insulin, once extracted from pig pancreases, is now made by modified E. coli. Artemisinin, an antimalarial drug, is produced by yeast engineered with plant genes. These are chemical factories in living cells. The future may bring bacteria that eat plastic, yeast that makes rubber, or algae that produce hydrogen. Nanotechnology is chemistry at the scale of billions of a meter. At that scale, materials behave differently. Gold nanoparticles are red, not yellow. Carbon nanotubes are stronger than steel. Quantum dots emit precise colors of light when excited. Chemists can build structures atom by atom, creating new materials with properties that do not exist in nature. Nanotechnology is already used in sunscreen, zinc oxide nanoparticles, stain-resistant fabrics, and some cancer treatments. Artificial photosynthesis is a dream, using sunlight to split water into hydrogen and oxygen, then using the hydrogen as fuel. Plants do this naturally, but inefficiently. Chemists are designing artificial leaves, devices that mimic photosynthesis, but convert solar energy to chemical fuel at higher efficiency. If successful, artificial photosynthesis could provide clean, storable energy from sunlight. It would be a chemical solution to the energy problem. The future also includes chemistry in space. Astronauts will need to synthesize medicines, recycle water, and produce fuel from local resources, perhaps extracting oxygen from lunar soil or carbon dioxide from the Martian atmosphere. Chemistry will make long-duration spaceflight possible. It will help humans become multiplanetary. You are living through a golden age of chemistry. The problems are huge: climate change, antibiotic resistance, energy storage. But the tools are powerful. Chemists can see atoms, move molecules, and design new compounds on a computer. They can learn from nature and surpass it. The discoveries of the next 50 years will likely be as transformative as those of the last 150. And you, resting here, are part of that story, not as a chemist, but as a beneficiary. The future will be made of molecules, and chemists will be the architects. The quiet beauty of chemistry. After all these sections, from ancient atoms to future fuels, what remains? A sense of quiet beauty. Chemistry is not just a set of facts to memorize. It is a way of seeing the world. When you look at a flower, a chemist sees pigments, scents, and the energy of sunlight stored in molecules. When you taste bread, a chemist sees the Maillard reaction, yeast fermentation, and the transformation of starch into sugar. When you feel the warmth of a blanket, a chemist sees van der Waals forces, thermal conductivity, and the slow vibration of atoms. The world becomes richer, not poorer, when you understand its chemistry. There is beauty in the simplicity of the periodic table, a single chart that organizes everything. There is beauty in the complexity of a protein folding into its precise shape. There is beauty in the dance of electrons, in the breaking and forming of bonds, in the flow of energy through reactions. Chemistry is the poetry of matter. It is the language that atoms speak, and you have been learning that language section by section as you drifted towards sleep. Think of the molecules in your own body. They are not random. They are arranged with exquisite precision. Your DNA contains the instructions for making every protein you need. Your enzymes catalyze reactions with speeds that industrial chemists envy. Your cell membranes self-assemble into bilayers that separate inside from outside. You are a masterpiece of molecular engineering, honed by billions of years of evolution, and you did not have to design any of it. You just had to be born. Chemistry also teaches humility. You are made of the same elements as the stars. The carbon in your cells was forged in a dying sun. The oxygen you breathe was produced by bacteria billions of years ago. The water you drink has cycled through oceans, clouds, and rivers since the earth was young. You are not separate from the universe. You are a temporary expression of it. That is not a cause for despair. It is a cause for wonder. You belong here because you are made of here. There is also beauty in the fact that chemistry works. It is reliable. Water freezes at 0 degrees Celsius every time, under the same conditions. Salt dissolves in water every time. Baking soda and vinegar fizz every time. This reliability is the foundation of technology. It is why you can trust that your car will start, your medicine will work, your food will be safe. The world is lawful, and chemistry has uncovered many of those laws. You can rest in that lawfulness. As this long journey through chemistry comes to a close, you might feel a gentle sadness. the kind that comes at the end of a good story. But the story is not over. Chemistry is happening right now, in every corner of the room, in every cell of your body. The atoms are still dancing. The bonds are still holding. The energy is still flowing. You're part of that story, whether you are awake or asleep. And tomorrow, when you wake, you'll see the world a little differently, a little more wonder, a little more gratitude, a little more chemistry. So close your eyes now. Feel the weight of your blanket. That is atoms pressing against atoms. Feel the air moving in and out of your lungs. That is oxygen and carbon dioxide trading places. Feel the warmth of your own body. That is exothermic reactions, thousands of them, keeping you alive. You are a chemical system, beautifully balanced, perfectly imperfect, and you are allowed to rest. The voice fades now. The molecules in your pillows settle into their arrangements. The hydrogen bonds in your blankets hold their gentle grip. Your own body continues its quiet chemistry. Enzymes working, blood flowing, neurons resting. No need to remember anything. No need to understand everything. Just the soft rhythm of breath, the slow pulse of sleep approaching. Chemistry does not demand your attention. It simply is, and you are part of it. Part of the atoms, the bonds, the energy. Part of the universe becoming aware of itself for a brief, beautiful moment. Rest now. Let the chemistry carry you. Sweet dreams.